Okay, so now we are starting. So with a warm welcome to all of you from IIT Bombay. I am Payal Mukherjee. I work as a project manager in FOSSEE. So Deepak, is it started? I didn't ask you before starting.
It started.
Okay, thanks. Okay, so welcome once again. And this is a workshop on the intermediate level of OpenFOAM organized by FOSSEE IIT Bombay. This workshop is a part of a learning program that was started way back in August, in the month of August 2024. And we are concluding it today with this intermediate level workshop, but we are not ending the learning process or working together. Okay, so this is just a formal end of the learning program that we launched in the month of August. And those of you are new to it, and because we are doing it online. We initially it was planned that we will do this workshop offline in person at IIT Bombay, but due to many requests that were coming to us through emails and LinkedIn, that we also want to attend, but we don't have the logistics to visit IIT Bombay for one day to attend this workshop. So due to all this, we decided to hold this workshop in online mode so that we can reach out to many participants throughout the country and abroad, and we can also record this, and people can refer to this whole workshop later on. Okay, so this workshop is organized by FOSSEE. I hope you all know what is FOSSEE. FOSSEE it's a project which has been developed at IIT Bombay. The full form of FOSSEE is free and open source software for education. Why the double E? It is because earlier it was launched only for the engineering field of education. That is why the engineering education was there earlier. But now we are offering the software which are useful for non-engineering stream of studies as well. For example, geology and geosciences. We also offer for the animation field, animation and the graphics field. We also offer for pure hardcore chemistry, and applied physics, everything. So now FOSSEE is open for all the streams of education. Okay, so this workshop will be conducted by the team members of OpenFOAM of FOSSEE. The team members are Mr. John Pinto, Mr. Evan Fernandez, and Mr. Manjil Situla. Manjil is working from Nepal, and John and Evan is from IIT Bombay. They are at IIT Bombay. And though this FOSSEE project is developed at IIT Bombay, we work, we network with people, and we have partners who are faculty members in esteemed institutions of India. And we also have partnered with the corporate people. We launched the advisory board of the OpenFOAM team of FOSSEE. And it was done yesterday. The launch ceremony was done yesterday at IIT Bombay, and it was a part of the industry academia meet, which was held at IIT Bombay in a hybrid mode. So we had many expert talks by the professionals who work in the CFD industry in the corporate. So henceforth, they will also be our team member. We will work with them as a team. Okay, we will take their inputs as well in the training program of FOSSEE. And we are fortunate to have two members from the advisory board with us today at IIT Bombay. Mr. Pushkar Sheth from Webtech Corporation and Mr. Nikhil Bhamre from CFD Baba. So they will also be there today with us. Okay, and I think you can see the topics that will be covered today in the workshop: conjugate heat transfer and need for advanced meshing, introduction to multiphase simulations, introduction to dynamic meshing, SnappyHexMesh, the usage of SnappyHexMesh, multiple simulations, multiphase simulations, and many more. Okay, so and Professor Naren also will be joining, Naren PR sir from the Sastra University. Okay, he will be joining just after the lunch break. And one more exciting thing is we are going to announce the candidates who are shortlisted by the FOSSEE team of IIT Bombay, by the OpenFOAM team of FOSSEE IIT Bombay. Actually, we have floated the people who are new and who are attending this intermediate level workshop today, and who were not in the who have not enrolled for the August learning session. So actually, we had floated some problem statements, and based on that, we have evaluated some of the candidates. So we have, received a lot of submissions, and out of that, we have screened and filtered a few good submissions who are potential, who have the potential to develop their work as case studies. Okay, so we will announce the name during the workshop today. So please stay tuned to know who all are selected, okay, in this learning program to work with us further. Okay, and these people can also join us in our internship, and we will they will not be screened anymore. They are welcome to join us as interns and fellows because they have already passed the screening test, and their submissions have been accepted by us. Okay, so as a next step, we will handhold them. We will give them some tips so that they can develop their work, and their work can be published as a case study project in at CFD site, which is cfd.fossee.in, and their name, their institution, and their work will be there permanently. So whenever they are applying for higher studies, they are going for job applications, they will be all they can always refer these publications in the future. So anybody can download it, refer it, okay, and develop the case studies as per their own choice of subjects. Okay, so with this, I'll end the introduction talk, and I'll hand over to my team member, my team member, Mr. John Pinto. So over to you, John. You can share the schedule if you like, or you can start directly interacting with them. Thank you. I'll talk to you later. I'll come back. Bye bye. John, over to you.
Thank you, ma'am. I'll just share my screen quickly. Yes. So whatever topics ma'am listed, later. Yeah. So whatever topics file ma'am has listed, we'll be going over them one by one. So before the lunch break, we will be focusing on conjugate heat transfer, and within that, we will also explain the SnappyHexMesh. Then after lunch break, we will go for multi-phase flows. That will be from 2 to 3:30, and from 3:30 to 5, we'll be looking at the dynamic mesh capabilities. So this is how the session is planned. So I will start. So what we are how we are going to go about it. Just 1 minute. Let me go into the slide somewhere. Okay, for some reason the slideshow is not working. Just let me reload this page.
Sir, and make it full screen.
Yeah, I'm trying to. Okay. Yeah, I hope it is in full screen now. Yeah, thank you. So, how we are going to go about this? So we will today because we are short of time, so we will only be demonstrating the various cases, and in the end we will be collecting a feedback form. And don't worry, all of you will get all the case file structures that are there so that you can try later on. Because if we were to do a hands-on session, we will not be able to complete all the topics that we have listed. So we are only going to demonstrate the cases, what is the case setup and how it works. And maybe if you have any queries, we will answer them. But the hands-on component will not be there for this workshop. So we are starting with conjugate heat transfer. So 1 minute. It's not okay. Yeah. So what are the modes of heat transfer? So we for the people who are not familiar with heat transfer, there are three modes of heat transfer. First is conduction, second is convection, and the third is radiation. For conduction, there has to be physical contact between the two materials, or the material will be solid in nature, like when there is no transport of the particles. But convection happens in fluids when there is bulk motion of the fluids. So you can look at this example. So whatever heat is being generated by the stove is going either by convection or radiation to the pan, and from there the heat is being conducted through the solid handle and then to the person who's holding it. But the inside the water, whatever heat is being generated, it is recirculating or it is moving and causing motion within the fluid, and that is convection. Radiation, if radiation is the mode of heat transfer wherein there is no medium in between. So how the energy comes from the sun to us, that comes via radiation, because there is no medium, there's complete vacuum. So these are the three modes. So now conjugate heat transfer is a combination of both heat transfer due to conduction as well as convection. So under which applications do we encounter conjugate heat transfer? So first is, you can see CPU cooling. So your CPU that is being cooled is generating the heat, and that heat is getting spread by these fins and distributed, and then cold air is circulated over this. So there is heat that is first being conducted through the solid material and then convected through the air. So generally in all the applications, you will not have only pure conduction, you will not have only pure convection or radiation, but you will always have a combination of these. That is where conjugate heat transfer simulations come into picture. And the second application you can look at is the heat exchanger. In heat exchanger, always there is a hot fluid flowing through one side. So in this case, the hot fluid is flowing through the tubes, and the cool fluid is flowing through the shell. So heat is being transferred from the hot fluid through the tube material and then to the shell fluid. So in this way, there is convection, conduction, and then again convection. So this to solve this, you need to go for the conjugate heat transfer class of solvers. Okay, so the geometry that we are going to look at today is, basically we thought that, okay, let us simulate one practical case. So we were thinking of simulating the temperature rise in a magnetic core. So the magnetic core of a transformer gets heated during operation. Okay, and that heat needs to be dissipated to the environment for safe working. Otherwise, that core will melt. So for that reason, what we are doing is we are taking a simplified form of the core. Generally, core will have some hollow patches, but we are considering that to be solid for obviously ease, so that we are able to mesh it quickly and demonstrate. But in practical cases, the core will also have what you can say hollow sections. Now this core is 50 mm wide, 30 mm tall, and 10 mm in thickness. And we are considering the working fluid to be air. The air velocity we are taking as 0.01 meter per second. And these are some of the properties of the solid core. Now, if you see, we have the core, but we also need to decide the computational domain. So we will have to keep the core somewhere in the center of the computational domain, and we would need to have a fluid that is around it. So in the fluid, the what you can say, equations for the fluid will be solved. In the core, equations for the solid will be solved. We need to create a mesh, something like this, to be able to solve CHT. Now this can be done in multiple ways. Because this is a simple geometry, we can do this mesh very easily using the toposet utility. That is good enough for basic geometries. But today we wanted to demonstrate to you the SnappyHexMesh dict. So whenever you have complex geometries and you want to place them inside a fluid domain and mesh them, SnappyHexMesh is a very good what you can say candidate. Or then you can also go for third-party applications. You can mesh in any of the desired measure that you want, and then you can import it. Like OpenFOAM has the capability to import mesh from Fluent, so you can import even Fluent mesh using the command Fluent 3D mesh to foam. So now we have understood that if the geometry is complex, there is need for advanced meshing. So I will hand over to Evan, who will demonstrate to you how SnappyHexMesh works, and he will mesh this domain. Once the meshing is done, we will move ahead with the case setup. Okay. So I will hand over to Evan.
Good morning, everyone. I am Evan Fernandez. Start my slide. Okay. So now that we have our mesh, basically have our geometry and everything, we need to mesh it. So before that, let's learn a little bit about the theory behind SnappyHexMesh. So this is the basic outline of what SnappyHex will be doing. Basically, whatever is inside your SnappyHex dict file. First, what is SnappyHexMesh? Most of you might ask. It is a meshing tool that is used to generate a mesh over a 3D object. You can do it over a 2D object as well when the object itself is a complex one. It helps improve your simulation accuracy by refining the mesh around your object. You can add layers depending on how complex your geometry is and what is your application. So the meshing process is as follows. First, you have to generate a background mesh. Now, this is done with the help of block mesh utility within OpenFOAM, or you can use any other external mesher of your choice. Key things to note while doing a background mesh is it should consist only of hexahedral cells. That is, it should be a structured mesh with an approximate aspect ratio of 1 closer to the object itself, your object of interest. And your object has to intersect with the cells of the background mesh, obviously, meaning that your object has to be within that domain. Next, you have the actual geometry file. Now, in this case, in SnappyHex, there are a number of files that it accepts. The widely used one is an HTML file. So you can import an HTML file within the OpenFOAM domain and mesh over it. Now your modeling can be done again with an external modeler. In this case, in a particular case, we've used FreeCAD. Now your geometry will be located in your constant folder. Within that, there'll be a tri-surface folder. Within that, you will have your geometry folder. Now, once you have both of these two are put into the SnappyHexMesh. This is where your actual meshing process begins. This will control your snapping all the way down to your boundary meshing, refinements, removal of cells, and the addition of layers. Once this is done, then it will move to OpenFOAM. Basically, it will generate a mesh file that is easily readable by OpenFOAM itself. First now, moving to the background mesh. The background mesh, as mentioned before, it is generated with the help of the block mesh utility, consists of hexahedrals. And the cells, basically the cell size that you give of your background mesh is your base cell. Based on this cell size, your further refinements will happen. And this base mesh will cover your entire domain. Then you have refining your background mesh. Now, once you've generated your background mesh, closer to your object of interest, you will have a finer mesh. That is done with the castellated mesh controls within your SnappyHex. All of these features, I will explain it once we enter the actual SnappyHex dict file. What this does is it will split your base mesh into smaller meshes depending on the refinement layer that we specify. And these edges of the object itself is extracted with the help of the surface features dict that will be in your system folder. So speaking of refinement layers, as mentioned before, you have your base level over here. This one is your block mesh cell size. Now, when we specify a level to it, it will split that base mesh into 4 equal parts. And then as we increase the levels, each of those 4 cells will be split into a smaller 4 cells. So that's how the leveling refinement levels work in SnappyHex. Now, once we've done a refinement level and you need to move to the next process, that is your removing of cells. In this process, all the unwanted cells, like if you want to do a simulation over an airfoil, all the cells within the airfoil will not be necessary because we're only calculating all the flow around it. So these unwanted cells are removed with the help of location and mesh keyword within that SnappyHex. What this location in mesh does is that you have to specify one specific point within your computational domain. Now, in this case, if I specify the point within this outer domain, it will keep all the cells greater than 50%, and anything that is lower than that within this object itself, it will remove them. Similarly, if I specify the point within this airfoil, it will mesh everything within this airfoil itself, and it will remove all the cells around the airfoil. So that way you can specify whether you want an internal mesh or you want an external mesh over your body. Then once the meshing removal, everything is done, you will have jagged edges. Like as you can see over here, these cells need to be refined a little bit. That is done with the snap mesh to feature. So this is done by the snap controls. This ensures that you get a good quality mesh that is usable in simple terms. Once that is done, the final step is to add a layer around your object of interest. What this does is it will smooth out the layers around your object, and any irregular cells that are there, it will basically just refine it around your object. So speaking of the case structure, this is a case structure that we are going to move into. You have your zero, constant, and system. Within your constant folder, as I mentioned, you have your try surface. This is where your metal, basically your HTL file will be there. Along with the HTL file, when you run in the system folder, the surface features dict, when we run this command, that is a surface feature, it will generate an e-mesh within your try surface folder, and it will generate another folder within your constant folder. I'll show all of that further. Once your surface features, this utility is done, we move to the SnappyHexMesh dict. This contains all your meshing parameters, all the refinements, cell size, anything that you have to specify, everything is done through this. And lastly, you have the mesh quality dict. This ensures that your mesh is in a usable range. And in this, we can specify various parameters to control your mesh quality. Okay. So let's move to the case itself. Oh boy. So in the case that we are going to run for the demonstration purpose, it's a coarser mesh. But to show basically what SnappyHex can actually do, I have run already a finer mesh. Let me open it in the terminal. Also, when you're generating a finer mesh, note that it will take a lot of time depending on the number of cells that you specified. Similarly, in Paraview to open the file also, it will take time. So keep that in mind when you're meshing a very fine case. Sometimes it might give you an error saying that Paraview isn't responding or something. Just click on wait to generate eventually. So we'll put a slice. Okay. Now in a conjugate heat case, we need a mesh that can capture everything inside the object itself as well as around it. So for that case, we made this mesh. Now, let me hide it. So as you can see, this is the object as John sir mentioned in his slide. Now, this mesh doesn't look that great. That is because it's like a visualization problem. This can be easily handled. Over here, you have your triangulate slice. If you switch that off, you will get a cleaner mesh. You can put this one on. So SnappyHex will look something like this. As I mentioned, hexahedrals are there. So this is your base cell size, what we specified in block mesh. And these are your refinements based on your refinement level. Based on a refinement level, it will break it down into the desired cell size. I'll show you one more view of your. Now, as I mentioned about adding layers, as you can see, the mesh closer to the edges are more refined as compared to the ones the center. This is good in capturing any curved objects if you have. So any complex geometry that you have is captured well with SnappyHexMesh. So now let's move to the actual case itself. So this is your clean case that you have. You have your zero folder. In Conjugate, you will have two folders, that is your fluid and metal. Then you will have your constant. Within constant, as I mentioned, you have your try surface. This is where you copy and keep your HTL file. In this case, we have our metal HTL. These are all the remaining files that are there. Okay. In your regions property and all, you specify your fluid and air. Then you have your system folder. System folder, you will have three of these folders. You will have the mesh quality dict, SnappyHexMesh dict, and your surface features dict. So first, let's go to the surface features dict. Within this, you specify over here your HTL file. Whatever is your HTL file name, you place it over here. What this does is it will read that HTL file and it will generate an edge mesh. That is done with the include angle. It will read how many features are there based on that, features as in your edge. And based on that, it will refine those edges and will read them properly. Higher the number, you will have lower the number of features that it will capture. Whereas if you have a lower number, it will capture more features. Then over here, you have your non-manifold edges. This is if you have more than two faces connected to each other, you can switch that on. If you have one connected face, you can switch that on and off based on your application. Then we have our actual file, that is your SnappyHex. Now, in your SnappyHex, first you have these three. That is your cache-latent mesh controls, snapping, and add layer. You can switch them on and off based on how complex your geometry is. Now, in this case, we'll keep them true as we need to just generate a simple mesh. Then, first we have our geometry section. Within this geometry section, first you will specify the name of your basically your HTL file. This file is your geometrical entity. Over here, I've mentioned each of the types that are allowed and read by SnappyHex to generate your mesh. So in this, we can see you have HTL. You can import an OBJ file also. Then we have our type try surface. This is just a type of mesh it's going to generate. And you have your user defined name. Now this name is specified by us. In this case, I've specified as metal. If you don't specify it, it will default take it as metal and will put it as region. So it will just rename it according to itself. So you'll have to just check that. But putting a user defined name is essential because further you will be using these names further. And as you saw in the refined mesh, we put in the final mesh that it was very fine. We've put a refinement box. Now what this does is, one second, I'll just switch tabs. Yeah. So what does this refining does is, now suppose suppose we have our object. This is our HTML. This is our HTML file, and this is our domain. Okay. Now, what the refinement box does is that it will specify a normal box around your HTML depending on the coordinate system that you specified. So now we specify this as refinement box 1. And if in case you want to specify a secondary box, you will specify this as refinement box 2. Now, wait, now I will just switch back to my computer. So as mentioned before, you can rename it to anything that you want as long as you remember. So it's simple to just rename it as refinement box. Over here, we specify the upper limit and the lower limit of your box, that is in your minimum and maximum. As I mentioned, in this case, we put two refinement boxes. One is closer to the object itself, whereas the second one is a little bit farther from it. Once we're done with that, you move to the castellated mesh controls. This is where you control your refinement parameters. Now, in the first one, you have your max local cells. This is the maximum number of cells allowed per processor. If your processor exceeds this number, it will switch from balancing to further before further refining it. Balancing is done further over here. So instead of refining it, it will directly switch to this level and it will move forward. The second one we have is your maximum global cells. This is the total number of cells in the entire simulation. The refinement will stop once this limit is reached, and this number is the cells, basically the overall cells without removal. So in the end, if you have a simple geometry in which you are going to be removing most of the cells, this number won't be the actual end cell size of your final file. Then we have the minimum refinement cells. This is your minimum cells required for refinement per iteration. This avoids excessive iterations. Now, if we specify this as a lower number, if the minimum number of cells are 5, and it will take the least number of cells, that is, if there are even 5 cells, it will start to do an iteration over it. So this is time consuming. So if you specify a higher number, it will take a group of cells and it will start refining over them. Then you have your max load unbalance, that is 0.10. This is the amount of load imbalance allowed per refinement. Now, what does max load unbalance do? It is the amount of load imbalance allowing per refinement. It refers to the distribution of computational workload entirely across all processes in parallel. So if we specify this as 0, it means that each of the processor is going to get equal number of cells to process. So what we do is we keep a little bit of threshold so that the processor isn't completely loaded and it will have like a 10% give or take of cells up and down, that way it is. So this is where you specify that. Then you have your n cells between the layers. This is the number of buffer layers that will be between each of those refinement levels. This helps prevent a sharp discontinuity between different refinement layers. Now over here we specified 8. What this does is it will create 8 layers between each of the refinement levels. So it will be like a gradual change from one refinement level to another one and won't be a drastic one. If you lower this number, it will be a drastic one. Depending on how you want it, you can specify that number. Then we move to the features part. This is where, as I mentioned, you have your edge mesh. Now this is generated with your surface features dict that we saw previously. And this one also we specify a refinement level. This now, as I mentioned before, refinement level of 4. So your base cell will be refined 4 times. So you'll have that much fine mesh. Then we have our refinement surfaces. Within this, we have refined our metal. Again, this is the name that we specified. So that's, as I said, if you do not specify a name, you will have to know how to write your name over here. So it's easier to specify just name and then after that use that same name everywhere in your file itself. Now in the refinement surfaces, you have your refinement level. Now this is your minimum and maximum refinement level. Then we have this one. Now within refinement surfaces, you have 2 options, whether you want to do basically whether you want your mesh to be within the domain itself, basically within your object also, or you want it around your object. If you want it inside your object, like in our case, we need it within the object itself. So we specify cell zones and phase zones. The name that we specify is user specified. This will help you identify your cell zone that you've given. And then we have a cell zone. This is where you specify whether you want it inside a geometry, outside a geometry. Now, in case you want to do an external flow and you just need to remove some cells from within the object itself, that can be done with this patch info. Now you specify patch info, and in that you'll specify a type. The default type is wall, and you cannot specify anything else beside wall because SnappyHex will take it as a wall itself. That's how it works. So if in case you want to do an external flow, you can switch this on. In this case, we'll just switch it off. Then once that is done, you have your resolve feature. This one controls the amount of curves that is captured by SnappyHex. The higher the number, it will result in lower features. Whereas if you put a lower number, it will capture more features. That's why we specified a lower number. Then you have refinement regions. This is your region-wise refinement. In this one, we've put metal. Inside this, in refinement regions, you will have three types. That is your mode. In mode, you will have distance, inside, and outside. Now, in distance, it will specify the base level on basically your how to say. Suppose you have, if you have a base, your cell size, you specify that base, and then as you move away from the object, that size will increase. That is how your distance works. Whereas in inside, you will specify a refinement level within the object itself, and it will basically refine the mesh within itself. Outside, it will do the exact same thing, but in the opposite direction. So in this case, we put a metal. Each of the refinement boxes, we've specified it to mesh within itself. So it will refine each of those boxes from inside. Then, as I mentioned before, location in mesh. This is the point where you will specify in your domain. This will determine whether you want an internal mesh or an external mesh. So this point is quite important when you're specifying what kind of meshing you want to do. Then you have your allow freestanding zones. In this case, we put it as false. This one will handle your zones that aren't bound by the geometry. What this means is that suppose if I put it as true, it will keep these freestanding zones. That is useful when defining. So basically, if you want any isolated faces or any zones that are isolated from the object itself, if you specify it as true, that is what that does. If you specify it as 4, if there are any freestanding zones that are not connected to the body itself, it will start to delete them or it will try to snap it. So this may cause sometimes an error, but most of the times, if you have a simpler geometry, if you don't have any freestanding zones, it's easy to put it as false. Then you have your snap controls. This is where it will basically check your snapping and how does the snapping process go about. So in the first one, you have your n smooth patch. In this, we put 3. This will specify the number of patch smoothing iterations. Then we have a tolerance. Now, if your tolerance is less than 1, it is good for a finer mesh since it will try to take the closest cell and it will snap it onto the object itself. Whereas if you have a moderate mesh, 2 is fine. Anything above 2 is good for a coarse mesh because it will take any cells close to or any cells that are a little bit farther from the object and will snap it. So if your mesh is quite coarse, it's good to have a higher number of tolerance. Then we have the solver and n solve iterations. This is the number of iterations that it will do to achieve or snap each of those cells onto your object itself. Higher this number, higher will be the mesh quality. You will have a better quality mesh, but it will take also a lot of time. So keep that in mind when you increase this number. Similar for the n relaxation factor iteration. This will also have a relaxation factor. Then you have your n feature snap iteration. And this will specify how many iterations it needs to snap the features, that is any edge or any sharp angles that you have to the object itself. Similar with this also, higher the number, more amount of time it will take, but you'll have a better quality mesh. Then we have the implicit feature snap. Now, in this case, we have it set to false. Now, this determines whether you want to automatically have your object itself detected by SnappyHexMesh, or you want to detect it by using that surface features extracting. So in case you want to automatically detect your object within the domain and mesh it, you can set it as true. Whereas if you set it as false, the explicit feature snap has to be set to true, because it will start to search for an edge. If in case you have any sharp angles or you have a curve or something, this one will read the file that is generated, basically your edge mesh file that is generated by a surface features, and it will, even though it cannot find a proper edge, we specified an edge mesh, it will directly snap all of the cells closer to that edge itself, since it's already read by surface features dict. So it will say that there is an edge over here and it needs to be snapped. So that way you will have a more refined mesh closer to the edges. And then we have our multi-region surface snap. This determines where you're snapping on multiple regions. This is essential when you have multi-phase regions. If you set it to true, it will mesh individually each region. Whereas if you have a simpler geometry like our case, it's set to false because we do not have that many regions that need to be meshed simultaneously. Then once you're done with the meshing part of basically the cells and everything, you add a layer. So in your add layers control, it will add whether you want to add a layer around your object itself. So you have your relative sizes. This again set to false. This one will determine the layer size relative to the cell size. So this one is it will determine the layer size relative to your cell size. Then we have our layers. This one will specify the layer addition to a particular patch. Now in this case, we have again used our metal. Around that, we specified to put 2 layers of meshing, basically 2 cell layers around the object of interest. The expansion ratio is similar to grading. It will determine how much growth you want from the layers as you move away from the object. Then you have your final layer thickness. This one, it sets your final layer thickness as a fraction of the cell. Now, suppose you set a target thickness of the final layer as a fraction of cell. Suppose you put this as 0.9. For example, if you have a local, basically your base cell size is of 1 mm, the final layer thickness will be of 0.9 mm thickness. Then basically you can either use the final layer thickness or you can use the first layer thickness. So the first layer thickness is in which we manually set the thickness of the first layer itself, depending on your base level. If this is within that range, like if it is smaller than your base level, then it will achieve. If it is above that level, then it will not generate any refinement layer around your object. Then you have your minimum thickness. This will again determine the thickness needed around your object, which will generate your layers. Then you have your n grow. In n grow, we specified it as 0. Now, n grow will mark your neighboring cells, any cells that are around your object, for a potential layer addition. Now, in this case, we set it as 0. Suppose we specify it as 2. What this does is it will take 2 layers, basically 2 cell distance above your object, and it will potentially keep that in mind that there are these 2 cells. In case we need to mesh around the object itself and add a layer, it will take those 2 cells. So it will potentially add a layer around your object. So this is where you can specify how much you want. Then we have our feature angle. Again, like previously, this specifies the angle, basically the edge. Lower the number, it will capture more of the features. Higher the number, it will capture less. Then your split feature angle. This one will control your growth over edges. split feature. Yeah. Then these are all your relaxation factor. Okay. These are the number of snapping iterations and your relaxation factors that will be in play when you do your snapping, your smoothing, normals, everything. Okay. Then we have this one is important, max phase thickness. So your max phase thickness, it will be, this is what stops your layer growth on highly warped cells. And you have this max thickness to medial ratio. This one will smooth the growth with ratio thickness to medial. What this means is that it will ensure a smooth transition between layered and unlayered regions to maintain a mesh quality and avoid distortion. Now, if this number is high, it is crucial for boundary layers where you need, like for an external flow, you need the layer closer to the body to be well refined. So if you have something like that, you can specify a higher number. Whereas if you have a smaller number, it is good in narrow regions since it will not refine it that much, but it is moderately okay for most of the case. The default range of this is between 0.3 to 0.5. So basically you can use it at the default region, the default range as well. And then you have your minimal axial angle that is a 90. This controls your layer addition where mesh aligns with the edge. Yeah. And max, okay. This one, your N buffer cells no extrude. This one will create a buffer region for any new layer terminations. This and then finally you have your N layer iteration. This is your overall iterations for layer addition. Again, this one higher the number, good, better quality mesh, but you will have more time. It will take more time to mesh the whole thing. Then we go to the mesh quality controls. This is where we include our mesh quality dict. This is the dict that is in your system folder. I'll show it in a second. In this one, we can specify the number of iterations that is there to smooth and to generate a good quality mesh. And then we have the error reduction. Now this amount is basically for displacing all the error points. Now suppose you have an error of 1 mm and we specify this as 0.75. It will move a mesh 0 to a distance of 0.75 mm per iteration. So it will basically refine it slowly based on your iteration numbers to the desired number. So it won't be a drastic change. Then we have our write flags. This one will control what is written during your meshing process within your terminal. So in this case, we wanted to write the scalar levels, the layer sets and the layer fields. Basically, it'll give you an output on your terminal itself. And then we have the merge tolerance. This is the fraction of overall bounding box of the initial mesh. So this is the mesh quality dict. This is where you specify the basic parameters that you need for a good quality mesh. This can be changed according to how you want to use your actual object itself. So as I mentioned before, first you have your block mesh. This will generate your base mesh. So in this one, we specified a simple box, a cube, since we have a three-dimensional body. This is a simple cube. We specified the vertices, the blocks, and this we've given the cell size. The edge grading, there's no edge. And then we put our boundary conditions. Now in this, we have the left-hand side, that is your fluid inlet, right-hand side fluid outlet, and anything around it is the walls. So once you do this, we move to the SnappyHex. Within this, we specify each of those parameters. So the main parameters that you can change is the metal. First, you specify your HTL file. Then you specify your refinement box. If you want to add a refinement box, you can. If you don't want to, it's basically depends on your application. Then we have a cache-related controls. Over here, you specify the local number of cells you want, and then you specify the global cells. Note that higher the number, more time it will take. So keep that in mind. You can specify your refinements and everything over here. Then you specify your features. Now, since we've put over here in the lower end, we have clicked on true for explicit feature snaps. So if this is true, make sure that your emesh file, that is your basically your edge mesh, is there in your features file, since it will be reading this one to generate a good quality mesh around your edges. So that this is important if you're using the extrude external one. Then refinement features. In this, you can basically, if you have an internal or external mesh that you specify over here, your resolve and everything, and you have your regions where you specify this. So now once these factors are done, there are two ways to do meshing. One is in your series configuration, and other one is in your parallel configuration. So these are the set of commands that you will be running for if you're running it in serial. If your geometry is simpler and your mesh size isn't that large, you can use it in a serial format. Whereas if you have a finer mesh, it will take time to run it. So I'll show you how to run it in a parallel configuration. So first you go to the file, then you open the terminal. Yeah. First you run the block mesh command to generate your base mesh. So once this is done, I'll show you how the block looks. Paraform. So this is a block that we have. Note that there's nothing inside it for now, since we've only generated a simple block mesh, a block using block mesh. Now, once that is done, you run the command surface features. Now, note that surface features, if you're running OpenFOAM 9, this is the command. Whereas if you're running a higher, basically if you're running the .com version, you will have surface feature extract. This is the option for OpenFOAM if you're using 2212, 2212, 2312, any of the higher variants. Now, in this case, we're using OpenFOAM 9, so we will have surface features. As you can see, it has read the file, basically a HTML file, and it has generated a emesh file. Previously, there was only a metal HTML. Now there is an emesh file, that is your edge mesh. Along with that, it has also generated this file, that is your extend features edge mesh. This one. Once you've done this, now to run it in parallel, we need to decompose your block mesh. So we'll decompose the whole domain. Now this one is set to 4. Once you've done that, you will run SnappyHex in parallel. Now again, depending on your cell size, you will have this process will take time. So keep that in mind. Now, since we are going with the coarser mesh, it should run faster. Just wait for some time. Okay. To faster make the process faster, we'll change some parameters within our SnappyHex. Okay. So we lower these local and cell sizes. So again, we run block mesh. Once we've done that, we will run surface features to extract the edges and then decompose. And then we'll run SnappyHex in parallel. So by the time this process is running, we will check if there are any questions in the chat box. Is there any other method than location to retain the mesh? Like in multi-region foam, it is tedious to find all points. Okay, so you're trying to ask how are we specifying the mesh within the domain itself and the object also. Okay, so that is done over here. In your metal, we specify the cell zone and we specify a phase zone and we specify this inside. So what this does is it will generate a mesh within your object itself. If in case you do not write this, it will just generate a mesh around it. It will remove all the cells from inside the object and it will term it as a wall. That is how you do. Then hope that answered your query. Then did you use 4 processor for parallel meshing? Yes, in this system, currently I'm using 4 processors for running the simulation. How SnappyHex is compared to CFMesh. I'm not sure exactly what is CFMesh. I'll have to look into that. And do we have any limitations on the mesh count? The mesh count as in, are you trying to ask whether you have a limitation on this, on the cells? So there's no limitation as such, but if you specify a higher number, obviously it will take a lot of time to mesh your actual geometry. So you have to keep that in mind, because if you go with a very fine mesh, your computer should be able to handle it and you should have the time. So usually a moderate number should do the job. And then somebody, I think, okay, these are all previous questions. Okay. Let's check the mesh. Okay, this is still meshing. Okay, one more question is there. How can we perform computation on HPC? How can we connect to HPC?
For HPC, you need to set it up like that. Okay, because there will be multiple nodes which will be communicating with each other. Again, the communication can be through that.
Okay.
Either it will be MPI, you will need to submit your runs using
In Islam.
so the communication can be using Slurm or what was the other option? But so for that, see, you need to have means OpenFOAM has to be installed in a certain way. Generally on the main node, you will install OpenFOAM in the shared folder so that all the subfolders have access to it. Then you will also need to write a script, like how you do in ANSYS, so that that communicates. You need to basically submit what is called like a job on the HPC. So there will be one job scheduler. Job scheduler will take that job and then distribute it to the number of nodes. So there are steps to do that, and I think some not exactly tutorials. You can read it in forums on how to install that. We have done something like that and we are working on it. So right now we have a system in which we run what you can say job on a cluster with 5 nodes. We are planning to increase it to 20, but that is not something that what you can say we can demonstrate now in the interest of time, and also it is what you can say it's very specific topic. Everybody will not need that. So this we are basically interested. This is only for people who are in the intermediate level. We want to bring them up to a level where they understand what is happening. But HPC again, it is specific. So generally for institutes, say like in IITs, NITs, wherever the HPC facility is there, you need to install what you can say OpenFOAM in that way. You can contact your system admin for that.
Okay. So the meshing process is done. So now since we've run it in parallel, you need to reconstruct the mesh. So for that, you have the command reconstruct par mesh, and you will only do the latest time. And we want to specify to generate the mesh within the constant folder. So we have constant. Now I'll show you the mesh. Now, since we've gone with a coarser mesh, we'll slice this. There is some visualization problem. We'll just delete this one again. Slice. Okay. So I'll show you the case that is already run. This one is having some visualization problem. One time. So now since we've gone with a coarser mesh, it did not add a refinement layer. Now that is a reason wait, I'll show you. You're supposed to specify in your add layers, your thickness and all of these parameters have to match your base level. Now, if your base level mesh is small enough and your refinement layer you're trying to add is greater than that, it won't add any layers. So make sure when you're adding layers and all that it is well below that value to generate any layer. In the fine case that I showed you previously, in that one, the refinement level of the base, basically the add layers, the layer around the edges of that object was smaller than the base level. That's why it was able to generate a clean surface, clean layer around the object of interest. So, yeah. So go back to the template. Now, once you've meshed and everything, since we have a conjugate heat transfer, you need to split that mesh into a proper fluid and into a proper solid. So to split that mesh, you have the split mesh regions into cell zones. And over here, we are specifying default region name as fluid. Why we are doing this is because if we do not specify it, it will just add a name as region 0 or something. So it's better to just add a region name. In this case, we've added fluid. And now, as you can see, in this case, there is no polymesh. Once it begins to do the splitting mesh, it will basically break down the mesh into a proper fluid and a proper solid, and it will add those polymesh files into each of those file structures. So you'll see it in a few minutes. Okay. Until the splitting mesh is done, now Johnson will explain the conjugate heat transfer case structure.
Thank you, Evan. So, as you might have seen, SnappyHexMesh is basically a lot of parameters. So it's very confusing. So my suggestion will be that always, keep the default parameters, run with it, okay, and slowly tune the parameters one by one so that you gain more understanding on this. And unless you, what you can say, get your hands dirty, try different things, you will not learn. Okay. So the best way to learn OpenFOAM is to practice. Okay. So that is my suggestion. So look at this recording whenever you get it, look at the various controls, try changing them one by one. Don't do many things together. You make one change, you see how it reflects on the mesh, and same way. So this way you will learn much more. So hands-on learning is what is needed in this case. And if you would have attended the session yesterday, you might have seen that using this SnappyHexMesh, obviously for demonstration, we took a very simple case, but using this SnappyHexMesh, you can also mesh complex geometries. Like Mr. Nikhil, he demonstrated meshing of a lion, right, with so many details. The SnappyHexMesh was able to capture all those details. But again, it takes time, and then you need to fine tune the parameters to do that. So you can try something like that. So I will explain to you what is the case structure. So hmm, Okay, so you see what is the general case structure. Let me go into the slideshow mode so it is much more clearer. Yeah. So what is the general case structure? So if you have, we hope that people who have come here at least have a basic knowledge of OpenFOAM. You have done at least the basic tutorials. So you will know that in OpenFOAM, there are basically three main folders: zero, constant, and system. And inside zero folder, you will have the boundary conditions for the various fields like pressure, velocity, temperature, and so on. Okay. And in the constant folder, as the name suggests, you will specify the fluid properties. If you have any FV models or options, that will be added there, and also the mesh will be located in the constant folder. So these are generally things that are constant, as the name suggests. Then in the system, you will have, if you are doing meshing, you will have the block mesh dict, then you will have the control dict, and some other files that are needed. Like say, in this case, we wanted to run the simulation in parallel. So you need to have the decomposed par dict. So running the simulation in parallel is necessary if your simulation is time consuming. Basically, if the cell count is high, you cannot run it on one core, because basically your simple simulation, they will run on one core, and all the systems nowadays will have at least four cores to six cores. So you can utilize the full capability of your system by using this decomposed par dict. Okay. I will see. I'll try to show that once, depending upon how much time I have. Then you have your FV schemes and FV solution. Okay, as the name suggests, FV schemes will have all the discretization schemes, for your various terms, and FV solution will have the solution algorithm that you're using. So basically, in CFD, what happens is your what you can say governing equation is discretized, right? So whatever are the discretization schemes that you use for them, like upwinding scheme for time, it will be maybe Euler scheme, backward scheme, Crank-Nicholson. All those things are specified in the FV schemes file. The FV solution specifies how you are going to solve the final system of equations that are generated. Okay, so the basic understanding of CFD is that once you discretize the domain, you create a system of equations, and they need to be solved by certain algorithms, and that are controlled by the FV solutions. Then your control dict controls your what you can say how you are going to run the simulation. What will be the start time, end time, time step, and if you need some other functionalities, that can be added as functions in your control dict. Now, as if you look at this folder structure, it is a little bit more complex, because in CHT what happens is you have multiple regions. So you have one region named fluid and the other region named metal. So we have kind of we could have renamed it as solid also. So it depends upon you, right? You can have a fluid, solid. If you have multiple solids, that is also possible. That is another case that I will demonstrate to you. That is another case that I will demonstrate to you. Okay. Now, so what happens is in CHT case, in each of the folders, in each of zero, constant, and system folder, you will have two folders. Basically, in our case, you will have two folders, and depending upon the number of regions, you will have those many number of folders. So in zero, there will be two folders. Like in our case, we have one region that is fluid. So you'll have a folder for fluid. Then you have another region called metal. So you'll have a folder for metal. So in the fluid, you'll have boundary conditions for the fields that are inside the fluid region. So for fluid, we will solve the pressure, temperature, and the velocity. So there will be boundary condition files for them. Now, metal region, there is no flow, right? And so pressure also, there's no meaning of that. So you will have only one file, that is a T file. So you'll find, so you'll have only boundary conditions for T. Similarly, when you're specifying constant, in that you need to specify what will be the what you can say your thermophysical properties, your momentum transport, that is your turbulence properties. All those things again are specified for fluid in the fluid folder, and for the metal in the metal folder. So properties for the metal are added in the metal folder. Properties for fluid are added in the fluid folder. Now this tri-surface is only specific to SnappyHexMesh. If you did not have SnappyHexMesh, this tri-surface would not be there. Okay. Similarly, in your system folder, you need to have specific FV schemes, FV solution, and if you are going to decompose the domain, or decompose par dict in both your fluid domain as well as in your metal domain. So inside this, what we say is the discretization schemes for the fluid are written in the fluid file. The discretization schemes for the metal are written for the metal file separately. So this is the basic structure of your CHT multi-region case. So let us go over the boundary conditions that are there for this specific case. Okay, so this is my template case. I'm just opening. So inside 0, as you see, there's fluid and metal. So in fluid, we have P, PRGH, T, and U. Okay. So why P and PRGH? So basically, whenever you have what you can say the effect of buoyancy or gravity, right, in flows, then the pressure due to buoyancy will be different, right? If you move along, like if there is elevation, if there is multi-phase flow due to density, the total pressure, what you can say, pressure will be different. The hydrostatic pressure will be different. If you remove that hydrostatic pressure, then you will have kind of like a one single pressure system for the domain. So for ease of solving, generally from the complete pressure, the total pressure, the rho GH term, right, that is the hydrostatic component is subtracted, and you have the PRGH pressure. So generally for multi-phase cases and for heat transfer solvers that have the buoyancy, or you can say that take into account the buoyancy effects, PRGH pressure is solved. Okay, so if you look at that, we will have boundary conditions in the PRGH file, right? But if you look at the P file, everything will be calculated. So pressure is calculated from PRGH. How is pressure calculated from PRGH? So once PRGH field is solved, you will have all the PRGH pressures. From that, you can calculate P by just adding the rho GH term over there. Okay, so that's why for P, we will keep the boundary conditions for all the phases as calculated, right? And in PRGH, we will be specifying the pressure. So as we've already discussed, there is an inlet, outlet, and then there is walls. So for every other wall and inlet, we have given a fixed flux pressure. Okay. Now this will adjust the what I can say pressure gradient for the body force as well. So this specific type of boundary condition does that. It is similar to zero gradient, but it will slightly tweak the what I can say gradient to adjust for the body force terms. Then for the outlet, we are giving a fixed value of 0. Okay, so that is what this outlet is there for the boundary condition. So we have our P and PRGH files are done. Close this SnappyHexMesh. Now T is your temperature file. So for temperature file, at the inlet, we are giving a fixed temperature of 300. So internal field is where we initialize. So it is like the initialization. So initial temperature is 300. For the fluid, I am saying keep the same temperature, that is 300. So it is the dollar sign means we are referring to the variable. The variable name is internal field name. So whatever was the value over here, take the same value over here. Okay, that is what it basically means. So fluid inlet will also have an inlet value of 300. Now for the outlet, we are giving a boundary condition called inlet outlet. Now this is again derived boundary conditions. They allow for reverse flow. So inlet outlet basically allows for reverse flow from the domain, right? Then this fluid metal is the patch that gets created when you have just a moment. Yeah, there's some disturbance. Fluid to metal is a patch that gets created at the interface. So if you let me open my slide. Yeah. So if you see this interface that is there, right, between the fluid and the solid, that also we need to specify the boundary condition. So that is what we are doing over here. So this is the boundary condition of temperature. So basically what boundary condition we are using? We are using the compressible turbulent temperature coupled baffled mix. The name is very complex, but it is a simple thing. So what it is doing is it is maintaining the continuity of the temperature and the fluxes at the interface, because there should be temperature continuity. There cannot be discontinuity over there, right? Whenever the metal is getting heated, the same heat is going into the fluid. So the heat flux has to be continuous, the temperature has to be continuous. Like whenever you solve any heat transfer problems, right? At the interface between a solid and the convection, say like if you have a conduction and convection, then you will write minus k dt by dx is equal to h into delta t, that sort of a boundary condition. So what you're doing is you're maintaining continuity of the flux. So that is maintained as well as the temperature is maintained over here. And at the remaining walls, okay, we are giving zero gradient. These are the walls. This is the top, bottom, and front and back walls. Remember, this is not the walls of the geometry which is heated. The walls of the geometry that is heated has the name fluid to metal. So for that, so wherever you need coupling between the solid and the fluid, you use this type of a boundary condition. So this is similar to the coupled boundary condition of fluid, if I may say that. So T is done. Yeah. So P, RJS, T, and U are done. So this is for the boundary condition for the fluid. Similarly, for the metal, if you see, there is only T file, and in that case, metal will have only one interface. And so you see, in the fluid, the name was fluid to metal. In the metal, the name is metal to fluid. So it is like a shadow. What you can say? Shadow patch that is created, right? So here also you need to specify the same boundary condition. Only difference is here the kappa method or the thermal conductivity will be calculated from the solid thermo, and there it would be calculated from the fluid thermo because that is on the fluid side. So this shows for how you get the thermal conductivity. So these are the boundary conditions, right? Let me go to. So I have looked at the zero folder. Now important, let's look at the constant folder. So extrude mesh features, polymesh, tri-surface, all these things get generated during your meshing, right? What is important is this region properties file. So in region properties, you are kind of specifying what are the regions. So generally in CHT, there will be only one fluid region and one solid region. I shouldn't say one, but it is categorized into fluid and solid region. Now fluid region, so we have only one fluid region and it is named fluid, right? So Evan just demonstrated that when you do the split mesh regions, you have given the name fluid. If you don't give the name fluid, then by default it will take something like region 0 or something, right? And then you have to go and change everywhere. So it's better that you overwrite it with fluid and write the name fluid over here. Okay, then for solid, I have only one region and its name is metal. So I'm adding metal over here. Apart from that, suppose if I have another solid zone or if I have another solid zone, I just give a space and write whatever the other name is. Okay, that also will demonstrate to you. So this is the way you are defining the different zones. So you have two regions and you're saying one is fluid and one is solid. So it will solve the equations for solid for in the metal region. It will solve the equations for fluid in the fluid region. This is the file that determines that. So this is one important file. Then in the constant, I will have a constant folder for fluid and constant fluid folder for solid. So here important is the gravity. So whenever if you want to take into account buoyancy effects, then gravity must always be on. Okay, and then you need to look at the sign depending upon how you have oriented your geometry. So in our case, the gravity is in the downward y direction. So we have given minus 9.81. That is the gravitational acceleration in the y direction, in the negative y direction. Then momentum transport, here you need to specify your turbulence parameters. Okay, so here we have kept the simulation type to laminar. So we are only doing a laminar simulation. If we want to what you can say add turbulence, then we will switch this to RAS, and then RAS is then we will use all the what you can say any turbulence turbulence parameter that comes under the RAS family, so that you can use like K omega or K epsilon or so on, right? Or maybe Spellet-Elmeras, all those things you can use, and then you can specify them and their coefficients in between. So right now we have kept the simulation type to laminar. Then we have the reference pressure. So we need to specify some reference pressure. We have added a reference pressure of 1E5. And then thermophysical properties. Now this is something that is important, right? So here in thermophysical properties, we specify what are the properties that are available, or what rather than available, what are the properties of the fluid that should be used and how those properties are being calculated. So first the thermotype, right? So here HE rho thermo, what does this mean? HE rho thermo, it means that calculate what you can say this thermo either based on like you're either calculating the energy based on the enthalpy or the internal energy, and you are calculating the properties based on density rho. Okay, so that's what it means. So there are also other types like HE psi thermo. Okay, now if you see, I'm saying all these things, but if you need more details on this, right, it is always best to look at the documentation. So you go, I'm showing you how to search also. So thermophysical models. So you type thermophysical models, OpenFOAM, right? And in the user guide, maybe V12 user guide. Let me go for V12 user guide. It is almost same. So if you see, they have mentioned what each of it means, right? Hmm. So here, see here, they have used HE psi thermo. That means the what you can say, the relation between temperature, pressure, and the properties, right? They are calculated based on the compressibility rather than, in our case, we have used rho thermo. So it is calculated based on the density, right? So there are multiple things over here. You can use rho thermo, fluid thermo, psi thermo, right? And then the thermo, here we are using E constant. Okay, you can because we are, this is the, I think this is the fluid. So we are solving for the internal energy. So we are using E constant for the thermo. Yeah. So you can have either H constant, right? That means Cp and HF values are constant, right? Then what you can have is equation of state. So we are saying that my density is constant because here I am not accounting for the effects of buoyancy. If I have to account for the effect of buoyancy, I cannot give a constant density. If I have already imposed constant density, then how the density will vary, right? So equation of state can either be like ideal gas, perfect gas. So here, these are with the various equations of states that are available. So generally, what you can say, something that is widely used is either Boussinesq or your ideal gas, right? So in Boussinesq approximation, what you do is basically the effect of the buoyancy change is only added for the what you can say, the buoyancy term over there, and everywhere else in the complete region, the density is considered to be constant. So this kind of saves computational effort, and this is valid if your beta delta t value is far less than 1, right? Generally, maybe like 1-2%. Such guidelines will be there. So you keep 1-2% is what I'm saying. So it will be like your beta delta t value should be 0.02 or maximum 0.03. Okay. Then you can go for Boussinesq approximation. So what this does is it changes the density based on the temperature, but only for the buoyancy term. And for rest of the terms, it keeps it keeps it constant, right? Then you can have in perfect gas and all those things, right? Perfect fluid, perfect gas. So perfect gas is like an ideal gas. So generally, either you use ideal gas or what you can say, Boussinesq approximation. If you have fluid, then you use perfect fluid. You can give tabulated values also of density as a function of temperature and pressure if needed, right? So there are multiple things for you to explore depending upon your application. So for the time being, we have used a constant density. So we are keeping rho constant over here, right? Then species, if you have multiple composition, then you need to specify the species. Now at present, only one model is available in species and its name is also species. So what we do is inside the species, we specify the number of moles and the molecular weight of each component. Okay. So that is something that you need to do. So in this case, because we have only one species, only one will be there. If you have more than one, like if it is a mixture, then you will have multiple. Okay. Then under equation of state, we have given a constant density, right? Rho constant. So we are just having one rho value, and that is a constant value. If you would have used Boussinesq, then you would need to specify, where is that? You need to specify a reference density and the beta value. So those things will be included in the equation of state. Then for thermodynamics, that is we have used, I think, E constant. So we are specifying the what I can say, CV value, that is specific heat at constant volume, and we are specifying the heat of fusion. So if we want to account for phase change or something, then HF value is added over there. Okay. Then the next thing is the transport properties, right? So for transport model, we have given a constant transport model. That means all my properties, transport properties. What are the transport properties? Generally, in any simulation, you have in CST simulations, you have major two transport properties. One is your viscosity, that is nu, right? And the other is your thermal diffusivity, that is alpha. So these two properties have to be specified. But if you see, you have specified over here mu and Prandtl number. So how is your nu and your alpha calculated? So because your Prandtl number is nu by alpha and nu is mu by rho. So all these things are kind of linked. So from this mu and Prandtl number and your rho, you can calculate your what you can say nu value as well as your alpha value, that is the thermal diffusivity. So these two are critical in calculating your transport or your uh, diffusion values. So this is how it is specified. So right now we have used the constant model, but if you see over here, there are a lot of other models that are available, right? As I told you here. Okay, here is another example. Yeah, if your properties are changing, so they have given you some examples. If properties are changing, how do you incorporate that, right? If there are mixtures, where was that? Yeah, so this for transport model, I have used the constant transport model, but you can say that your properties like viscosity, it is changing with temperature, right? Either it changes by this way, or it is changes by a polynomial relation, okay? Or you give a tabulated value, right? So all these things are possible. You can explore them, right? Then energy formulation, I'm using the sensible internal energy, okay? So I'm using sensible internal energy for my calculation. Just remember this. This is for the fluid side. I close this, go out. For my metal, I have two important things. One is first, let us go to the thermophysical properties. So here everything else remains same, but if you see, instead of He, I have He solid thermo. So this model is will be used to compute the properties, right? Now again I have pure mixture, then constant transport, and all these things. Again, I think I have gone over it. Hmm. So here I am saying what is my molecular weight, right? Then what is the transport property? Kappa means your thermal conductivity. So here you have the unit watt per meter Kelvin. So yeah, your HF, if there is phase change, then your CV value and your density. So all these properties are needed for calculation that you specify over here. Now, something that really struck me yesterday, I don't know if some people attended yesterday's session, was that Mr. Nikhil pointed out something really nice, is that in whenever you're doing OpenFOAM, you need to know these values, right? You're manually entering those values. So you get a feel for those numbers. As engineers, we should have a feel for the numbers, whatever we are putting into, right? Whether it is the size dimension, the heat capacity values, the density values, right? And what happens generally in Fluent is you just click and then, okay, somebody asks you, okay, what is the thermal conductivity of SS? You will be, okay, I don't know. So this is actually one good point of OpenFOAM, is that when you are manually entering the values, you get a feel for it. Obviously, some people will just randomly do it, but as good engineers, I suggest that you get a feel for those numbers. So what is happening? What value am I putting? So this is something that came to my mind. So I thought I will say that. The other thing is FV models. So right now, if you see the our problem at hand was, yeah. So my problem at hand was that the core is having a what you can say core loss of 100 watts. That means whenever the transformer is working, due to the eddy current, some heat is getting generated, and that quantity is around 100 watts. Okay. Yeah. So this 100 watts of heat in the simulation, we need to add into the domain. So how do we add that? So, okay. So to add that, we are incorporating a FV models. So this FV models is a utility that OpenFOAM provides to add what you can say some source terms for us. So in the we have named our heat source as metal heat source, and we have a type of FV model like heat source that is available. So what it does is we have said selection mode all. That means in all the cells of what this FE model file is available in the metal. So it will take all the cells within metal and add a what you can say uh, heat transfer rate of 100 watts in it, right? So if I write over here capital Q and 100, it will take the absolute value. So within the complete cells, I need to add absolute value of 100. Okay. Then the other option is I can give what you can say volumetric rate. So that means if I know the volumetric rate rather than the absolute value, then I can specify that. So it depends upon what input value you have. By the value per unit volume, like sometimes you will have volumetric heat generation rate, right? So if that is the input that is given to you, that means the heat generated per unit volume. Then you can replace this capital Q by small q, and that is nothing but the heat that is generated divided by the volume of the domain. So these two types of entries are allowed over here. Okay. Let me close this. Okay. So where was I? So we have looked at the FE models. We have looked at thermophysical properties for the metal. Okay. So now I think we have looked at all the files for the constant directory. Now let me go out and let me look at the system directory. Right. Inside system, then what we have is we have the block mesh dict. Okay. I think this Evan explained to you briefly. Block mesh dict. What he did not explain is the decomposed par dict. I will go over that. I think, but then the decomposed par dict. Yeah, this is okay. This is one, and inside fluid. So generally for CHT case, you need to have a what you can say your decomposed par dict inside your fluid as well as inside your solid domain. Okay, but as a placeholder, you also need to have it outside in the system folder. So if you see, there is also a decomposed par dict, FV schemes, and FV solution. Though these schemes and solutions are only there, but the schemes and solutions means they are part of the file structure. They are needed over there, but whatever decomposition, whatever schemes and solutions we are giving, they will be read from the separate files. Like for the fluid, it will be read from the fluid section. For the solid, or it will be read from the solid section. Okay. Now let me just open one decomposed par dict. So in decomposed par dict, you have here you specify the number of subdomains. So basically, this is the number of processors that you have, right? So how do you decide this, right? For beginners, you don't know how many subdomains you have, right? So what you generally do is you open your terminal, right? And if you are on Linux, if you're on Linux, type ls cpu, right? When you do ls cpu, it will give you all the details of your CPU, right? So if I zoom, if I go up, so it is telling me that I have 2 threads per core and I have 12 cores and 1 socket. What is this socket? So in some motherboards, there may be 2 sockets, and on those 2 sockets, there are 2 processors. So if there are 2 sockets, that means there may be 2 processors on your thing, and then you kind of need to multiply these, right, to get the number of what you can say cores. So here I am saying I have 12 cores per socket and I have 2 threads per core, right? So and I have only 1 socket. So if I multiply these 3 numbers, how many CPUs I will have? So I will have 24 CPUs, and that is what is written over here. Okay. So I in my simulation can specify a value up to 24. So that is the general idea over here. So I can go up to 24. But remember, just randomly increasing the number of subdomains will not help you. Okay. So you need to have a balance between because what happens is if you are increasing the number of subdomains, right, every subdomain will need to communicate with each other, right, later on. Okay. So and if in each subdomain there are only few cells, then that kind of takes over from the advantage of having multiple cores. So you need to balance. So by that what I mean is that the gain in what you can say speed or the reduction in computational cost is not linear with the increase in the number of subdomains. So you maybe you need to try that for your separate case, right? So here I am having 4 subdomains, and the method that I'm using is hierarchical. Okay, that means in my X, Y, and Z direction, how I need to break the blocks. So I need to break it in 2 in my X direction, 2 in my Y direction, and 1 along the Z direction, right? So that is something that you can try. Instead of hierarchical, you can also maybe write simple. Then there is Scotch. In Scotch, it takes it by itself. You don't need to specify any of these components. So if you want to know what are the various other models that are available in any of these cases, what you generally do is, suppose I want to know what are the methods that are available inside this, right? Other than hierarchical. So I can just replace this hierarchical by maybe say a word like banana, right? And then I comment this out. Now, if I run this, OpenFOAM will throw an error, right? And it will say that the keyword banana is, okay, let me just show you that. This one, right? Decompose part. Hmm? Oh, it is already there. Okay. Hmm. Maybe I'm not in the correct location. Where am I running this? Yeah. Sorry for that. We have too many cases. Yeah. So if you see it, the case is already decomposed. So if I want to demonstrate that, first I will need to delete this. So one is if I can delete it this way, or I could have deleted it from the terminal. Let me open this in the terminal now. So I am in the correct location. Yeah, I am in the correct location. Now I am sourcing my OpenFOAM OF9. So because I'm running on OF9 version, basically in FOSSEE we run on multiple versions. So we need to source the version that we are using. So I will have all the commands that are in OpenFOAM now at my disposal. So let me decompose the case, right? Sorry, I think I'm making the change in the wrong. I made change in the wrong. No, but then I did not make a change in the outside folder. I made it in the outside folder. Okay, okay. So I made change only in one file. Yeah, so I made change over here. Or maybe I did not save it. That was the problem. Okay, so now you understood where we make mistakes. I had not saved that file. So I need to decompose, and then because my mesh is split, so I need to use decompose for dash all regions. Okay. So you see, it threw an error, right? So it is saying decomposition method banana is not valid, and the valid ones are hierarchical, manual, matrix, multi-level, none, squash, simple, structured, right? So many are there. So you can search, each one of them, read about them, which one works in which scenario. So these are the things that you can try. Okay. So yeah, so somebody is asking, is it wise to use hyper-threading in CFD physical core is working? Yes, yes, you pointed out rightly. You pointed that out. Uh, I think I forgot to mention that for some reason. So Ajay is, what Ajay is saying is really valid. So what happens? Maybe let me do LSCPU again. So what happens is, in processors like this AMD, also the new Intel processors, hyper-threading functionality is there. That means in every core, right, here you have two threads. So one CPU core handles two threads. So it is switching between them, right, and then doing the work. So if you want to improve the speed of your what you can say simulation, I think you should disable hyper-threading. Okay, because it is only one core that is handling the two processes, so it will not speed it up. So your hyper-threading should be disabled, and you should use only the number of cores that are there, the number of physical cores that are there. These two are not physical cores; then they are like kind of like virtual cores. So use only the physical core number. Yeah, thanks. Thanks for pointing that out. I kind of forgot to talk about that. Yeah, so limit to 12 cores. Okay. Yeah. What I was saying. So I had done changes to that. Okay, so I was saying if you need to find what are the other options that are available in place, then you can use the keyword. I'm just saying banana that because that is what the CFD community in general says, but you can write anything. If you want, you can write monkey also. It's fine. So yeah, so in fluid, I had made that change. So I will go ahead and remove that. Okay. So I have looked at the decomposed part. Yes. Yes. So fluid metal. I said that we need to add the heat source. That was done. Now we are in system. Okay. In system in fluid. Let me look at FV schemes. So again, the time discretization is done using the Euler scheme. Right. Then there are gradient schemes, divergence schemes, Laplacian schemes, all these things are there for you to choose. Now, again, over here, the choice of schemes, like which ones to use, right, depends upon your problem, your mesh, right? So, one very good resource, which I have also read multiple times, is Wolf Dynamics. Okay, Wolf, Wolf Dynamics, and I think for meshing, not Snappy, they have a general document. So they have a general document for selecting the controls. You can also read for meshing. So they have a lot of documents that are available, right? So you can look at the PDFs that are available over there. Right? So they have what was one? Okay, if I find it, I will definitely share it with you. So they have various PDFs that are available. So in that, they give certain guidelines, right? So that is based on years of practical experience. So basically, when you have a certain level of skewness in your mesh, when your non-orthogonality is say up to a certain level, then you need to switch between schemes, and this is something that you know will not come. What you can say will not come to you in day one or day two. It will come to you only after you have done n number of simulations. You understand what each of these schemes do, like whether they are what you can say first order schemes, second order schemes. So for this, I recommend that you take some time and do that. So see Euler method. It is an explicit formulation. So whenever you use an Euler method, you will have to select your time step in such a way that it is within the stability criteria. You can the other option is you can go for backward. Or you can go for Crank Nicholson. Okay, so those method will allow for a little larger time step, but they may be oscillatory also. So it depends upon the problem. So these things you decide based on again your mesh and your problem settings. So this is very problem specific. So one thing will not work for all. Generally, what you do in such cases is just copy the base tutorial that was given, right? So in your tutorials, some tutorials will be given, right, for CHT. Look at them. So that will be a good starting point for you. And then modify them based on a specific problem if it is not working properly. So that is my suggestion to you. Sorry. Then FV solution. So here again, for computing my row final PRGH, right? PRGH final and my what you can say. See, because I'm solving for internal energy, so I will solve for a U equation. Sorry, U equation and a E equation. I messed up. Right. So which solver I'll be using for that, and what will be the tolerances for that, and then the algorithm that is going on. So it is solving based on the Pimple algorithm, and if you need to give any relaxation factors. So generally in transient simulations, because this is a transient simulation, it is not advisable that you relax the equations too much, and then you will lose time accuracy. Okay, so if your solution is not converging, it is best to reduce the yeah, I think somebody shared some manual already. Yeah, so it is always best to use a lower time step. Okay, so that is FP schemes and FP solution. Then next is in the metal folder. Again, same thing. So there will be FP schemes and FP solution. Yeah. So again, as I said, these are problem specific. So now that's it. So let me see how to run the case. Okay. So now again, if you want to run the case, there are two options, right? One is if you have done it in series or if you have done it in parallel, right? So if you are meshing in series, then the initial what I can say commands like block mesh, surface features, then SnappyHexMesh dash override, and then split mesh regions with default region name as fluid. This will create the complete mesh for you. After that, you can directly run by the CHT multi-region foam command. Okay, and then you can view the results in parafoam. Now, only thing over here is whenever you have multiple regions, then the normal parafoam does not work, and you have to use the parafoam dash built-in command. So this works. So remember this. So if you're getting error after running parafoam, if you're in CHT, then you should go and use the parafoam dash built-in command. Okay. Now, if you are running it in parallel, then as Evan explained, that you need to first decompose it and then run, and then over here, if you see, you need to run it by the MPI command. So the command works by what you can say, giving the MPI command, then the number of processes. Again, this depends upon how many processes you have. And you cannot just change over here. You have to change over here and in the decompose partict as well. Then your solver name and then hyphen parallel is the keyword that is telling it to run in parallel. Now, after the parallel run has been done, then you reconstruct the case. You can reconstruct all the regions and then you can view the results. Okay, so let me show you. Sorry. Okay, so Snappy is done on this. Okay, so Snappy is done on this. So let me, I will not decompose for simplicity. Let me run CHT multi-region foam. Okay, so here you see it has started to run. Okay, and it has selected various thermophysical models. It has selected the where was that part in the solid? It might have selected one. Yeah, FP models. So it has selected the FP models and it is adding a heat source to all the cells within the solid region. And then it is computing the Courant numbers. So the other thing that I forgot to tell you is the control dict. Yeah. So in the control dict, I am saying start from latest time. Now this is helpful. The latest time command is helpful if you have stopped your simulation in between for some reason, right? So we keep doing that. So say if I run it till 1 second and after that I want to restart it, I don't want to start from zero again. So then this start from will be latest time. Okay. Stop at end time. And end time I'm specifying to be 10 seconds. And the delta t that I've chosen is 0.0001. That is 0.1 microsecond, milliseconds. And then I'm saying write control is adjustable write time. Okay. So with this, what will happen is I will get proper files written at proper time intervals. Otherwise, I will have files written at various, any random time intervals. Okay. Then purge write is basically used. Say something for, I don't know. It may not be as helpful as in transit simulation as in steady simulation. So if you're doing a steady simulation, you keep writing the data so that suppose in between your simulation stops or it crashes, you have some file that is there which you can take and use that as an initial guess. Okay. Now, in steady simulation, you don't need to write, say, all the files, say, because I don't know when my computer will stop working, right? So that is just a guess. So if you say purge write as say 2, then it will save only the last 2 files. So I am saying that right after, say, if I say right after every 1 second, so it will save the time, it will start saving after every 1 second. Now, if I am on the 8th second, it would have saved the file for the 7th and 6th, but I will not have the files for 5, 4, 3, 2, and 1. That means it keeps cleaning that. The advantage is that whenever you are doing large simulations, you do the one file, like specifically for this case, one file that whatever I write will have a size somewhere around 300 MB. Now, if I write 100 files, that will be close to 30 GB. Okay, so if I don't want to save those many files, then it is better to use purge write. The other thing is the choice between, this is important, the choice between a transient solver, right? Because right now we are running it as a transient case. So choice between a transient case and a steady case depends upon what is your application. Like for example, uh, say if you are having a heat flux that is oscillating in nature and you want to capture the response of your system, okay, then you cannot run a steady state simulation. Okay, you want to see how your system responds to a transient change, you will have to do a transient simulation. Okay, but say for case like this, the one which we are solving, even a steady state simulation is possible. We have showed you transient, it can be switched to steady state because you are only interested in what will be my temperature at once it reaches steady state. So in that case, always go for steady state, it will converge faster. Okay, but we have showed you how to run a transient case. There is another case that I will be showing you that is very interesting. Okay, so this is the choice between steady and transient. So next, write format. I would suggest keep the write format as ASCII. For some reason, it is binary over here. Okay, ASCII means we will be able to read it. Binary, it will be in zeros and ones. So if you even if you open the file, you will not be able to read it. So change it to ASCII. Then these are just write precisions. How many what you can say decimal places you want. Then yeah, this is something very important, runtime modifiable. So see, now if I were to change anything in my control dict while the simulation is going on, and if I have this runtime modifiable true, that means it will take the updated changes and it will start working on the simulation itself. That means I can, during my runtime on the go, I can change the parameters. So if I have this runtime modifiable true, now, and then if I have this adjust time step, okay, set to yes, then it will limit my maximum Courant number and my maximum diffusion number. Okay? Because if you don't want it to exceed beyond certain limit for stability regions. So if your say maximum Courant number is going higher, then it will adjust your time step and lower the time step to reduce the Courant number. And if your Courant number is say too low, then it may also increase the time step. The other thing that what we have done over here is we have added something called as a function. In that function, we are monitoring the average temperature fluid metal interface. So what we are doing over here? So if you see, we are using the post processing utility. I will not say post processing. Yeah, we are using some function objects to gather some data, right? In this, what we are doing is we are calculating the temperature at the interface. So we are saying that use the surface field value, what you can say, this utility. And in that, I want the area average. That means area average. Area average what? Area average temperature. The field is temperature. Okay. Then it is available in this library. Okay. Whether it is enabled or not, true. If I want to write it, yes, write for every time step. And write interval is 1. I want to log it, yes. The write field is false because I don't want to write these fields for all time step. I just want it to be written in one file. So I kept this as false. Then the region, it is working on the metal region, and my patch name is metal to fluid. So I want the temperature of metal to fluid written over here and for the T field. So this way it gets written. I don't know if it has started running. Yeah, it has started running. So maybe I can show you. Yeah. So you see, once you do that, a post-processing folder gets created, right? In that, because I've said it for the metal region, a metal folder, an average fluid temperature interface gets created. In that, it starts from 0 because that is, it will create a folder according to your time. So it started at 0 time, so 0 folder will be created. So if I open that, a surface field value dot that file is available. So all the contents will be written in this file. If I open this, you see the average temperatures are written over here. Okay. Now, because obviously the simulation, the time step is very small, the values are not increasing that much. Okay. But if you run it for a longer time, it will keep running. Okay. And you can plot this. So you can either plot, you can open it, plot it in Excel, or the other thing is, wait, you can use, you can open this location in your terminal and you can use foam monitor You should use GNU plot. Yeah, so I can also, sorry. I'm sourcing it and then I'm using the utility foam monitor. So it works by this way. You specify foam monitor and then the file name. The file name is surface field value dot dat. So if I just start typing and press tab, it will automatically write it. So if you see, it is starting to plot. So this is one way of monitoring the solution, right? So you want to know whether your solution has reached steady state or no. Because in the case of transient, you will not know when your solution has reached a steady state. So generally, you solve this till your curve goes this way and then flattens. Okay, and as soon as it starts to flatten out, right, means it will asymptotically reach one value, right? Then you say that okay, it has reached steady state. Then you can stop the simulation. So this is one way of monitoring the whether your simulation has reached steady state or no for the transient case. Okay, I'll just close this. So the utility that we have used is foam monitor. Pushkar, PyFoam to track residuals. Yes, you can use PyFoam. There is another utility, built-in utility available. We can do the same thing in using. Basically, you add a residuals. There's a file named residuals, right? You add it in your control dict, and you can use that as a function. You can call it in your. Where is my control dict? Yeah. So over here in functions, you just write hashtag and then include func and then residuals. So it will calculate residuals and you can track the residuals using the foam monitor. So that is also one way of doing that. You can use PyFoam as well. Depends, like there are many things. For some reason, but in the CHT case, for us, the residuals are not working in this V9. I don't know. Previously, it was working for us 6 months back. Suddenly, what has happened? I don't know. Some update or something. I'm not able to figure it out. It is not working only in CHT case, but I have another case. I will demonstrate in that. I'm able to track the residuals. I'm able to do the other things as well. Yeah. So this is running. This was what I wanted to talk about for this specific case. Okay, so see, this is taking ages to run because I have shown that this is a transient case, right? So just let me stop that. That's why we've already run it and we have kept the case that is solved. I will open that. See, I've already solved. You see, so many files are there. After some time, we stopped writing, because it was saving too many files. And if you see one file, its size is around 250 MB. Then if you have 100 files, then gone. So you need to decide what you want, right? So transient simulation was not needed, but okay, we thought let us show how it will evolve. That was the idea. So let me open this particular case. Yeah. So as I told you, I need to first source my OpenFOAM version. Then I will have to use Parafoam built-in. Okay. Otherwise, it throws an error. Yes. So if you see the data is too much, takes a little bit time to load. So if I want to view the internals, I will have to first create a slice. I will click on the slice over here. Then I want the slice to be the Z normal so that I am able to view it, right? I want to color it, say, based on velocity. Okay. I will hide the plane. And if you see, go to the last time step. Yeah. So this is how the flow is taking place. You see the flow is coming from the left and going over this block. And because we have the top, bottom, and the front and back have been given as walls, so we see no slip kind of a phenomena happening. That means we are generally capturing the boundary layer that is there. And see, Evan was talking about the add layers, right? So add layers, basically you use that to be to add the boundary layers near an object. So whenever you need to refine that. So again, in that he told you two options are there. One is whether you specify the last cell size, or you specify the first cell size. Generally, you go for the first cell size whenever you want to control the y plus value, right? You want to have you want to do the, what you can say, uh, yeah, turbulence modeling, and you want to use wall functions, then specifying the first cell size accurately, right, the y plus value accurately is important, so that you can fine tune and control by the first cell height. So in that case, you control the first cell height, and then from there you need to control the transition ratio to get a nice smooth mesh. So I was talking about that. Let me go to the temperature field. So if you see in the temperature field, the block has heated up. So we have ran for around 100 seconds. In that 100 seconds, the block had reached a temperature of 490 Kelvin. So, okay. Okay. So now I still have time. Good. So there are a few things that I wanted to show you. Yeah. Let me close this. Okay. So I have. Yeah. So I have another template for another case. Okay. Have we mentioned this? No, we have mentioned the other one. So let me first open this and show you what is the case at hand. Okay. So that it becomes easier for me to talk about the case. So Length, minus length. Okay, okay. Okay. Leave it here. Okay. So maybe I can do this. This will be better. Yeah. So this is better. So if you look at uh, this is a case where the outer region is a fluid. We have solved this as a 2D case, right? So this case was set up by our one of our colleagues, Divesh. Okay. So he runs the channel DD Fluids. He's very famous that way. So he had set up this case. So this is again a very interesting case when we want to demonstrate the capability of CHT, because unlike the case that we showed only two regions for simplicity. Now here we have three regions. So the central region, which is heated over here, right? That region is your heater. So that heater is embedded into a metal. That means there is a metal inside a metal, and from there it is getting heated. Generally, suppose if you want to simulate, say you have a cartridge heater embedded into a block that is heating, and then that heat is diffusing into the block, and from there it is being taken up by some fluid. So this is the application that comes to my mind. Then you can do what you can say, this sort of an approach. Or if you want to do CPU cooling, where there is a block, there is another heater. So there are maybe, there are three layers to it. So there is a block that is the CPU itself that is generating heat. On top of that, you have the, what you can say, the heat dissipator. And then on top of that, you have the fluid. So such case also. But this is different in the sense that over here, the heater is completely embedded into the solid. So we have three regions. So one is the region heater, then the region metal, and then the region solid. So this is something that we want to simulate. So how we have set up this case. So let us look at that. So if you see, I'll go to the template, so it will be easier for me to explain. Yeah, so we have the zero, constant, and system folders. Can you change the color map? Yeah, I can change the color map. You want me to? Um, the preset, maybe jet or something like that. Yeah, you can change that. That is fine. Okay, so just let me close this. Let me go to the case setup once. So 9, if I use tree. Yeah, so if I run the tree command, you see that inside zero, there are 3 folders now. Okay, the first folder is fluid, then there is a heater, and then there is a metal. Okay, now inside fluid, there are files for the fluid, inside heater, files for the heater. Now this was done in a previous version in 2000 in V7. So there, for some reason, a P file was also needed. Okay, but for the from the new version onwards, the P file is not needed. Only the temperature file is needed for the heater and the metal. So that means for the solid regions. Okay. Then we have a constant folder. In that we have fluid, heater, metal. Again, the properties. Then another important file, the region properties. As I said, that defines the regions. Then again, fluid, heater, metal. In each of them, you will have the decomposed under the system folder. You will have decomposed product, FP schemes, and FP solution. Okay. Then, as I told you, to mesh, you have 2 options. Either you mesh it using what you can say the toposet utility, or you mesh using SnappyHexMesh. You mesh using external mesher. Here we have used the toposet deck. So I will also explain to you the toposet deck in this case. Okay, so let me go through all the files one by one. So under zero, you have fluid. So the boundary conditions are basically the same. Okay, so if you see, P will be calculated throughout, and PRGH will have fixed flux pressure for all the walls, and outlet will have a fixed value. Okay, then under temperature, again, internal field is initialized to 300. At the inlet, the air is coming at a value of 300. Outlet, inlet outlet type of boundary condition, and coupling at the fluid to metal interface. And all the remaining walls are zero grading. So these boundary conditions kind of remain the same. So I will not go over it. Now, so if you see, there are 3 regions, right? So now if I open constant, something important, see in the region properties file. So if you see, earlier for our case, we had fluid and we had only metal, right? So here we have fluid, metal, and heater. So there are 2 solid regions. Okay. So for these 2 solid regions, they are defined over here in the region properties dictionary. So this is how the solver knows that for the metal and for the heater, I need to solve it as a solid. Okay, so this is my constant. Then inside each of them are my thermophysical properties. So again, thermophysical properties, I am calculating everything, the same thing as I told you, right? You need to specify the density, thermal conductivity, and the CVCP values. Now, yeah, heater. This is important. In the heater, if you see, we've added FP models. Okay, and if I open that FP models, so this is something very good. So the previous file was on V7. So in V7, somehow it was much easier to write this code. So I have modified that. I have modified it to work in V9. So if you see, in our case, right, the one which we presented before, we were adding heat at a constant rate, right? And that heat is being added throughout. Now, in this example, what we are saying is that we want to add heat for a specific time only. Okay. And after that, we will stop heating it and then see the response. And then we look at the transient response. So that's what we are doing. So we are using the type of source as semi-implicit source. Okay, we are using the selection mode all. Again, this file is located in the metal folder, sorry, in the heater folder. So all the cells inside the heater domain will be selected. Okay, and volume mode is absolute. Okay, that means I'm adding whatever value that I add will be added to the entire domain and not on the volumetric per cell volumetric basis. So that's what it means. Okay. Basically, it means if you have the value in watts, you keep it as absolute. If you have the value in watts per meter cube, you keep it as specific. So just remember this. Now, I'm using the semi-implicit source type of a declaration. So I will have an explicit component and an implicit. Because we are explicitly specifying our value, we will add our value in the explicit. And if you see over there, I'm using the coded type of a definition. So this coded type of a definition allows us to, what you can say, change the values based on the location of the mesh, based on the time. So here what we have done is change the, what you can say, source that we are going to add based on the time. So if you see over here, I have defined a scalar named power amplitude just for the sake of it, right? I'm saying calling it as 100 just to show you that maybe I can use that and then modify that amplitude based on the time as well. So here I am using an if-else statement. I am saying if x is less than 1, x in this case represents the current time, okay, in this formulation. So if my current time is less than 1, I am saying return magnitude of power amplitude. That means return this return value 100. That means for time less than 1, the heat that I'm adding is 100 watts. Else, that means if time is greater than 1, I'm adding 0. That means I'm heating only for 1 second. So this is one example that we have given you. You can add, what you can say, you can add a sinusoidal power input over here with this mag, right? You can add a sinusoidal power input and this mag will give you the magnitude. Something like that also you can do, and you can look at the response. So these are just some suggestions which you can do. So with this, what will happen is we are adding heat only for 1 second and then we are stopping the heat addition. Then we see how the system responds. Okay. So after I do this, I'll close this. Yeah. So this was something that I wanted to show. Yeah. The other thing was my so again over here in the control dict, I am adding a function utility to track the interface temperature between the this I'm tracking between the heater and the metal interface. Okay. How it heats up. The other thing that I wanted to actually explain is toposet dict, right? So what happens is maybe I will run this and then explain to you. So that will be much better. Yeah, this is a template. So okay, I have opened it. Yeah. So I will first run the block mesh utility. Okay. Once I run the block mesh utility and I will view this mesh. You see, it is a simple mesh, block mesh, right? In which I have added small, what you can say, a fine mesh. Now, this is just one region. Okay. It has not been split into multiple regions. So my aim is that in the center, I want one solid, right? And within that, I want one heater. So block mesh has just meshed it and given me n number of cells. Now, with toposet dictionary, what I can do is I can select some cells at the center, right, which correspond to the size of my domain, right, and then I call them as say metal and call them as heater. So this is a simpler way of generating this mesh. That means I take already the mesh that is generated by block mesh, and only certain cells that are at the center, I will what you can say capture, select them and rename them, okay, as what you can say solid or metal. So now how do I do that? So that I can do by the toposet utility. So that is in your, so that for that to work, you need a toposet dict in your control, in your system folder. So over here, I will kind of explain to you all whatever is done over here, okay? So what we are doing is under actions, whatever actions need to be taken are defined over here. So we are creating a cell set. Okay, the type is cell set. Okay, so we are calling that cell set as CS, and we are creating a new cell set, and the source is box to cell. And basically, what it does is we are giving a box, right, with some endpoints, and all the cells that lie within this box are being selected by this utility source info and box, and those cell sets those cells are added to the cell set called CS. Okay. Now, this dimension is selected such that it matches the dimensions of the heater zone that I want. Okay. So if you see over here, my heater zone is 1, 2. So heater zone is 1 centimeter by 1 centimeter. Okay. Something kind of like that. Yeah. So all the cells within that zone, I am selecting it and I am calling it heater. Okay. So first is I am creating a cell set out of that, right? And that cell set, I am converting it into a cell zone. So the second action is convert the cell to a cell zone, and that cell zone is named heater. So once I do that, if I do only this much, all the cells at the center which lie within this box will be added to a new cell zone called heater. Okay. Then after that, what we are doing is we are creating another other cell set. For some reason, we are calling it BS. Okay. We shouldn't have called it BS, but okay, we have called it BS. Now, okay. So I'm creating a new cell set. I am okay. I am again mentioning a box. All the cells during this box. Okay, excuse me. So all the cells within this box we will select, okay, and add it to the new cell set. Now, yeah. So basically what we are doing is around the heater, there are 4 regions. Okay, that means the heater is being encapsulated by the metal. So I'm selecting only the regions around that heater. So these are the 4 zones, 1, 2, 3, and 4. So all of those 4 zones, I don't know how, maybe I should sketch it. So that will be better. Just give me a moment. Yeah, I hope this is visible. Yes. So basically what we have done is so I have say this is my metal block. I'm now only looking at the central region, okay, leaving the fluid aside. Okay, I had one okay, I have I will maybe change the color. So I have one central region called heater. Okay, so initially what I did is I selected the endpoints. So this will be in okay, how do I do that? Okay, maybe I do it over here. So if you remember, this is OpenFOAM always deals with things in 3D. Okay, so the heater is actually something like this. Okay, it is in 3 dimensions. So whenever we are specifying the box, okay, to capture the cells, we need to specify these corner points 1 and 2. Okay, when we specify these corner points, it will consider that to be one sort of like a zone, and all the cells that lie within that zone, it will select. So that is what the first, what I can say, command did, right? Box to cell, and then that we created into a cell set, and that cell set became a heater. So the pink one is done. Now, for some reason, what we are doing is now dividing this into 4 regions, right? So say this way, I can now do that. So I will divide it into this way. So I have 4 regions like this, right? So this will be 1, 2, 3, and 4. Okay, so I can use 4 box to cells and capture this whole remaining area. Okay, so that is one approach to do that. That is how it is done over here. Now this numbering may be different, but this is the approach. You can understand that. The second approach is, which is much more simpler, is I would have done is, rather than that, go for a box to cell, start from here and then go to the 3rd dimension, right? And select that. So it will capture all the cells within the black box. Now, once I have captured that, the disadvantage is, remember that all the cells within the black box also lie within the pink box over here. That means within the heater. So that means all the cells of metal also have the cells of heater within that. So I would have had to delete the cells of heater in that. So I would have had to capture that all the cells within the black box and delete the cells within the heater. So that is another way of what you can say, creating a cell set for the metal region. So the one which we have demonstrated is one way, and the other is that. So I think both those ways we can try. Okay. So let me switch back. So I'm back. So if you see, all these four cell sets are for the what I can say, the region around the metal, and then all of them. So if you see the utility, if you see after we created one cell set, which was a new cell set, the action was new for it, right? For the others, we have the action is add, and the name remains same. Okay, so we are just adding to the same cell set. So we are kind of grouping them and adding to the same cell set. And once we have added the cells for all the regions, then we create from that cell set a region called metal by using the cell zone set. Okay. Now what we are doing is we are similarly we are using the same approach, and all the cells around the metal region now. Okay, all the cells around the metal region that are in the fluid domain, because our metal is inside the fluid domain, we are selecting all of them, right? And then adding it to the cell zone fluid. Okay, so we have created another cell set. So this is a much more lengthier way of doing it. I suggest that you create one cell set that encompasses the complete domain and then subtract the cell set, or you delete, use the delete function instead of add function. So that is the easier way of doing that. Maybe that is something also that I don't know, that I don't have enough time to demonstrate that, but that is something that you can try. So only the action will be, I will give you a hint that once you've got the entire cell set, then you use the action delete, and then this box to cell will be the box. Like if you, from the fluid, if you want to delete the metal and heater part, so you first create a box that contains the whole domain, then use the delete function and use a box that contains the metal with the heater embedded in it. So that was the much more easier way of doing this. Okay, so we have done that. Now let me go back. So that was topo set dict. So once we have done that, that's my thumbnail. Yeah. So what we have done is we have done block mesh. So after we have done block mesh, we need to run the topo set utility. S is capital. So if I run topo set, if you see over here, yeah. So it is creating cell zones, right? For the cell zone that is the at the center, there are 400 cells. So these 400 cells are added to heater. Okay, then for the other, right, we have 450, then another 450 are getting added to it, then another 1000 are getting added to it, right? No, after that, 900, 100 cells were added. Okay, and so on. And then we have, where is that? Fluid cell zone set. Wait, let me have. For cell zone set metal, we have a total size of 1100 cells. Okay. Similarly, for fluid, all these things have been done for fluid, and we have fluid cell zone set as 38,500. So this is our domain that we have added. Okay. Now, after I've done the topo set command, remember it has created those cell zones, but it has not split the mesh based on those cell zones. So we need to run the command split mesh regions. Into cell zone and then overwrite. So this is my command. So I have split. So once I do that, if you see inside my zero fluid, then that cell 2 region will come, and inside my constant, inside fluid, I will have a polymesh folder. That means it has split the mesh. Okay. Once this has happened, now we can run the CST case. So see, it compiled the dynamic code for adding heat, and now it is running the case. So just give it a maybe 30 seconds or a minute to run. Let me grab a glass of water till then. Yeah. So see, our simulation is done. Now we can view the results. Again, to view the results, you will go to Farcom, and then use the built-in function. Okay, I think so. If I click apply, because it is 2D, I don't need to add a slice. I can directly look at my temperatures. Okay, so see, to begin with, now see with time, because we saved only after 1 second, right? So after the first second, if you would have saved in between, you would have seen the metal part also getting heated, but we saved after every 1 second. So till 1 second we've added heat. So you see it to become to be red, right? And we have reached a temperature of roughly around 310. Now in the next time step, you see that it is not heating, but it is cooling. Okay. This is because we stopped heating after 1 second. So whatever heat was added, it now is cooling that region, right? And maybe we can also look at the velocity. So this is how the velocity is for this case. Now let me show you the what I can say, the interface temperature curve. I will close this. Yeah, I will close this and let me open the foam monitor. Post processing heater, average temperature 0. Foam monitor and then so if you see over here, what we are doing is we're capturing the interface temperature. So till 1 second, the interface temperature was rising because we were adding heat. As soon as we reached 1 second, it started to drop. Okay. So now you see another thing that I want to point out is, I don't know if you all missed this, is that see, whenever we added this utility in my control dict, I am getting data for every time step. Okay. And I am able to see the temperature rise. But in my paraview, right from 0, I directly go to 1. Okay. I don't have anything in between. This is because I have not written the data. Okay. And why I have not written the data? Imagine if I write the data for every 0.1, 0.01 second or so, it will kind of completely what can they fill my hard drive. So whenever you are doing a transient simulation, right, it is very important for you to sit, right? I don't know. This was also this also came out in yesterday's talk, and this is very important. Whenever we take courses also over here, we say that to the students, before you touch the simulation, sit with a pen and paper and write down what you need. Okay. And what you're expecting, what are the results, any theoretical analysis, whatever it needs to be done is done. So that is the first step of CFDs. First step of CFD is not meshing. Okay. First step of CFD is to take a pen and paper and completely break down your problem on the paper itself. Okay. So I know that I want to track my interface temperature, right? That is my objective. So that's why I've added this interface temperature, what I can say, algorithm to track the interface temperature, and I'm getting this plot. If I would have simulated this case and then I want to extract this data, it wouldn't have been possible because I'm saving data at only 0 and 1 second. So you see, I would have missed that. I would have missed that detail. So this is something that is important. Okay. What else I wanted to say? Yeah. So another important thing. See, over here we are only monitoring the surface temperature because I told you for some reason in our CHT case the volume added. 1 minute. The Zoom window is kind of coming in between. Yeah. So, where am I? So for some reason that those utilities are not working. But I have another case which I have run. So with that, I can demonstrate those utilities. So I have a pipe. Okay. Okay. I have a pipe. First, I'll demonstrate what are the contents. So I am simulating a flow through a pipe. So I don't know, I think you don't need to go through all the boundary conditions, but the most important boundary condition is for the temperature. So for the walls of the pipe, I am giving a fixed flux. Okay. And that flux we give by using the fixed gradient kind of a boundary condition. So all of us, we are accustomed to giving the zero gradient boundary conditions. But at the wall now, I have given a fixed gradient boundary condition. This is because if you know Fourier's law says that Q is equal to K times my temperature gradient, that is dt by dx normal to the wall, or dt by dn is what I should say, right? So if I want to capture the gradient dt by dn, then that is nothing but the Q, that is the flux that I want to give, divided by the thermal conductivity of the medium, in this case the fluid. So that we have calculated. So my flux is 20 watt per meter square and my thermal conductivity is 0.024. So from that, my gradient comes out to be 826.45. So this is one way of adding a flux, that you give a fixed gradient. Okay. Then at inlet, my temperature is 300 and at the outlet, it is zero gradient. So this is the only boundary condition. So remember this. Now, along with that, so in the heat flux pipe, and remember, okay, one more thing I wanted to point out. See, I did Q by K, but if you see the thermophysical properties, I am not explicitly specifying K over here, right? Thermal conductivity is not explicitly specified. The reason being, you are specifying Prandtl number, you are specifying mu, and you are specifying rho. So if you specify K, you are kind of over defining the problem. Right, because Prandtl number is mu by alpha, alpha is K by rho Cp. So only one unknown remains, that is K, which you can get from this. So that's why the solver does not need you to specify K. If you specify, then you are kind of like over, what you can say, over constraining the problem. So that's why K is not needed. K gets computed from these values. So it is a basic simple math. I think if you have done a little bit of heat transfer, you'll be able to understand that. So that's why we don't explicitly specify the thermal conductivity. Yeah. The next thing that I wanted to show you was my system folder. Okay, why? So in the system folder, if you look at the control dict, right, we are adding something called as volume field values. So this function works by giving you the volume averaged value of any quantity that you want. So whenever you are running a simulation and you want to know if your simulation is converging or no, like in the first case, we only were able to somehow only capture only the interface temperature, because for some reason with CHT, the volume averaging was not working. Okay. This is not CHT. This is buoyant simple foam. Okay. And over here, I am able to use the volume field function and extract the average temperature inside the complete region. And I'm able to plot this. Okay, so so with this, if I do this and if I plot it, I will get the temperature, what you can say, how it is increasing. So this is something that you can add. Okay, outlet zero gradient. Somebody asked outlet zero gradient. Is it for pressure or temperature? Outlet zero gradient is for temperature. For the pressure, I have specified a fixed value, and the inlet is zero gradient in that case. So I have given a velocity inlet and a pressure outlet, so to say. Like I have specified velocity at the inlet, and at the outlet I have specified a fixed pressure of 0. So don't worry. I will share all these files with you for all the participants that are available. I know that I'm speaking a lot. You're not getting to do things, but this is the only way wherein I can cover a lot of content in this short amount of time. Because if I give this file and you are doing it with me, and if I have to sit over here and answer every question, then we would have been doing only what you can say SnappyHexMesh till now. That is our experience. So we have generally for such cases, right? We do a 6-day workshop. So that we did in last February. The recording is also available. In that case, we had shared the files. We allow for follow along. We take questions. And then we have 5-6 groups of people who are online and helping, all the people, all the students who are there. So for this session, I know it is difficult, but then we we had to decide, we had to make a choice what we do. So we decided that we will only demonstrate, but we will be sharing all these files with you. So if you see these templates that we have made, these templates are to be shared with you. Okay. So only thing is we will wait till the end of the session and we will share all these templates with you. Okay. So where was I? Yeah. So in the template, we have 3 files. Similarly, we have for multiphase and dynamic meshing as well. Yeah. So let me go to the result and directly present. Uh, Running buoyant simple form is pretty straightforward. You just run block mesh and then you run the buoyant simple form case. Okay. Another thing that I added over here. Yeah. So see, another thing that I added over here, which I forgot to tell you, is that yeah, I missed over there. So this field was there. So this was creating a problem. I have commented this. So if you see, I have added a heat flux uh, post processing utility, right? So what is this doing? It is writing the heat flux on the patch wall for every time for me. So now how will this be helpful for me? Okay, this will be helpful for me if I want to calculate what will be my heat transfer coefficient later on. Okay, so how do I intend to do that? I intend to do that in ParaView. Though if we do a little bit more advanced programming, we should be able to do this by writing a what you can say a small code of our own. But then that is not the agenda of this. But then using this small utility, we can do it easily in ParaView is what I wanted to demonstrate over here. So I told you that I have written what you can say in the end, a wall heat flux utility that will compute the heat flux at the wall and write it. Okay. So now if I run the case, this case is already ran. Maybe I'll just open it in terminal. It opens. I click apply. So if you see, if I do surface with edges, I have a nice structured mesh. I don't know. This is O-grid type of mesh, I feel. But I might have made a mistake also in naming. So you see the mesh is refined near the wall where I want to capture the boundary layers and slightly coarser near the center where the gradients are very low. So wherever in the regions where you are expecting maximum gradient, your mesh should be fine. So this is the cross section, right? I can align the mesh along the x-axis. So this is how the mesh looks along the length. Okay. Now to view the insides, I'm adding a slice and I'm showing you the say velocity. And then if I play this, so this is how my velocity profile looks like. Okay. So I have a boundary layer that is forming at the walls. Now if I switch to temperature, I see that the temperature field is diffusing more because of the way that we have set it. And what you can say, it is combining and we are getting a combined, what you can say, thermal boundary layer. So now once we have this, what I can do is I showed this only to show the internal region. I'll delete this. What I can do is I can only look at the outlet patch and compute the heat transfer coefficient. So how I can do that? I can first filter and then take only the using the extract block utility, look at only the wall. So I click on extract block, click on wall and apply. So it is only selecting the wall for me. See, now everything else is gone. So only the wall. Now, okay, I missed one step. I'll go back, delete. So whenever you say import or you import the results into ParaView, right? What you need to do is any additional variables that you're generating, which are not directly part of your case setup, they don't get added into the fields directly. So you need to check them, say like the flux phi and the wall heat flux. So I want the wall heat flux to be used. So first I will go down, check it and then apply. Then only it will be available for me for post processing. Now again, go back to filter, then alphabetical extract block. And then I want only the wall to be extracted. Okay. So you see, we have this. Okay, wall. Now, what I can do is I can compute. So use the calculator function. Now over here, if I want to calculate the heat transfer coefficient, so I call it HTC my heat transfer coefficient is my flux. So fluxes will be in the scalar. So I go to the wall heat flux divided by, so Q is equal to H delta T. Q will be in the flux. So H will be Q divided by delta T. Yes, Q divided by delta T. Delta T will be the wall temperature. So again, wall temperature will be in the scalar minus the, now see, this is something important. Right? This, for a flow through pipe, you don't have one bulk temperature. Say if you had a flow over an external body, right? The free stream temperature is what you can use as a reference temperature. But flow through a pipe is a very different case. Even though I've demonstrated for this, so I have to show. So here there is no one reference bulk temperature, but the bulk temperature itself changes from inlet to outlet. If you read the theory, right? So this may not be an accurate representation, but my what you can say idea over here is just to demonstrate that something like this can be done. So because my bulk temperature is changing, I am now saying, okay, leave it. I'm just giving the inlet temperature. That means I'm calculating it based on the inlet temperature. Okay. So this is, remember, this is not the correct approach. Okay. So for this particular problem, that is flow through pipe. For flow through pipe, your bulk temperature is not constant along the length of the pipe. Generally, it varies linearly from the inlet to the outlet. Okay, so now once I do that, if you see, it is coloring this based on heat transfer coefficient, and rightly so, heat transfer coefficient at the inlet will be very high. When the flow has just come in, the boundary layer will be thinnest over there, and so heat transfer coefficient is lowest and then increases. You can plot this and so on and so forth. So this is another way of doing this. From this, again, from heat transfer coefficient, you can compute Nusselt number. But again, then you cannot compare this with the analytical solution only because can't we take T average? What do you mean by, okay, what do you mean by T average? You mean average of the patch? Okay, somebody had posted a question. Maybe let me see over here. I think I've almost covered everything that I wanted to show. I wanted to show you, I have mean temperature of the patch. Yes. So one thing is, remember, how you calculate the mean is very important. Okay. So if I just take a patch, like if I take an inlet or an outlet patch, let me demonstrate that. Okay, this is, I extracted the block. Maybe let's delete this. Okay, delete this. I will just directly from here, for simplicity, just look at the outlet patch. Okay. If I click on the outlet patch and then click apply, I'm viewing only the outlet patch. I want to view only the, say, temperature over here. Okay. Now, if I do this, right, that means if I rescale it for the current time step, and if I look at it, to the direction Z, yeah, this is the right direction. So if you see, my temperature is hottest at the wall and cold at the center, right? This is my temperature. If I look at the velocity, okay, my velocity is lowest at the wall and highest at the center. Okay, so if I just average it for the patch, that means if I take an average area average of the temperature, that is not the correct representation of the mean temperature. The reason being, whenever you want to calculate the bulk mean temperature, you have to also take into account that maximum fluid is flowing from the center, right? Because the velocity is high over there, right? If you look at it in that terms, the velocity is high, so the amount of fluid that is going from the center will be more, and over here from the velocity. If I do rho A B like Q, right? The flux, the volumetric flux will be highest at the center and lowest at the wall. But if I look at the temperature, it is the other way around, right? So if I do just a patch average, it will mathematically average and give equal weightage to all the cells, and that is not an accurate representation. Whenever you want to do that, you need to apply it. You need to do something like rho A V and then into T. Okay, if you understand what I mean, you to understand this, I suggest that you read the book by Encro Pereira. They will explain how to calculate the mean temperature for such internal flows. So that is not the correct representation. Even if you take that, it will be better than the inlet temperature, obviously, but then it will not be accurate. If you want the accurate, then you have to compute that in that way. Okay, I think I hope that is clear. Now, maybe quickly, I have another 2-3 minutes. I think I have already taken all the questions that are there in the chat. What I wanted to show you is to end with this is to show you where the solvers are, right? This CHT solver. So I can show you the path, or I can show you another way of doing that. Yeah. I'm gonna keep forgetting that. So if I just type in my thing, if I type SOL solvers, right? So it will take me to application solvers, and there here I can maybe grab whether I'm not sure if this will work. Uh, P, P, I hope this works. No, it is not working. Okay. But I will definitely show you where it is. So you know that your OpenFOAM is installed in the OPT folder. Okay. So inside OPT folder, now I have many versions of OpenFOAM installed, but I'm looking at OpenFOAM 9. In that, all your applications or your solvers are stored in the applications folder, and there inside solver. So there I can go to heat transfer solver and then CHT multi-region foam solver. And if you see inside CHT multi-region foam, there is a main C file, .c file. You can open that and you can see what is the algorithm, right? How it is calculating the different things, right? Um, so very quickly, what I wanted to point out is, yeah, so it is just saying first it solves for the fluid region, then it solves for the solid region. That is how, if you look at it in the terminal also, it is going through all the fluid regions, solving for the fluid, then going through all the solid regions, solving for the solid by using the solve solid and solve fluid files, right? And solve fluid and solve solid files are available in the fluid and the solid. Okay, and inside that you have, see, you have solve fluid.h. So there it is saying what you need to solve, the what you can say E equation, Y equation, rho equation. So you can go through this and try to understand this. See here, one more thing was the energy equation. Yeah, E equation. Yeah. So if you see in the energy equation, right, very simple. Right? It is saying He thermo. So now what it is saying is that if your He name is E, then that means if you're solving for the internal energy, then you have a different equation. If you're solving for enthalpy, then there is a different equation. Okay. So both, so the term only He means that you can switch between H and E, and very smartly they have done it over here. They allow, in one equation only, they have kind of used like an if else statement. So if the question mark over there, right? So if it is H, if it is E, it will solve it in one way. If it is H, it will solve it in another way. If you want more reading on this, I suggest that you search for energy equation OpenFOAM. Some very good content is available. Yeah, CFD Direct, correct. On CFD Direct, they have kind of nicely explained, because in OpenFOAM we solve for the total energy equation. Now, depending upon which solver you are using, right? So you can switch between total energy or internal energy, right? So here you see whether you're solving for the E equation or for the H equation here. These are the two equations that I was talking about, E equation or the H equation. So you can switch between them and solve. Generally for the solids, right, OpenFOAM 9 will not allow you to solve H equation. Solids only E equation. And for the fluid, you have a choice whether to solve for the based on the enthalpy or the internal energy. So I suggest that you go over this. This is a very good read, right, for people who want to get more insights into this. So apart from this, I don't know, are there any other questions? So I think we have, it is 1 o'clock. And then we should break for lunch, but okay. Nitin is asking, is CHT multi-region foam equally fast as Fluent? And see, I use both Fluent and OpenFOAM. So it is kind of a difficult question to answer. Now, fast in the sense of runtime, I suggest that Fluent may be faster in this case, because you see that it is just one solver which is highly optimized, right, for doing that. Now, CST region, multi-region form may not be as fast, right? But what it really gives you is the capability, right? See, now I opened the source code and I showed you. Okay, if you want to change anything, right, as a researcher, tomorrow, if you want to see, previously the total energy equation was not being solved, right? So this is what this article is talking about, right? This article is talking about, so if you don't solve for the total energy equation, and if you solve only for the thermal energy equation, then you see that you are not capturing the, what you can say, expected analytical results, because you are missing out on on some things. But they were able to modify this. So for some applications, suppose if something is not working, right, you can yourself modify and change this. This sort of functionality is available nowhere. So if you are thinking, you are comparing between Fluent and OpenFOAM, so you have to look at the pros and cons, okay, in that way. So maybe Fluent may be a little faster, and it will also converge. That way, it is also very robust, huh? It will give you converged results. And even if you make mistakes in the setup, then also it will give you results. That is also true. Okay. So with OpenFOAM, you have to kind of like really know what you're setting. Otherwise, if you get kind of get incorrect results. So that way, I feel OpenFOAM is much less of a black box than Fluent, because with Fluent, even a beginner will click 2-3 buttons and they will get a solution. So my take is that, okay. So yeah, after doing one simulation on Fluent, you feel as if you are kind of mastered CFD. So that is the feeling that you get, right? So, but definitely Fluent, from my experience, Fluent is faster in this case. Yeah. So okay, thank you. So I feel, so if we don't have any other questions, we will break for lunch now. We will meet sharp at 2 o'clock. 2 o'clock, Professor Naren will join us, and he will brief you, give you the theory about multi-phase flow. What are the various approaches? After he has done that, I will go over a few cases. Okay. Uh, I'm not sure what it means. Is open form an explicit base method or implicit? I'm not sure what you're asking. See, explicit and implicit formulations both exist. I think you mean is in time explicit, right? And implicit formulation both exist. So see, CHT, we were using an explicit formulation for time. That's why our time step was, we had to make it, what you can say, lower. You can also run it as steady state. You can run it implicit by using other schemes. Instead of Euler, you can go for backward, and so on. So that is something that you can explore. Again, you check for DDT schemes, more on it. So what I was saying was, yeah, Professor Naren will join us. He will give us a theory of multiphase, right? What are the various models, like what are the various modeling approaches for multiphase? Okay. And once he sets the stage for us, then I will demonstrate a couple of cases. Obviously, we may not be able to go into complete depth of that, but I will try my best to tell you whatever I know, and I will also point you to some very good sources from where you can gain some more knowledge on that. So hoping to see you after lunch. So we will break now. Thank you, everyone.
Hello, everybody. Very good afternoon. So welcome back after lunch.
Yeah,
It's not
good
yet
afternoon.
2, but Professor Naren has joined. So
Yeah, you're able to hear me?
hello.
Are you able to hear me?
Yes, yes, we are able to hear.
Yes, thank you.
Yeah. So it's not yet 2, but some of the participants have already joined. So if you like to talk to them, so Professor Naren is our esteemed faculty partner of OpenFOAM team FOSSEE, and he has guided several students for the internship and fellowship of OpenFOAM team FOSSEE. And he's a very well-known teacher and researcher, and we are really fortunate to have him in our team. So, sir, if you would like to interact with them, so in the morning they have had a session by Evan and John, and now after your talk they'll continue the demonstration part. So before your talk, if you like to interact with them.
Yes, I think I'm audible, right?
Yes, sir. You're audible.
Yes, fine. Okay, right. Okay, so I think can I start?
Yes, sir, it's almost 2. I think we can start.
Okay, right. Okay, so let we'll join, or maybe I'll just informally start. We'll just wait for some 2-3 minutes. So I'm very happy to be as part of uh, this program. And this is always pleasure to be part of FOSSEE. And whenever they call, I think I could not resist. Only thing is I could not travel physically all the way to, yesterday to uh, Bombay. But otherwise, I'm very happy to be part of the FOSSEE and OpenFOAM initiatives. Whatever small we could learn, we could share, and I think it is always nice. And uh, for the participants, I think this is a very good opportunity for you to learn something which is which will be a clear differentiator in terms of the CFD knowledge or the tool that you would like to know. And I would wish that after this workshop, you would take it up, some of the case studies, or you will become intern, you will become long-term intern or semester-long intern, and you will continue uh, to work for the true spirit of learning of this open form tool. So that's one. If that happens, I think that is what will make all the FOSSEE team members also happy. They are all striving just to make sure that everybody learns this open source, free and open source tools, be it open form or something else, also in the other FOSSEE forums. And we will practice in our workplace and then help to promote this. That's a very single objective of FOSSEE, and I'm sure that all the participants will also work on that line. Now, this is going to be a very small session in sense. I'm just going to introduce multi-phase flows. Let me just, I hope my screen is visible. In case if my screen or audio is not visible, I would request one of you to unmute and then speak so that I can correct myself. Uh, in this talk for the next 30 minutes, I'm just going to introduce the snapshots of what is multi-phase flow and what are the broad modeling methodologies for the multi-phase flows, and then leave the session and to be continued by, and then from FOSSEE, they will take it on 2 sample cases. One is, I think, a droplet dynamics, and another is on the bubble column. So that's I think the plan for this session. Now, before that, this is something and when an interesting website which I want all of you to look into it if you are a fluid mechanics enthusiast. I'll just, for want of this thing, I'll make my video off. Yeah. This is called Gallery of Fluid Motion. If you just go to Google and then put Gallery of Fluid Motion, this is one of the first link. You will also have a YouTube of American Physical Society which hosts this. but you will get to this website. And if you click here, previous galleries, right, you can go into any of these, and you will be able to see fascinating videos of how different fluid contacting patterns are there, right? Some of these are available in YouTube, some of these are only available in this website, but this is something, a source of an enthusiast if you are a fluid mechanics. This has lot of different types of fluid flow motion in terms of liquid, gas, liquid, solid, and so forth. But just have a look into it. So this is what first I just want, before even I start the presentation, I just want that please look into this gallery of fluid mechanics. So if you just go to Google, put gallery of fluid motions, you will get into this. And this is from the American Physical Society. Now, with this as a starting trigger, we will focus now on what is multi-phase flows. And before I begin, before I go into the technical part, I wish to first convey my gratitude to Professor Kannan Moudgalya, Professor Janani, Mr. John, I think, who is actually who is supposed to is conducting this open forum sessions, and I think he is also going to conduct a follow-up session. And of course, the whole part of the FOSSEE team, Payal, madam, and the audience. I have kept the presentation very simple so that the idea is not to make everybody an expert in just 20 minutes or 30 minutes, but to introduce to them what are the salient features of multiphase flow. These are some of the references. You can go back and read them, and that will help you to learn a little more better on CFD and multiphase flows. Especially if you wish to do something in terms of chemical reaction modeling or involving reaction, I would refer you to, I would help you to read the Jacobson's book. This Crow's book is like a kind of standard multiphase handbook, which will help you know about the different technicalities with respect to the multiphase flows. So by now, I think you are very clear that what you are doing in fluid mechanics or in CFD, we are trying to simulate the fluid flow within the concept of something which is, we call it as continuum. What do you mean by continuum? In a sense, we don't see the molecular phases. Now, if you see on your left here, let me just be the slideshow more. If you see here on the left, what you see here is actually a water molecule, but this is a molecular view, and you will see a lot of empty spaces. This is not something that we are seeing in fluid mechanics. What we see in CFD is something like this. We see as though the space is continuously filled with the fluid. This concept of continuum is based on something, a dimensionless number, which we call as Knudsen number. Now, there are slight differences. Some people write as lambda by L, and some people write it as lambda by L, and some write it as L by lambda. That does not matter. Hello?
Yeah, your slide is not in full screen mode. Click on the display setting.
It is not seen.
It's not in the full screen mode.
Okay.
Click on display setting.
Yes, just a minute.
Top. And duplicate slide though.
Yeah. Are you able to see now? Thank you.
Yeah. Thank you.
Yes, fine. Yeah. So that means it is either lambda by L or L by lambda. Lambda actually tells the mean free path of the molecule. So that means between two collisions, how much distance the molecule travels. L is a characteristic dimension of the system, right? And I'm sure that all participants would have gone, have at least a fair idea of what are the governing equations that we solve in CFD. We solve primarily the continuity equation, which is actually the equation of mass. We solve the Navier-Stokes equation, which is the momentum balance equation. Obviously, when you have energy, if there is a thermal difference or there is a temperature distribution, we solve the conservation of energy. And if there are reactions, we solve something called species transport, which I have not written here. All these are called the transport equation. Now, all these are again tied to something which is called control volume. We are taking a volume which is so small, yet we will not see any discontinuities. We will still see matter to be continuous within that small, it is infinitesimally small or a fictitious volume. So that's the concept of control volume. Now, with this, we can represent all the equations that we use. I mean, the mathematical model based on which CFD, we are predicting the fluid flow as one equation which is represented here. In this, if you change this phi to any of these, you will get the respective equation. So that means if you make this phi as 1, you will get it something called continuity equation. Instead of this phi, if you make it as velocity, which can be u, v, or w in terms of the respective direction, then you will get actually the momentum balance. And obviously, similarly for energy balance and the species balance. These are nothing but the flux terms. These are nothing but the molecular diffusion terms. These are the source terms of the sink term. For example, for the Navier-Stokes equation, the source is typically the pressure drop gradient. So that means the pressure difference across 2 points acts as source. And similarly, the gravity term acts as a source because that causes the fluid motion. So it is actually the source. Now, what is this diffusion term in terms of Navier-Stokes? This is basically given by the Newton's law of viscosity. If it is going to be a laminar flow, we will just incorporate Newton's law of viscosity. Otherwise, if it is a turbulent flow, then we need to add the turbulent contribution to the shear stress distribution also. So we can represent this as one equation wherein by changing this terms of phi, you can get the respective transport equation. All these transport equation will follow this general principle wherein accumulation plus net outflow is equal to net diffusion plus net source flow. Now, why I have given here as net, the word net denotes here, it is like output minus input. So when I say net outflow, it is outflow minus inflow. Why I'm saying is net diffusion, because diffusion can occur both at the inlet and the outlet. So this is net diffusion. This is like out minus in. Similarly for the source term. Right, and all these terms are usually per unit volume per unit time, right? Somebody has said the negative pressure gradient is missing. Yeah, here I have not incorporated the sign. Actually, I have just told what are these terms. In fact, for the gravity also, depending on what direction the flow is there, this will actually have plus or minus. So that's perfect. Somebody is very sharp. So here I have not told the signs. I have only told the broad nature of the term. Depending on the flow direction, depending on how the flow is orientation, you will actually have the sign convention also being added into it. That's why all these things are in return generally as net. Now let's go into the multiphase flows. I'm just going to very quickly move through different types of contacting patterns that you observe. Now the difference between this is for a single phase flow. What you see in slide 8, this transport equation, this is actually for a phase. This is not for multi-phase. This is so long what you have been doing is for a single phase flows. If you have a liquid flowing through a pipe, if you have a water flowing through a pipe, or if it is a stir tank, we are only focused on one particular fluid flow. But what happens in multi-phase flow is more than one phase flows. So that means you will have either a gas liquid, you can have a liquid, you can have a liquid solid, or you can have a gas liquid solid. So more than one phase, more than one thermodynamic phase coexist in the system. This is what, before the start of the presentation, I asked you to even check into the gallery of fluid motion where you can see different type of contacting patterns. Now, based on whether they are horizontal flows, vertical flows, whether they are gas liquid systems or liquid systems, we can have different types of these contacting patterns. So, for example, this is called dispersed phase flow. Why it's called dispersed phase flow? Because you have one phase which is almost continuous, which you see in light blue color, and you have another phase which is like here droplets seen all over the system. So this is something called dispersed. Whereas if you see in the bottom, these are called stratified flows. Why they are stratified flows? This is primarily one fluid phase, and this is another fluid phase. So you primarily have two fluid phases. They are still co-flowing, but they are only in contact through this surface which separates them. So that is why this is stratified flow. This is in terms of horizontal gas liquid flows. You also have this in vertical flows. So this is the picture for a vertical flow, where again you will have something like a dispersed phase flows to something like a stratified or annular flow in this case. These flow regions and how they occur and what condition what will occur, it all depends on the hydrodynamic parameters of the operating condition. So different people have given something called flow regime map. Now this flow regime map helps us to understand at a given condition which of these contacting patterns happens. And now, like for example, what you see here is a contacting regime map for gas liquid system, but now it is written in terms of flux. Now you can again have, this is for horizontal flow, this is for a vertical flow, again in a different velocity as the abscissa and in the ordinate. This is actually for a three-phase flow, so where you actually have a aqueous, you have an oil phase or a organic phase, and then how it gets dispersed. Right? Now this is for a gas solid system again, now where again you can have multiple patterns. Now the idea is something like this. So what we know as of now is, if there are more than one phases coexisting, then there can be different flow patterns, and these different flow patterns affect the performance of that particular equipment. Now that equipment can be a two-phase flow heat exchanger, that equipment can be a reactor in a sense. If you think of a petrochemical complex, if you think of refining systems, all these are primarily a gas liquid systems, right? Or gas liquid solid catalytic system. Their performance in terms of their reaction, or how much heat can be recovered, or how much a particular process can occur, depends on how these phases get distributed. This distribution of phases affects the contacting area, and this contacting area eventually affects what is the performance in the system. So that means we need to predict these performance based on these hydrodynamic features. Now, one thing which I'm shown here is from one of my colleagues along during my PhD times from NCL. So what they have done is taken a boiler, right, and then they have tried to predict what happens in a boiler as the heat is being conveyed and it goes to the different primary and the secondary heat exchangers. What you see here is how is a flame zone, and this is how the temperature distribution happens, and eventually how the heat is being convected. Now, if we want to model completely this, then that means we need to model this contacting pattern. We need to model how these two phases coexist. Now, that means we need to predict now how a dispersed phase and a continuous phase, a primary phase and a secondary phase flows together. What happens, how they get distributed, what would be their phase holdup. What do you mean by phase holdup is, on a per unit volume, how much of one phase will be distributed in another phase, and whether both of them are going to affect one another, or it is only one way it is going to affect, or it is the turbulence of also both the phases are going to coexist. All this will determine how this multi-phase flow pattern exists. Now, with this, something what we broadly have in the modeling of multi-phase flow is something called volume of fluid, Eulerian-Lagrangian, and Eulerian system. I think after this, I just want to write and then show. So I'll go here. So that means we broadly have three types of modeling patterns. So one is the Eulerian, which is also called the two-fluid model. We have something called Eulerian-Lagrangian, which is the dispersed phase model. This is called dispersed phase model. And we something have volume of fluid. All this depends on what are we interested to see, or that means to simulate. If we are interested, suppose if we are interested to see the surface or shape or how the interface between two faces exists. So that means if you have a chamber or if you have a system, let's say this is filled with gas, and if you put a droplet, if you put a liquid droplet, you know that as the liquid droplet falls, it may change different shape. If you are interested in capturing this surface, if you are interested in capturing this surface, then this we do by something called volume of fluid approach. So in volume of fluid approach, we track the interface. We track the interface of each of the dispersed phase. So that means if there are 10 bubbles, we will capture the interface of all the 10 bubbles have to be tracked. It's not just one. Suppose if I put multiple droplets here, so that means each of these droplets, for each of these, we need an equation. So that means if there are n droplets, we will have n equation to track n surfaces. Now, in some situation, this is what is the objective. The objective is to track the shape. The objective is to track the surface. Like for example, where this could be important. Suppose let us think of a spray where you are spraying a fuel. It can be a fuel injection system, so as part of automobile, or it can be as a part of a burner. Now, if you spray a fuel, the injection characteristics will affect the size of the droplet or the bubble, right? Eventually, the liquid droplet, the fuel droplet has to vaporize, and that vaporization will affect the combustion dynamics. Now, this not be just in the fuel system, you can even think in terms of a deodorant. So if you have a deodorant spray, now we use a lot of liquid deodorants. When we spray the deodorant scent vaporizer, we get it as a liquid droplets, and the size of the droplet and the shape of the droplet will eventually govern how far is that deodorant is effective. In a sense, how far we see that particular vaporizer, we see that particular scent or deodorant as effective. If these are something that we are going to model, then that means we actually need to do the WOF. So in WOF, what is the primary equation? You actually have one transport equation for the primary phase and one each for each of the secondary phase. So this is essentially the same equation that you have seen as Navier Stokes, but only thing the number of equations are more, and how they are coupled, their interface is coupled by the surface tension force, because it is essentially the surface tension that helps you to track the interface. So the two phases are getting coupled through the interface momentum transfer. So in that interface momentum transfer, one of the key part is actually the surface tension of one phase in another. Now, in some cases, we are not interested in shape. We are interested in how much of dispersed phase is present. So when I say how much, it is volume of dispersed phase to the total volume. We are interested in this fraction. This fraction is called phase holder, usually given a symbol epsilon. So epsilon of I means volume of the dispersed phase I with respect to the total volume, right? Suppose if you have a system here, which is actually having a primary phase, and suppose if there are now secondary phase, whatever I am showing in blue color is actually the secondary phase. Now, what I'm drawing is not the actual shape. We are not worried of actual shape or size, because you cannot see the shape or size in terms of the EE model. But what we wanted to know is what is the volume of this, whatever I have represented as a blue phase, divided by the total volume. So that means, is it 10% of this phase is occupied by the dispersed phase, 1%? This is what is something of interest. So now the objective is not the shape, not the size. We are not worried about the shape or size. We are worried about where is the liquid, or where is the dispersed phase, or where is the gas, which is the dispersed phase. It's present in the primary phase. So in the matrix of primary phase, where are the dispersed phase located? So we wanted to know what is the dispersed phase holdup and its distribution. Now, when I say distribution, I am not talking about size distribution. I am talking about how epsilon varies with respect to XYZ, right? With respect to position, how it varies. Suppose if you have a column, say let's say a bubble column, which is, let's say, filled with liquid. And in that, suppose if you spark gas, so if you spark from gas, it may form bubble. Remember, what I'm drawing now in blue is not the actual shape. I'm just figuratively representing as though there are like a gas phase. Now, gas phase, this could be like this. Now, if you clearly see in this cross section, sorry. Yeah. Now, if you clearly look into this cross section, this. Yeah. Now, if you clearly look into this cross section, it is not everywhere that the gas is there. Gas is there in this region more, whereas it is very less in the other region, right? So this is what is called the distribution of the holdup in a particular column or in a particular reactor. We are interested to predict this. Why we are interested to predict this? Because this holdup again tells how much phase is there. This how much phase will tell whether reaction will happen, or heat transfer will happen, or mass transfer, phase transfer will happen. And this will eventually govern what will be the output. What will be the output from that particular column or that particular equipment. So we are interested in this phase holdup. If this is what is your interest, then we do something called TFM, which is also called EE or Eulerian or two-fluid model. In the two-fluid model, you have one equation for the primary phase and one equation for the dispersed phase. In contrast, if you see the volume of fluid, if there are 10 bubbles, there are 10 equations for each of the bubble. Here you don't have 10 equations, you have only one equation for the primary phase and one equation for the dispersed phase. And these are coupled. How are these two equations connected? Because if you don't connect these equations, then it's like they don't talk to one another, and then you cannot solve them and get it. So they are connected by something which is called momentum exchange factors. Now, we know this factor for a long time, but not in this word. Like, for example, drag force. Drag force is one type of momentum exchange factor. There are other such forces also, something called lift force. You have called Bassett history force, and so on and so forth. So that means these are nothing but interaction terms. They are primarily force terms. They depend on how far is the velocity difference is there between the two phases. So what I write here as del U is nothing but velocity of the primary phase minus velocity of the dispersed phase. It can be written as either way also. So this force is proportional to the difference in velocity between the primary phase and the secondary phase. It is proportional to the what is the area of the dispersed phase. Obviously, it is proportional to the density difference between the continuous phase and the dispersed phase, or the primary phase and the dispersed phase. And there's obviously a proportionality constant, and the proportionality constant is nothing but the coefficient of that force. So if it is a drag force, it is called the drag coefficient, or if it is a lift force, it's called lift coefficient, and so on and so forth. Now, this momentum exchange factor is what needs to be introduced in the model. So when we simulate a model, we will show in the next session that we will specify these forces. Predominantly, this drag force is what is specified, and there are different correlations available for this drag coefficient. So when we specify this drag coefficient, we will end up simulating the two-fluid model or the Eulerian model, wherein the objective is to get the hold-up distribution. Now, I think it's close to be 2:30, so I'm just stopping here. I'm not going in detail about Eulerian-Lagrangian model, but I'll just tell you what is the objective behind Eulerian-Lagrangian model. In the Eulerian-Lagrangian model, the focus is to track the motion. Track the motion of the dispersed phase. So if you are interested in shape and size, we do WAF. If you are interested in the phase hold-up distribution, what is their volume percentage, how are they present, then we do the two-fluid model. The Eulerian-Lagrangian model, here we track the motion. We are interested in the path that is traveled by the dispersed phase. So based on what is expected objective in a multiphase flow, three different modeling approaches are being used. I think in the practical session, you are going to take a single droplet and do it. So you are going to do a droplet. So that means where you will take a single bubble. You can also take a single liquid droplet or a bubble, and then see how the shape changes. That you will do about WAF. And I think then you are going to see something in a bubble column. So in a bubble column simulation, you will take primarily a column, fill it with liquid, and then you will sparge it with a gas, and then see how the gas distribution occurs. So this is primarily the hold-up distribution, right? That is what you are going to see in the practical session. So I think this is enough for a very, very brief introduction. Anything else, Mr. Pinto?
Sir, only if the participants have some questions.
Yeah. Okay. For detecting cavitation, what is recommended? Usually is to, okay. So if you want to use, if you want to detect cavitation, right? So the from your question, your idea is you want to have cavitation to be seen. So that means you want to simulate this. Now that means you don't want to see the bubble size or shape. You are primarily interested to see how much volume of a given space is being occupied by the cavitating bubbles. If this is the case, we can do by two-fluid model, but only thing we need to add something called the source term. Now, why we need to add a source term? CFD by itself does not know that it has to change a liquid to a vapor state. Because usually when cavitation happens, the pressure in a particular point goes below the saturated vapor pressure. So if the pressure in a liquid goes below the saturated vapor pressure, you will have a liquid to vapor transition. This liquid to vapor transition is the result for generating that vapor. This CFD will simulate. Okay, it will simulate and it will show you that at a particular point, the vapor is less, the pressure is less than the saturated vapor pressure. But this CFD will not have implicitly. We need to write this as a subroutine, or you need to give it as an external code, right? So what I mean by this is you need to tell how much vapor needs to be generated. So in a sense, the rate of generation of vapor. This rate of generation of vapor anyhow is proportional to this pressure drop. What I call this as pressure drop is not the actual pressure drop in the fluid space. It is the pressure drop in the fluid minus the saturated vapor pressure. Only if this term is positive, this source term will get activated. If this source term is not, if the pressure does not, only if it is becoming negative. If it is becoming less than that, it will get activated. Otherwise, if the pressure is greater than the saturated vapor pressure, this source term will be off. So that means you will not see a vapor. I think that's on the cavitation question. Any other method possible to detect cavitation? I think if you're asking in terms of experiments, how to detect, one way to detect is to have an ultrasonic horn. If you see papers on cavitation, they would usually have an ultrasonic horn. So there's something like how we have a medical stethoscope, right? So we can have that stethoscope attached to the outer part of a system. It could be a pipe or it could be a reactor where you are expecting a cavitation. And because when these cavities burst, they release sound waves, and these sharp sound waves can be detected by these stethoscopes, and that will act as a detection of the presence of this cavitation. There is not there is a new part development. Testing will definitely not able to get it, but it's okay to make sure there is not excessive cavitation. This is for new part development. Okay. So we can't use X-ray because, in a sense, it's not going to be a very permanent. When the cavitation happens, the bubbles are generated for a microsecond, right? And that may not be detected by an X-ray, right? X-ray, to detect an X-ray, you need some kind of interference with the X-rays, right? So that means you may give an X-ray, or let's say it could be a gamma ray tomography or whatever it is, and obviously you will not be able to focus this on a very large part. The best, easier way is to use the sound waves itself, because at least it is non-harming. Because having an X-ray for a very large part, I don't think it is viable, because these are ionic radiations. So it is better to use sound waves to detect, sound horns, or what you call as stethoscopes, to detect. Yes. Right. Okay, thank you. Okay, so I think that's all I have for the day, and I wish all the participants to have a very good practical session with John. John, you can carry on.
Yes,
you.
sir. Thank
Yeah,
you so much,
thank
sir.
you, sir.
Thank you.
Thank you so much. It was a wonderful session as usual from Professor Naren. Yeah, so for Professor Naren, we have Mr. Pushkar and Mr. Nikhil who have joined the advisory board of FOSSEE, OpenFOAM FOSSEE. So they are also with John today in the lab. So John and Evan, they are in lab, and Mr. Nikhil and Mr. Pushkar, they are also there.
Oh, that's great. Thank
Yes,
you.
sir.
That's nice. Yeah.
Okay. Thank you, sir. So we'll move ahead with John's.
Thank you. Yeah, carry on. Carry on. Yeah.
Okay.
Okay. Thank you so much, sir. It was a really insightful session. I hope the participants are now aware of the various techniques and when to use which technique. So, sir has presented it really well. It's always good to have sir. Breaks down the concepts into some easily understandable parts, and it is very good for the beginners. So, thank you, sir. So, we will move on. I will just share my screen quickly. Okay. So, just give me a moment. Yeah. So basically, I have 3-4 cases over here. So we will try to cover as many as possible, because we also need to give time to Mr. Manzil. Yeah.
Sir,
Who will be
increase the font size, please.
okay. Yeah. I hope it is visible now. Yes.
Yes,
So, yeah. So after this, we will have the session on dynamic meshing. So we have around 1 hour. So we will go over as many cases as possible. So we will start with, so here, as sir has mentioned, our cases are divided into two parts. One is which is based on the VOF. Okay. The ones which are based on VOF are the VOF bubble, dam break. Okay. VOF bubble and dam break are based on the, what you can say, VOF approach. And then fluidized bed and bubble column are based on the two fluid model, that is the Euler-in model. So these are the different cases. So the last thing that sir discussed, right, was the Eulerian Lagrangian approach. So basically that requires DEM, and we are not going to do that, okay, today. So if you want any information on that, we have previously conducted a session in February, so you can search on YouTube, right? So we have some recorded sessions that are available in which the theory and some practical applications of DEM are discussed. Okay, so let us move on and let us look at the first one, that is VOF bubble. So again, what are the case structure is similar, right? You have zero, constant, and system folder. Now in zero folder, we have something called as alpha dot water, and then PRGH and U. So in this case, right, we are solving for the phase fraction. So alpha means the phase fraction. That means what is the volume of the phase to the total, what you can say, total volume of the cell volume. So that is our phase fraction. So we have one file in which we are specifying what is the boundary condition for this phase fraction at the different phases, at the different patches. Sorry. So what are the different patches? So first of all, let me show you the what you can say, how the case setup looks like. So I will open the case that is run already. Yeah. 1 minute. So you see, this is our setup. Okay. So what we have is we have a, actually this is not, this is in 2D. So just wait, let me hide these controls. Okay, 1 minute. Yeah, I'm trying to move this. Hello, am I audible now?
Yes, John.
Okay, okay, thank you. I think on this control, by mistake, I clicked on how do this. Yeah, okay, I'm keeping it. Yeah. So 1 minute. I think I'll go back. You may have missed what I was talking about the block mesh. So, so in the block mesh, we have three walls. That means the sides and the bottom is of type wall and the top is of type atmosphere. So this is our case setup. Now we have to look at the boundary conditions for this. So in alpha dot water, for all the walls, that is the side and the bottom, we have given the boundary condition of zero gradient. This means that the phase fraction doesn't change near the wall. Between the cell and the wall, it is same. Now, this also means that we are not modeling for any contact angle. Okay, if we give any contact angle, then zero gradient basically means that the contact angle is 90 degrees. So the interface is at right angles. We can give a contact angle also in this place. So that is also possible if we want to simulate that, if that is what we need. Then for the atmosphere, we are giving an inlet outlet type of a condition. And we are saying that the phase fraction, that means we are saying that we are allowing for reverse flow. And if there is reverse flow, then alpha dot water will be zero. Okay, that is what we are trying to say over here. Then the next is PRGH. Now in PRGH, for all the walls, we are giving a fixed flux pressure boundary condition, right? And for the atmosphere, we are giving a total pressure. This is generally used, when we want to simulate, say that like the outlet is open to the atmosphere. So then we simulate that by considering the total pressure. And default faces are just front and back, so they are empty because we are doing a 2D simulation over here. So that is a PRGH folder. And velocity, if you see, all the walls are of type no slip. So side and bottom are no slip. And the top is pressure inlet outlet velocity. Okay, this is more like a zero gradient type of a boundary condition. Okay, but again, accounts for reverse flow. So this is zero. In constant is where we are going to specify the properties. So if we are adding some turbulence, then it will be mentioned over here. But this is a laminar type of a simulation. So we have kept the turbulence to be off. Now in the transport properties, here is where we need to specify the phases. Okay, so we have only two phases, that is water and air. And for each phase, we will specify their transport properties separately. So for water, the transport model is Newtonian, and we are specifying the viscosity and the density values. Okay, for water. Similarly, for air, the transport model is Newtonian, and we are specifying the viscosity and the density. Now, sigma is the surface tension. So surface tension between the air and water. So that is also given. So these are the properties that are needed. Okay. So this is in the zero constant folder. Now in the system, we have gone over the block mesh utility. Then decompose paradigm, see, it is used if we now the mesh size that we have is slightly coarser, right? Because this is only for demonstration. If you have a very fine mesh, you want to refine the bubbles, and get a very sharp interface, then the mesh also has to be equally fine. Or you can go for adaptive mesh refinement that we will define show in the next demonstration. But still, the mesh will be slightly finer than this. So then we need to simulate this as not as a single case, but in parallel. So that time we need to go for decomposing the domain. And in this case, if you see, we have used the Scotch method, which will do it automatically. So we don't need to specify any parameters like what will be the decomposition in the X, Y, Z direction. That we don't need to specify in this case. Okay. Now, so if you see, generally in OpenFOAM, when you are initializing temperature, pressure, or anything, we just initialize it in this zero folder, right? Say if I open alpha.water, if you see the internal field, whatever value you specify, the complete domain will be initialized by that value. Okay, so that is called as a uniform initialization in one time. But whenever you want to do a non-uniform type of an initialization, then we can't do it from here. So we have to make use of the set fields utility. So that is what this what you can say set fields dict is for. So if I open the set fields dict, So again, you see, if you have followed the topo set tutorial, this is kind of similar to the similar to it. So what I'm saying, by default, the value for all the fields alpha dot water is 1. That means I'm saying the complete domain is water for the time being. Okay, alpha dot water. Now what we are saying is, for when we have to select cylinder, because remember this is in 2D, so the bubble in 2D will look like a cylinder. Okay, that's why what we are doing is we are using the cylinder to cell function to select all the cells within that. So if this is open, so see, we want to select all the cells that lie within this domain, within this blue box. So what, how we are selecting? We are selecting them based on this. Yeah. So we are selecting that by specifying the center. You see, we are specifying 2 points, right? P1 and P2. So these are the centers of the two circular faces of the cylinder. That means this center and the center of the back face. Okay, so those are the 2 points, and we are specifying the radius. So just by specifying these, what you can say, 2 points and the radius, we are able to select all the cells that lie within this. So if I just do this, and if I do surface with edges, you will see that all the cells that lie within that, right, are selected. Okay, and those cells are initialized with water. So that is done. So first is the cylinder to cell utility. So this will select all the cells that lie within this domain. Now in all the cells, we are saying that alpha dot water is 0. So if alpha dot water is 0, that means that phase is completely air. So that's why if you see it becomes blue, that means that is air bubble. Similarly, we have initialized this. We also need to initialize the top section, right, with air, because we are not what you can say simulating. We are not allowing a, what you can say, interface from where it can leave. So we have extended the interface, and we are simulating that at the top there is air. So we are simulating the interface between water and air as well. Okay. So the top section also needs to be initialized. That we are doing using the box to cell utility.
डेटा क्योंकि हाँ वैसे ही डेटा जैसे मिनिमम हो.
Okay. I think somebody might have unmuted by mistake. Sorry for that. So we have the box to cell utility to select the cells in the top. So how do we do that? Again, you see, we need to specify 2 points. Okay, what will be those 2 points? So if I were to say that 1 point will be this corner, right, from where the blue one begins, and one will be the corner point at the top. So diagonally, how I had shown in the diagram. So by specifying those 2 points, we can select all the cells within that box, and for them again alpha dot water is 0. So this is to initialize the fields non-uniformly. So set fields utility is used for that. Okay. Yeah. So now see, we are using the solver that we are using is interFOAM, and we are again using adjustable time step with maximum Courant number and maximum alpha Courant number. That is this is the Courant number for the flow, and this is the Courant number for the interface. That is, maximum values are limited to 1. Okay. So with this setting, let us now try to simulate this and see how this works. So I think I've opened it in the terminal. Yeah. So first let me source my OpenFOAM. Then I need to do block mesh. So once I do block mesh, if you see, my domain is ready, right? And if I do alpha dot water, it is completely water. Okay. So nothing is initialized because this is the right till now we have not run the set fields utility, right? So it is taking the values from the boundary conditions file. In that we have initialized the complete domain to be of water. So that's why we are getting this. Okay. Now, after this, let me run the set fields utility. So as soon as I run set fields utility, right, it is selecting those cells and initializing it to be with water. So now if I run parafoam command, and if I click apply, so you see those fields are initialized with air. So that is what the set fields utility does. Now we need to solve this. So because it is a simple case, I'm not decomposing it. We can just solve by running the command interform. Okay, and it solves pretty quickly. So we just have to run for 0.3 seconds. So another few seconds, and then we can look at the results. Actually, I have the keys run already, but okay. So see, if it is a coarse mesh, it runs very fast even on the single core. We don't need to decompose. Yeah. So we have finished running. So now let us look at the results. Now, if I click play, you see the bubble rising, the oscillating, deforming, and going up. Okay. Now, if you refine the mesh, then you will see much more clearer behavior with this. Okay. And you see the top interface also moving when the bubble kind of hits that. Okay, that is also moving. So this is something that we have simulated. Now here we see that the interface is being tracked. Okay, this is VOF. Now if you look at this, our mesh is very fine. Okay. What if you want to use something called like adaptive mesh refinement? So now for that, let us go ahead and look for the dam break case. Okay, so so in this, I am not taking the standard dam break case. I am taking the case with dam break with obstacle. So this is already available in your tutorials. You can go. Oh, okay. Yeah. One more thing that I kind of forgot, but I will go to it is, if you look at this VOF bubble, right? If you look at this, the file name alpha.water was named as alpha.water.org, right? Means for original file. Why we do that? Okay, because if you don't do this, now if I open this alpha.water file, see what happens. This is after the simulation has ran. Okay, see, it is not responding. Why? Because the file size has become too large. Why is this? Because when we run the set fields utility, this file, the alpha.water file gets overwritten, and all the values of the phase fraction get written in this file, and this boundary condition moves down. So later on, when you want to modify any changes, then this will not open and it will create problems for you. So the best way to do it is your alpha.water file, you should name it as alpha.water.org, right? So this file OpenFOAM reads, but when it is when after you what you can say run the set fields utility, it will not overwrite onto this file, but it will create another file alpha.water. So by this way, you will not mess up your boundary conditions files in case you want to make any changes. So this is why you need to rename it as alpha.water.orig, means like the original file. So that is why all these cases you will have the alpha.water file written as alpha.water.orig. Yeah, so now I wanted to go to what I can say dambreak.obstacle this. So this, I don't know if you all have seen the dam break case. Maybe I show you the dam break case first. I'll directly go to that run folder. Let me run this. Okay. Again over here, generally, you see the setup. I wanted to show you the setup. So, oh, okay, okay. Yeah, sorry. So, the thing is why it is creating a problem is because I need to switch the versions. This version is for OS 2212. Thank you. Now, if I run, okay, I need to do this again. Yeah. So this is our domain. So if you see, our domain is, yeah. So our domain is like a room, which has an obstacle. So if I slice it in my X normal, or best way is I will reduce the opacity. I will reduce the opacity. Yeah. So now, now you will be able to see that we have an obstacle in the center, and then we have a column of water on the side over here. I guess this way. Yeah, a column of water on the side. Now, once, what is this dam rig? Basically, what we are doing is we are keeping on column of water, and it is imagined that it is held in by some sort of like an elastic, what you can say, membrane. And as soon as that membrane breaks, what will happen? That whole water will start to fall down. Now, using interfoam, we can track that complete interface, right? And we can see how that motion happens. So this is the idea. Okay, so this is how we need to set up this case. Now let me go to the, yeah, let me go to the actual case and show you the case files. So generally, again, alpha.water. Hi, see, this is what I was talking about. See, alpha.water file, because once we run the setfields utility, it gets rewritten, right? And all our boundary conditions get pushed down. And sometimes it does not open properly. So it is always best to rename name your file as alpha.water.orig. But in this case, what they are, this is a case that I have already run. Let me go to the. Yeah. If you see my alpha.water, so here for the walls, again, zero gradient. For the obstacle also we have zero gradient, and at the atmosphere, similarly, inlet outlet is there. Zero gradient means contact angle is 90 degrees. Okay, remember that. And then these are some turbulent properties, PRGH and the U file. U file again, it will be for the walls, it will be zero gradient, and for the atmosphere, it will be inlet outlet. Now in constant, we have one more additional file over here, that is dynamic mesh dict. Why do we need this? Because if you see the bubble rise, we had a uniform mesh throughout. Okay, but this is additional utility, right, with which we can refine the mesh near the interface. So I will run this, and then maybe I should show you this, and then maybe you will be able to appreciate this more. This is the run case, right? So let me make a slice over here. I think this is correct. So this will give me a good slice. Mm. Yes, I'm hiding this. Okay, yeah. So if I go to the, so if I just do this, okay, I think I should keep the main box on so that this is seen. Right? Yeah. So you see there is a column of water, right? And as we hit, that column of water is breaking and that fluid is spreading, and it is moving around the obstacle. So it will go around the obstacle as well. So if we want to capture this, we want to capture that interface properly, right? So in this case, what we have done is, let me go ahead and hide this. Yeah. And then instead of, let me go to alpha water. Yeah, I'll do this. I change. Yes. So if you look at this now, okay. So we have alpha dot water over here, correct? So that means we have the initial water column. This is not actually at the initial time. This is at the first time that we are writing. So if you see near the interface, the mesh is resolved, right? And at outside the interface, the mesh is quite coarse. Okay. This is what we are talking about, adaptive mesh refinement. Okay. So let's see what happens. As soon as I play it, right, it is moving. See, if I do it one by one, okay, that domain is moving, and as that domain is moving, the mesh is adapting to it, right? Or the mesh near the interface is always resolved, okay, and wherever the interface was previously there, then that mesh gets changed again. So this is what. Hmm. Yeah. So if you see, the interface keeps getting resolved. Okay, so this is the advantage, that we can have a coarser mesh in the domain where we don't need such a lot of computational effort. The more computational effort is needed at the interface. So we resolve the mesh only in that region. So that is what is needed. So this can be done by using the adaptive mesh utility, right? So for that, what we need to do is we need to use this dynamic mesh dict in the constant folder, and in that we need to. So this is a refinement interval. That means how often you want to refine. That you want to refine every time step, right? And in the field, I want to refine based on the alpha dot water value. That means if my alpha dot water value is between 0.001 and between 0.99, let me refine that. This is because this will capture the interface, right? Everywhere else, either it will be completely 0 or completely 1. Within this, we are capturing the interface. So there it will resolve. And for any level that is less than 10, it says you start to unresolve that. That means except the interface. Everywhere else, you start to unrefine it. Otherwise, it will remain refined. That is what. Then the buffer layers and maximum refinement is what you can see. Evan already discussed, right? Refinement level of 2. What does refinement level of 2 mean? 4 mean? Okay, that. And again, maximum cells. So sometimes what happens is if we don't, what you can say, it may keep refining, right? So we need to put some stopping criteria. Okay, if the cell limit exceeds, or in this case 2 lakh, then stop the refinement. That is what we are doing. Then correct fluxes are needed, because at the interface, when you're breaking the volume into another set, what happens is the fluxes are calculated for those each cells. So they then get recalculated for those mesh that is again done. So that recalculation, if you want it done, then you specify. Otherwise, you can leave it as none. Okay, and then if you want to write the refinement level, then this has to be true. So this is just the basic thing that needs to be added, and with this utility added, we will be able to resolve the interface. So this is something called this is something that is very good in OpenFOAM, that you can refine the interface only near the you can refine the mesh only near the interface. So for that, remember, you need to change only one thing, that you need to include the dynamic mesh dict in your simulation, nothing else. The all the what you can say code remains same: block mesh, set fields, and then interFOAM. So the working is pretty same. So the other thing that I wanted to show you was Dambrick 4-phase. So this is again a I'll directly show the result only. So this is again a very this is the same case as Dambrick. Only thing why I'm showing this is because, okay, let me open this in view and then I will show you. Okay. Yeah. This is Veena. What is the problem? Yes. What is starting? Because of the data, it is taking some time to load it. Maybe let me try again. Let me try. Okay. So here, let me go. So here you see there are 4 phases: alpha dot air. So all all the values in red is air. Okay. Then alpha dot mercury. So at the bottom we have mercury. Then we have an oil. Okay. Then we have water. So this complete domain over here, right, is filled with water, oil, mercury, and then the remaining is air. So what will happen once we simulate and once this interface breaks? Because now we have fluids with different densities, we expect that the heaviest fluid should be at the bottom, the lightest fluid should be at the top. Okay. So in this case, this is what we are simulating. Actually, I will show you the result and then let us see. So if you see what happens to water. Okay, so let me have all the alphas. Okay, so here the different alphas are there. Okay, if I click, so remember the light blue was oil, right? The creamish one was mercury. Hmm. Then the blue one is water, and the red one is air. So you see, oil is going on top of water, water is going on top of mercury, and mercury being the heaviest is sinking at the bottom. So this is how we can simulate all the different phases mixing. Let me go to the last time step, and you see what happens in the end. In the end, we have mercury at the bottom, then water, then oil, and then the last one is air. So how do we set up such a case, right? So for such a case, if you see, for each phase, there is one, what you can say, phase fraction, right? And we need to specify boundary condition for each phases. Yeah. So here at the atmosphere inlet outlet, that means allowing the reverse flow. Okay. Just let me open the ORIC file. Yeah, this is better. Okay. So here, this is what I was talking about, right? So here, you can either have what you can say type zero gradient. The zero gradient considers that the contact angle is set to 90, or you can specify the contact angle separately, like how it is done over here, right? Using the contact angle feature. Now, so it remains same. The other thing is properties will be in constant. Yeah. So in motion transport, we are not including transport properties. See phases. So if you see now, 4 phases are there, and all of them are separately defined, like water, oil, mercury, and the last phase is air. And then surface tension for each of them is given separately. So surface tension will be for a combination, like surface tension between air and water, air and oil. Here, I don't know, for simplicity, all have been given as the same value. This is the by default the case that is available in the tutorial that I'm showing to you. Okay, so this is something that you can look at and maybe modify to see how things change. Okay, the other, I have only 15 minutes with me, but let me quickly go because the other two are actually very important cases. Those are fluidized bed and bubble column. So let me go to first bubble column. Okay, so now bubble column case is the case of a two fluid model in which sir was saying that we are not interested in like these the cases that I showed you, in that we are tracking the interface between the particles. There is a separation between the phases, right? But in this case, Euler framework does not work like that, right? So how is that set up? So first let us look at the result, and then I will show you the case setup. So this case is pretty simple. So I have alpha dot air and alpha dot water. So let me show alpha dot air. So if you see at the top we have air, then we have water. The blue is water. Now as soon as I click, we see that what is happening. From the bottom, air is coming, right? And it is mixing with the water, and we have a dispersed phase. So we are seeing that both these phases are coexisting over here, right? And then we see some mixing that is happening. So with this, you can simulate that if you have a big container and if you're adding air from the bottom, how that air will move within the container, whether it will mix and go to all the regions, or it will accumulate in one region, something like that. If you want to simulate, that can be done. So this is just a template case for that, right? Now, if you want to simulate a case something like this, then what are the properties that we need to set? That is something important. So let us go those files. So let me go to the template case, become easier. Yeah. So in 0, again, we have alpha dot air, alpha dot water, these files. These files are similar, right? You will have boundary conditions. Only thing is, because we are giving some sort of like a sparging, we are saying that at the inlet, the value of the phase fraction is 0.5. That means 50%, right? And at the outlet, we are giving inlet outlet, allowing for reverse flow. Okay. And if there is reverse flow, then alpha dot air is 1. That means we are allowing reverse flow of air. At the walls, 0 gradient. Again, no contact angle between the walls is simulated. Then for the water, same. At the inlet, the phase fraction of water is 0.5. At the outlet, it is inlet outlet, but we are not allowing reverse flow of water. Okay. For the walls, we are giving 0 gradient again. Now, P will be calculated. PRGH, we are giving fixed flux pressure, and PRGH total pressure for the outlet. Okay, and the walls again fixed flux pressure. Now this fixed flux pressure basically adjusts the pressure gradient to take into account also the body forces at the at that patch. So this is kind of similar to 0 gradient, but takes into account the effect of body forces. That is what this does. Then temperature files, if we are simulating heat transfer, then we need to add the temperature boundary conditions as well. And the velocity files. So if you see, we are giving a fixed value at the of velocity at the inlet, and that is corresponding to the internal value. So here, because it is vertically aligned, the flow is along the positive y direction. So our velocity is 0.1 in the positive y direction. at the outlet, we are having a pressure inlet outlet velocity type of a boundary condition, right? And at the walls, it is no slip. So we are giving a fixed value of 0. Similarly, for the water, again, we have the same water. So we are not injecting water, right? So water, the velocity will be 0 throughout. Only air is coming in. So that's why the velocity will be only for air. But let me go to constant. The main so the main file is the constant file. So G will give you the acceleration due to gravity that you need to specify. Again, this will be in the negative y direction. Then we will the momentum transport between air and water. That these are the transport properties. Okay. If we are simulating for turbulence, then we need to specify. Here in this case, we have set it to laminar for both. Then thermophysical properties. This is something similar to what we discussed in CHT. So this is used to specify the properties and how the properties are calculated based on change in pressure and temperature. Okay, so this is the class that does that. Okay, now what is the most important file over here is this phase properties. This is something that we need to look at in detail. So here we see that there are two phases, air and water. Okay, so air is our dispersed phase and water is our continuous phase. Okay. Now for air, what type of model are we using? We are using the pure phase, and the diameter model is isothermal. Okay. So now what is this diameter model? So if you remember, Professor Naren said something that we need to the coupling between the phases is done by the drag force. Okay. And drag force is calculated by the relative velocity, the density, and the area of the area of the interface that is there. Okay. So, but here, because all the phases coexist, then how do we calculate that area? So to calculate that area, we consider that these phases are made up of particles of small diameter. Okay. So that's why we need to specify that diameter. So we can either specify, as in the case of water, a constant diameter. That means water will be considered made of particles of constant diameter, particles, bubbles, whatever you want to call them, of constant size, and that will not change throughout the domain. So, but air is considered to be based on the isothermal model. That means the diameter changes only with pressure. So as the bubble moves from higher pressure to lower pressure, its size will change. So that's why that is how this isothermal model works. Okay. So your size is related to the pressure in the medium. So if the pressure decreases, the size will be more. Pressure is high, the size will be less. So that is what is this isothermal model. And in constant diameter model, the size is fixed. Okay. And this size is what is used for the calculation of the drag. Okay. So based on this diameter, the interface area comes into picture. Based on this interface area comes into the picture, and based on this, the drags are calculated. Now there is something called as blending. So if you see, this is a case of what you can say bubble column. In this, in some regions, right, where the air is kind of fully mixing with the water, what may happen is the phase fraction of air becomes too high and the phase fraction of water becomes less. In that case, that may become a system in which water becomes the dispersed phase in air, or in some cases, water quantity is more, air quantity is less, and it may become that air is the air is the dispersed phase in water. So both of these can be there. Now, what this blending does is, whenever you are applying a drag model, the drag will always be based on whether air is flowing in water, water is flowing in air, or both of those mediums kind of coexist. So that is decided based on this blending factor. So here we need to specify what is the minimum fully continuous alpha phase and minimum partly continuous alpha phase. That means for any phase fraction less than 0.1, it will be considered as a dispersed phase, and for phase fraction more than 0.7, it will be considered as a continuous phase. So this kind of brings that limit, and based on this, the blending is done. So it is decided whether one phase is dispersed in the other, and then the drag forces are what you can say set accordingly. So here you see the default blending, if we don't specify a separate blending, then this default blending will be used for all the models. But for any specific model, you want to change that, then you need to write the name of the model and then specify a blending for that. So here they have said a default blending of 0.7 and 0.3, but for drag, they change it to 0.7 and 0.5. Okay. Now, if you see the surface tension value between air and water has been given. Interface compression, this is there because this model allows for sharpening the interface, but then that is of no use for us in this bubble column. Okay. Then the aspect ratio. Aspect ratio generally says what is the shape of the bubble, right? Whether it is spherical, elliptical. So here we are saying that it is constant and it is spherical in nature. Then drag. So if you see for drag, that is air in water, right? That means air is a dispersed phase. So air in water, the name only suggests that air is a dispersed phase. There you use the Schiller-Newman drag model. Okay. Now, if water and air is there, then again use the Schiller-Newman drag model. Okay. And air and water means if both the phases coexist, then use the segregated type of a model. Okay. So this is to account for the drag. Remember the drag, then drag is the force that is kind of giving the momentum exchange. Okay. Now virtual mass. So now virtual mass generally, see what happens is whenever one phase is moving relative to the other, there is one like an inertia force will be acting on the other. So that is taken into account by this virtual mass. So here one virtual mass coefficient of 0.5 constant coefficient type is been added. Okay, to this will account for the force due to the virtual mass. Now heat transfer. So if you have to simulate heat transfer, then we need to take here in this case they have used the Rance-Marshall model for heat transfer. Similarly, if there is phase transfer that is happening, we do that. If there is lift that is being generated, we can add that. And then wall lubrication. What is wall lubrication? Generally, these bubbles, when they go closer to the wall, what happens is because of the small flow between the wall and the bubble that is there, there is a what I can say push to, that the bubble feels when it goes towards the wall, and that is modeled by the wall lubrication force. So if that is something that needs to be modeled, that is added. Turbulent dispersion, because of the motion of the bubbles or what you can say, some turbulence is generated, so that is taken into account by the turbulence dispersion. So now all these things are there. Now you say that why only Rance-Marshall, why only Schiller-Newman, why not something else? Okay, what are the other options that are available for me? If you want to know all of them, okay, somebody said somebody is talking about swarm factor. Swarm factor means if the bubbles are kind of accumulating, coming closer to each other, right? There is a group of bubbles. Then the drag on them may not be the same as these individual bubbles. So if there is swarming effect that is there, so that will change that. And for that, then swarm corrections have to be added. Now, okay, I have few minutes, but okay, just give me some time. I want to show you something. So what you can do is, if you want to know what are the various models that are available, the best way to do that is to go and look at the source code. As I told you, the one option is you just what you can say, make a naming mistake or something on one of the models, and OpenFOAM will say, okay, this is not the correct one. The correct ones are. That is one way to look at it. The other is, I will show you the other way. Okay, the other is you go to your installation directory. So, okay, that is computer. So our installation directory is in OPT. Remember OPT, where OpenFOAM is installed. You go to that, go to applications, solvers, and in that we are in multiphase. So go to the multiphase solvers. Okay. Then we are using the multiphase Euler form. Remember, because we are doing two fluid model, Euler and Euler framework, we are using the multiphase Euler form. Now in that, we have to go to interfacial models, because drag and all those things comes under interfacial models. So in that we see various drag models are there. So if you want to look at what are the drag models available, you can open them. Okay, there are n number of drag models that are available. Urgent, then Gidus for urgent venue, then Ishizuber is there, segregated, Tomiyama correlated, venue, all these things are there. Now, which drag model will be used? For that, you have to really look into the literature for all these models. Means you need to really go into this and see, where they are applicable, what is their application range and all of that. Now, if you open any drag model, you can look at the .c file. Okay, and you can, if you zoom in, you can see, look at what is the correlation that this Schiller-Newman is using. So Schiller-Newman drag models, the correlation is 24 into 1 plus 0.15 RE raised to the power 0.67. Okay, and that is something also you can search and you can verify. Schiller- Okay, just let me see. Yeah, so here, if you see, somebody has added an image. So it is 24 times 1 plus 0.15 RE raised to the power 0.687. That is what is being modeled over here. Okay, so that means you've understood this. So using this as a template, you can also modify, make your own drag model. Okay, you want to change something, you want to tune it for your specific case. That is something also that can be done. So this is regarding the drag model. Now, similarly, you can go ahead and you can look at various heat transfer models, various what you can say lift models, then swarm correction. Somebody was asking what, so swarm correction, there are again, there is one is no swarm, then swarm correction, Tomiyama. So different things are available. You can you can look into that. Okay. Uh, Apart from this, yes. So I think this much is sufficient for this. So that is what I wanted to point out. Now, for the next case, bubble column. Instead of bubble column, now we have fluidized bed. Now, fluidized bed is again a very important case because if you look at it, let me go to the phase file. That is something that I wanted to show. In this, because it is what I can say, particles, solid particles in air, the particles are always the dispersed phase. In air will never become the dispersed phase. So that is one thing. And here in this case, particle size will not change with pressure, or it will not change with temperature, whatever it is. So that's why the constant diameter model has been taken. Now over here, we have also specified something called as alpha max. This is the maximum packing fraction. That means even if the particles were to what I can say go down and I should show, I will show you the case first so that you understand it better. I will run it once. Okay. Hmm. Sure. Yes. So if you see, I start off and if I look at alpha dot particles, right? If you see all the particles are at the bottom. Okay. Hmm. But if you see what is the maximum packing fraction, okay, the maximum fraction is not very large. It will not become one. Why is that happening? Because if we have spheres which are kept one on top of the other, even if they are kept what you can say completely packed, they will not occupy the complete volume. Right? If you must have seen that video where one professor is putting some balls into a what you can say into a jar, then say is the jar empty? No, you can add some little fine grains, you can add water that way. So the volume will not completely be occupied by these spherical balls. So that's why this is the maximum packing fraction, or this is the maximum alpha that can be achieved. Hmm. So this is one thing, and then we don't have any blending over here, right? Why blending is not there? Because in such a case, you always have particles to be the dispersed phase and air to be the continuous phase. That's why no blending is needed over here, as opposed to bubble column where that dynamics may change. Okay. The other thing that is important in this case is that here the properties. Sorry. Yeah. Yeah. Something. momentum transport, right? Yeah. So here these properties, right? So even though the simulation type that is mentioned is RAS, this is not to calculate the turbulence, but this is to calculate the what I can say viscosity and all those things. Because here it is based on these calculations are based on the kinetic theory for granular flows. So the how the what I can say solids will interact, what will be the viscosity and all those things that is taken into account by the kinetic theory of granular flows that is based on or built on the RAS framework. That's why it is coming over here. But that doesn't mean that this is a turbulence that is being added. So that is one more important thing. Now, I've said many things. You may forget all this, but I want to, what you can say, share a couple of resources that you can look into before I stop for the day, because I think we have only 1 hour remaining for Manzil. So what I want to show you is, let me do multiphase simulations. 2 very important resources which I found very helpful while sorry, open. Yeah. So one is this document by Wolf Dynamics, around 176 pages. They have discussed a lot of them, but not all these cases in details, right? But you can look at some of the, what you can say, they give, they sometimes, they tend to, mention why to use which value, in which condition you should use which value. So if you get time, you should go over this and read this and try to understand the interface compression that I was talking about, right? So in especially in what I can say bubble column and all, we don't need that, but this interface facial compression is there so that we want to have a sharp interface between the what I can say let's see if it was a bubble rise, then between the air and water, because numerically what will happen is the interface will start to diffuse. So over here we add something called as a compression velocity to kind of what I can say undo that kind of a numerical diffusion, if I can say that. Okay, so this is one good thing. So here you see they have specified when to use 2 correctors, when to use 3 limiters, in which case. So they have given some very nice what you can say thumb rules. Again, this is not what I can say, if they have said use one only, you'll use one. No, this is just a thumb rule for you to take and then change based on your case, right? Specific case. This is one. And the other very important or very good document that I saw was of 1 minute. One Iranian site was there, CEMF, if I remember correctly.
EMF.IR.
Yes, CEMF. Yeah, correct. Yes, this one. So this is a very good, yeah, thank you. So this is a very good resource again. So this is done by Professor Norouzi from Iran, and he has maintained, maybe there are only two tutorials in this case, 3 actually. If you want to do some combustion modeling, and also for that also they have, but where was that? Multiphase, let me go to multiphase and then tutorials. Yeah. So they have a couple of good tutorials. So if you want more information on this, you see this is for a older version. This will work in V7 only because this is for 2-phase Euler foam. That is kind of now deprecated and we have multi-phase Euler foam. So certain things may be different in this, but the general theory, whatever he has explained in this, given a very good write-up, so that will apply even for the multi-phase Euler foam. So if you want to understand like what is this, what is kinetic theory of granular flows, he's not explained that, but what are the models that are available? He has given at least some general idea. So he's listed down the models. Like say I was talking about isothermal models. So the diameter is based on the diameter and pressure. Okay. So such things. So various models that are available. So at least this will get you up to speed. Remember this document also will not completely help you. It will just help you to what you can say understand the basics. Then you need to look into research papers, and Professor Naren suggested some good resources. Read them, then you will be able to kind of do some very good simulations on this. So I think with this I would like to now stop and then hand over to Manzil. So Manzil will now start and he will give a talk about dynamic meshing, why dynamic meshing is important, and some very good simulations have been done. So I hope that you are, you will like it. So I think I have answered most of those questions. Yeah, Ajay asked one specific question about the interfoam and inter-isoform. I'm not sure about that. Yeah. So this I will have to get back to you. Okay, Ajay, I will get back to you on this. Maybe you can write to us. I will in the chat. I will add our what can I say contact hyphen CFD ID. I will do a little bit of research on that and get back to you. Okay. So if we don't have any other specific questions, I would request Manzil to take over and start with the dynamic meshing. Uh, okay, Deepak sir, can you give sharing access to Manzil? Screen share access.
Already given.
Already given. Okay, thank you.
Thank you, John, sir. So is my screen visible?
Yes, it is visible. Make it full screen.
Okay. Hello, everyone. I am Manjul Sitaula. I am currently working as the research assistant at FOSSEE IIT Bombay under OpenFOAM category. And this training session on dynamic meshing strategies in OpenFOAM is prepared in collaboration with Dr. Chandan Bose, who is an assistant professor of aerospace engineering at University of Birmingham, UK. So the main references that we have taken for this tutorial is the OpenFOAM Wiki tutorials and the Wood Dynamics website. So you can check out these websites. There are many more tutorials available for the dynamic mesh simulations. So the main agenda, presentation, familiarize the use of dynamic meshes, the capabilities that are available in OpenFOAM, and how to use it. So the few examples dynamic are morphing meshes, slices, and MR to meshify. We will be focused on morphing session and also do tutorial. So this training aim for the two intermediate level open users, and the tutorial cases have been tested for the OpenCFD versions in the version 2.10, 2.112, and also can be run in higher versions. But we need some certain changes in the keywords to be made to be able to run the foundation versions, that is the .org version. So you can post your queries in the chat box. So what dynamic mesh? So in dynamic are the capabilities or that mesh to change during the simulation time. So anything that allows the mesh motion or the change of mesh, that might be either deformation of mesh or the movement of mesh, or might be dividing of mesh into other smaller parts. So these all comes under dynamic meshing, and this is done to accommodate the moving bodies or moving or deformations. So we can see the general transport equation, and in case of dynamic meshing, we need to include the mesh velocity. So this equation is shown just to separate the equation from the for the case of static mesh. So in static cases, we do not include the mesh velocity, and for dynamic cases, we need to include this velocity and discretize it accordingly in the moving parts of the mesh. So mesh morphing can be achieved through mesh morphing by adding or removing new cells, by sliding, or by overset meshes. So we'll come to this shortly. And dynamic meshes should be compatible with all the physical models and all solvers. So it should not be limited to any particular models and solvers. So why use dynamic mesh? If movement body, that is it, the prescription or the boundary or that's moves with the motion, those dynamic meshes or meshes of fluid structure action, or when we have on mesh, all of this we need mesh strategy. So whenever the boundary moves, the movement of the boundary, the should be transferred mesh, and the equations must be accordingly. In the we have seen that we need the mesh to be computed So this mesh velocity or displacement calculated in such when the is moving or have to refine the mesh than dynamic mesh. You can see these three. There is the mesh morph, the AMI and AMR. Mesh morphing the actual physical of mesh. There is
Hello,
a
Manjil, just 1 second. Sorry to interrupt. Actually, your voice is breaking a lot. So a few of the members, they said that the voice is not audible clearly. Even I am finding that it is, breaking. So could you please adjust your sound system and talk
No,
once
no.
more?
The problem is in the network. Its bandwidth
Okay.
is low. That's why it's coming breaking.
Okay, okay, okay. Okay, please carry on, Manjil. Thanks.
Is my sound not audible?
Yes, now it's okay. Better, I think.
Okay, so I think I'll start with why we do wind dynamic meshes. So wind dynamic is when they have to us press body motion bound or wind or in case of fluid interaction or in where we need refinement and alignment. In all such cases, the meshes or the move near to calculate mesh displacement, mesh velocity, and include in the governing equation. So you can see figures that types of mesh dynamic disease. So the first one is the morphine, and is the other mesh refinement, and your third then second one is the adaptive mesh inter, and the third the adaptive mesh refinement. So in mesh there is the so is it now clearly or is it again my sound? Hello.
Manjul, are you saying something? Hello,
Is
Manjil.
is it
Manjil, your voice is breaking. Can you check your internet connection? Maybe take a moment, check your internet connection. If needed, log in through some other source. Why means maybe your data or something, because your voice is very choppy. Just give us a moment. We are looking into it.
Hello.
Yeah, Manzil. Hello.
So is my clear sound clear now?
Yes, Manzil.
Okay. So
Yeah.
let's begin. Sorry for the disturb. So why message? So when prescribed body motion or a predefined given boundary, there are cases of fluid structure interaction that is emphasized or coupling problem, or where in cases misrefinement, we need to refine this or on by tracking any scalar or tracking a physical variable, like in of the previous Johnson has about tracking the interface. In cases, need the dynamic message and our user capability. So, I open.com, that is the open version has the capability, which is not
Hello,
able.
Manzil. I think your voice is still breaking. Oh, yeah. So, do you want to stop screen sharing? We'll share the presentation, and you want to speak.
Okay.
If that will be helpful, or uh, or till you rectify your connection, you see some other source. What we will do is we'll send some. We have one feedback form that we need to send to the participants. We'll send that. Give them around 5 minutes to fill it. Maybe we can do that.
Okay, sir.
Okay, just give us. So, participants, till this technical glitch, actually some bandwidth problem is there with Manzil. So till this gets rectified, I request you all that I will be, shortly posting one link for your feedback. Okay, kindly do that. It will just take you 30 seconds. Now, what we'll be doing is all those who have filled that, we'll get a database, and I will also share the case files for all these cases with you so that you can practice. And yeah, we have already written the email ID for you to contact us in case you have any specific query, and we will try to answer you. Okay. So you need to write to us as at contact-cfd@fossee.in. So you can write and maybe ask your doubts. We will try to answer it as much as possible. Obviously, we can't solve your problem, if you understand what I mean, but we will try to assist you in any way that is possible. Okay. Thank you. Just give me a moment. I will upload the what you can say feedback form. Please, everyone, write your correct email over there because we will be sending the case files on those email IDs. Okay. Thank you.
So participants, I have just pasted the link for the feedback form. Please fill this feedback form till we overcome the technical glitch from Manjil's side. It's a very brief form. You can take 5 minutes to fill up this form. Now, once you're done filling up the form, you can just type that done. Okay, we are waiting.
Hello.
Yes, hi Manjin. So I can see 9 of them have already filled up the form. So rest of you please fill up and then we can start. Yes, Manjil. So do you want to present? Do you want to? Do you want John to present the screen and then you talk?
Yeah.
Why is it echoing?
Yeah, Manzil, once you rectify the echo, maybe we can start the presentation, if that helps.
So, can you hear me now? Is it echoing again?
No, now it is clear.
Okay, ma'am.
Yeah. Should I present the screen, Manzil?
Okay, I will try presenting myself. Then, if it is not clear, then let me know.
Okay, okay. Yeah, please try.
I think I've been disabled to screen share.
Yeah, Deepak sir.
Right now.
No, it's not. It's not giving me access to share my screen.
I given. You are a course now already. Just try again.
No, I don't have access. So it's not showing host course to me. I have joined with two devices, so I think you have given in another device. Can you give also the access to Manjil, another? Thank you. Okay. I think this is where I left off. So is my sound clear now?
Oh, yes, yes, it's very clear. Please go ahead.
Okay, so why do we need dynamic meshes that I have already explained in this slide? So I think it was not, my voice was not clear, so let me explain again. So whenever there is a prescribed body motion or a predefined body motion, when the boundary moves, or in cases of the 3D structure interaction or two-way coupling problems, or in cases where we require the mesh to refine or unrefine. So in such different cases, we need dynamic meshes. So here are given the three different types of dynamic meshes. So the mesh morphing strategy, the adaptive mesh interface, and adaptive mesh refinement are given here. So in mesh morphing, actually the physical deformation of mesh takes place. So the mesh will physically deform, the shape will change. But in AMI, we can see that there are two regions in being two regions that are separated by an interface region. So the rotating region and the static region. So we can also call this as a master region and the slave region. So in this interface between the static and the rotating mesh, there is the back-to-back interpolation. In order to find the solution, we need to interpolate between these two regions. So in this, in the right hand side, we can see that the bowel rise simulation. So as Jones has already presented the adaptive mesh refinement technique. So we need to trace a variable. We need to trace a scalar. In this case, we are tracking alpha water at the interface, and we need to refine the mesh accordingly. So we are dividing the mesh into smaller divisions and refining the mesh. So overset, so OpenFOAM that OpenCFD version, the .com version, has the overset mesh capability, which is not present in the foundation version. So in order to access this, we need, here is the given path. So it is located in the overset folder of the SRC folder. So these figures give us the physical perspective that how the same physics can be obtained or can be achieved by using three different mesh dynamic mesh strategies. So we can achieve the same physical problem. We can approach the same physical problem using three different strategies. Like here we have used the AMI. In the center there is the mesh morphing, and in the right hand side there is the overset mesh. So for to be able to use AMI, we need the axial symmetry. So it should be axis symmetric, and we can divide this into two different regions. In mesh morphing, we can see the meshes are physically deforming. That is, the connectivity and the number of mesh do not change, but the shape and the motion and the movement, there is movement of the mesh in mesh morphing. Whereas in overset mesh, there are overlaid disconnected patches, disconnected component meshes, which can intersect each other, but they do not deform. So we can see that there is no deformation of mesh in the overset mesh. So in order to transfer the information of the boundary to the background meshes, there are interpolation methods or interpolation techniques that takes place in the overset mesh. So in order to use the dynamic meshes in OpenFOAM, we need to use dynamic mesh dictionary. We need to locate it in the constant folder. So, and we need to, in order to assign a prescribed body motion or a predefined motion, we need to assign the motion type to the surface patch, to a cell region, or to the whole domain. So the mesh motion or the type of mesh motion function should be assigned either to a patch, cell region, or the whole domain. For adaptive mesh refinement, we need to define a refinement criteria based on a scalar field. So it might be a temperature, it might be alpha water. So at present, there are also codes available where you can track based on runtime basis. So we can track the velocity gradient, which is a function of time, and then we can refine and unrefine the mesh based on the runtime basis as well. So the boundary condition for the wall should be kept as calculated or the moving wall velocity, which we will later see. So to find the solvers that work with dynamic meshes, we can type these commands. So we can go to the solvers folder and then grab this .s file, so we can see that which solvers use dynamic mesh capabilities. And to see all the source code of the mesh motion libraries, we can go to these paths, so which we will later see in the demonstration. So there are two types of generally there are two types of motion functions. That is, one can be a predefined body motion. So when we have a predefined body motion, then we can use the motion solvers. But when you need to simulate a fluid structure interaction case or the two-way coupling problems, then we need to use the 6-2F rigid body motion. So dynamic meshes have strict stability and accuracy requirements, so which is to be considered. And there are instantaneous acceleration displacement taking place in the mesh due to the deforming boundaries, so we should also be taken care of. And the CFL numbers should also be monitored mostly in AMR when we change from refinement level to refinement level. And it is extremely important to monitor the current number, because the mesh will, when mesh deforms or when there is refinement in the mesh, then the CFL number will also change. So it is always recommended to keep it beyond the threshold value by adjusting the time steps and using adjustable time steps. So also in morphing mesh, we need to monitor the mesh quality, because when the mesh deforms, this skewness is not non-orthogonality in the exchanges. So we should all keep this below the threshold value and monitor it during our simulation. And dynamic meshes are very unsteady and computationally expensive. So simply mesh morphing is the dynamic meshing strategy that involves the shape of the mesh to change. So the connectivity or the connection of mesh do not change, the number of cells do not change, but the shape of the mesh will change. And mesh morphing can be achieved by either predefined functions given to the moving boundary, or can also be we can also input the using the table the displacement of the body or the angular displacement of the body as a function of time. So we need to also monitor the CFL number, because with large time steps or body involving large displacement, this will lead to the low quality meshes. So yeah, that's the point that we need to check the CFL number and the mesh quality while using mesh morphing. So oscillating cylinder, this is the case of the oscillating cylinder. So here we can see that the solvers that mesh motion library used is the dynamic motion solver FVMesh, and the motion solver is the libfv motion solver .so. This is the library, and the motion solver you use is displacement Laplacian. So basically, there are two types of solver. Either it can be a displacement solver or a velocity solver. So if we compute the mesh displacement, then it can be called a displacement solver. And if we compute the velocity, then it can be referred to as a velocity solver. So the displacement of the mesh can also be done using the by solving different equations. So in displacement Laplacian, we solve the Laplacian equation. So we, in order to find the mesh displacement, we solve the Laplacian equation, and there are also other equations, that is the SBR stress equation when the mesh movement involves large rotations, then we can use the SBR stress, that is the solid body rotation stress equations, and solve for the mesh displacement or mesh velocity. And the one thing to note is while solving this Laplacian equation, we also need the deformation diffusivity. That is, and we need to assign or we need to calculate this diffusivity. So here we can see that the coefficient of the diffusivity is calculated by the inverse distance method. And from where do we want to calculate the diffusivity is given here, that is the cylinder. So this is the patch name. So there are many solvers, and there are many mesh diffusivity types and the prescribed body motions that are available. We will see this shortly. So the cylinder, this is the patch name, and we have given the mesh motion function. So how does our cylinder move? How does this patch move? This is the we are given the type, the oscillating displacement. So it is it moves linearly as a sinusoidal function. So we have given the amplitude and omega, and this value is for the paraview. And we also need to assign moving or velocity to the moving boundary. And one thing to add is that we need to add cell displacement in the FV solution. So how do we calculate cell displacement? The solvers for the cell displacement should be added in the FV solution. So you can see the mesh. This is the mesh morphing. In the when the cylinder is so when the cylinder is oscillating, we can see that the shape of the mesh is changing, that the deformation of mesh going on. So we can also give the tabulated data as input. We need not need to assign omega or any amplitude, but can also give the tabulated input based on our experiment. So if you have experimental data, and we can also feed that data in our constant as a .dat file, and can simulate our case. So by using that data, we can see how the simulation, how the cylinder is oscillating or moving. It is translating in both horizontal and vertical direction. So different diffusivity functions have different effect. So the diffusivity influences that the movement of the boundary to the internal mesh. So how much influence how much the movement of the boundary influences the internal mesh deformation is affected by this motion diffusivity. So we can see that the inverse distance just simply means that as the distance is increasing, we have smaller deformation, or diffusivity decreases in the as the distance increases. So we have also the we can also see the exponential inverse distance, and we have to assign the patch name, the moving boundary name. We can also define for the multiple geometries. So we can do for multiple oscillating cylinders and give a different prescribed motion to the cylinders. So either it can be same motion, or either it can be a different motion. So in this cylinder 1, we have provided oscillating displacement in the y direction, whereas in the cylinder 2, there is displacement in the x direction. So we can see that in these cases, in the right hand side figure, the cylinder is moving in horizontal and vertical direction. So one is moving in the vertical and the other is in the horizontal direction. So we can do this just by giving different type of motion function. So this is the simulation of flapping airfoil, and we have assigned diffusivity as the quadratic inverse point distance. So you can also search which diffusivity method is best for your mesh, and according to your problem, you can change this diffusivity, and you can change the solver if you want to use velocity Laplacian or displacement Laplacian or displacement SBR stress solver. So according to your problem and your mesh, you can choose between these parameters. So the last one is the 6 TOF motion. So whenever whenever there is a fluid structure interaction, that is the flow will induce the body structural deformation in the body, or the flow might induce the cylinder to move or the body to move. In these cases, we need 6 TOF body motion. So when the body is deforming due to the force of the fluid that is flowing over it. So in this case, if the body is deforming, we need a different solver to calculate or to accommodate the deforming body. But but in this case, we can see that there is no deformation of the structure. There is only the oscillation of the structure due to the fluid force. So basically, we are solving the oscillation equation, that is mx double dot plus cx dot plus kx equals to a force, which is the force is the aerodynamic force or the fluid force. And we can see that the solver uses symplectic solver, so which solves for the oscillation equation. So we need two different solvers for the fluid flow as well as for the structural flow in 6 TOF motion. And also there are other parameters that should be included while while doing 6 TOF motion, like the mass of the moving body, that the structure, mass of the structure, the moment of inertia, the constraints, restraints. So there are other parameters that also need to be addressed during using 6 TOF body motion. So that's all for the mesh morphing. Now let's begin the demonstration. So is my sound clear now, or is it still lagging? Can anyone say?
It's fine, Manzil.
Okay. Thank you. Okay, now let's do our demonstration and for the flapping airfoil. Okay. Let me stop this here. So in this demonstration, we will be simulating the flow over a flapping NACA 001 airfoil. The NACA 001 is a symmetrical airfoil, and we will be simulating the flow when the airfoil plunges and pitches. So we'll be doing it. Let me go to the next slide. So we will be the outline of this demonstration will be that we will be slightly looking at the aerodynamics of the flapping airfoil, and we will be looking at the different parameters of the flapping airfoil aerodynamics, and we will be setting off the case, and lastly we'll post-process this in ParaView. So the problem is we need to set up a case for the plunging. That is, plunging means the linear oscillation, or it can be a translation. So just to say, it's the heaving moment of the airfoil, and pitching is a rotating movement of the airfoil. So I think you know these two types of movement, and we can also, if time permits us, then we can also combine these two motions we will see this. But if I can present it in this time frame, then I'll show it. So another is to post-process the result in ParaView and to explore some dynamic mesh libraries in OpenFOAM. So what flapping motion, there are two equations. This is a simple sinusoidal equation. So in the plunging motion, we are finding the displacement by using y equals to sin omega t, which is a function of time, and theta is also a function of time. So as these both are the sinusoidal motion equations. So where omega is angular velocity, and this is the same equation. So we can see in the figure that the plunging motion is the linear translation of the airfoil, whereas the pitching is the rotational angular displacement of the, where there is angular displacement of the airfoil. So linear displacement and angular displacement of the airfoil. So we can see that when the airfoil moves up and down, there is a change in angle of air. So when the airfoil is moving up and down, in the case of plunging airfoil, not for the pitching case, just for the plunging case, let me explain this. So when the airfoil moves up or down, so we can see that there is an effective angle of attack generated due to the velocity, due to the airfoil, that due to the wing and due to the free stream velocity, we have effective angle of attack, and we can see that the thrust is being generated. Some part of the lift is being converted into thrust due to the generation of angle of attack. And we also can note that this velocity of the wing will change with time, because if you do the derivative of the y equals to sin omega t, we also get 8 omega cos omega t, which is also a function of time. So as this velocity changes, the angle of attack will also change. But in both the cases, we can see that thrust is being generated in the forward direction, so there is generation of thrust. But we have to have a certain combination of the amplitude and the frequency of the airfoil, then only we can produce a thrust, or it might also result in drag producing wakes. So this is the thrust due to lift, but there are also many other factors that will influence the movement of this airfoil, and that will influence the aerodynamic force in the airfoil, like the vortex setting, like the wake formation. So these are other things that will affect the forces or the aerodynamic forces in airfoil. So these are two different important numbers that should be considered while simulating or while understanding the flapping aerodynamics. So the first one is the reduced frequency. So reduced frequency, nothing but the ratio of the flapping velocity with the free stream velocity. So this factor determines that when the value of k is high, then the vortex remains in the airfoil for longer period of time. Whereas when the reduced frequency is low, then the vortex is shed quickly. So this reduced frequency will also have to determine the steadiness or unsteadiness of the problem or the wing. So the other important factor or the important dimensionless number. So these both are dimensionless quantity. So is the strong number, so which is the product of k into a divided by c. And for flapping wings, we can use 2ks divided by pi c, where a is the wake width and h is the plunging amplitude. So for flapping wings, the wake width will be equal to the tip to tip the distance or the length swept out by the wing while it moves. So we can see the equation here, and we can see the strong number is a function of reduced frequency and amplitude. But we also need to study these parameters independently. So the strong number and reduced frequency should be studied independently while doing the flapping case, because if the product of k into h is 10, then k might be 2 and h might be 5, or k might be 5 and h might be 2. So in these two cases, the effect is different. So we must independently observe these two numbers while doing our simulations. So this is just for information. You can also check this detailedly, go to different research papers and see how this amplitude and how this frequency affect the aerodynamics of the flapping airfoil. So I think this is clear to some extent now. So this is the computational domain that we will be using. So we'll be using the k omega shear stress transport model, and the Reynolds number where we'll be simulating is for 10 to the power 6, and we'll be using morphing mesh. And what is different is that we'll have to assign, we'll have to include the dynamic make dictionary in constant folder, which is different in than the other static mesh cases. So the only difference is dynamic mesh dict for the solid body motion solver, and for the displacement Laplacian solver, we need to include the point displacement file as well. So which we will see now. Okay. So let's run our terminal. So is my screen visible? Terminal.
Yes, it is visible.
Okay. So I'm running this in WSL in Windows. So I have used OP9 to alias the to source the OpenFOAM version 9. And let's go to our own directory where I've saved my files. So I have here moving airfoil, and here I have the cases for pitching, plunging using displacement Laplacian, and the flapping wing and the so let's go to plunge. This is and let's see here. Now let's we have our this is for the plunging motion. So what are the files required? We will see it first. So let's first see the block mesh file, because we need to first generate mesh. So the block mesh file is located so we can see that the block mesh dictionary is located in system folder. And let's see. So this is our block mesh file. So we have imported the geometry of the airfoil as the tri-surface mesh. So we can directly use the OBJ file and then import it as tri-surface mesh, like we did in the SnappyHexMesh that Ivan presented. So, and here we are using the searchable cylinder for our simplicity. So the searchable cylinder we can, so that we can use the ease of the cylinder, the coordinates of the cylinder in generating our mesh. So here we use the project command for the mesh generation. So we have projected the coordinates that are required in the cylinder. So let me show the block mesh file. The blocks. So we can see that these are the blocks and the vertices that are being generated in the left in the figure. So we have projected the coordinates of the cylinder from the coordinates to the cylinder or into the airfoil, which is required, and we will use these coordinates to later to generate edges, so that we do not have to use individual points in all these cylinders. So we can directly use the edge of the cylinder and the airfoil. So we have the 0.3, the zero vertex is located in the z direction, as you can see by cursor. So this point zero vertex is being projected in the cylinder here, and at x equals 0.3. So this is the x equals 0.3. So to show that the plane that we are drawing this block mesh is xz plane, and y is the outwards plane that is coming out of the screen. So this x is in the horizontal direction and z is in the vertical direction. So we are at x equals 0.3. There are only two coordinates of the cylinder. That is either this coordinate or either the upper coordinate. So we need to project. If we project a point in this in the cylinder at this x equals 0.3, it will be projected either to the downward lower radius downward radius cylinder, or it will be projected to the upper point of the cylinder. So if we assign negative direction, that is here, we can see that in Z we are projecting -5. So if we are using -5, then it will project the point in the lower part of the cylinder. And where if we use +5, otherwise, if we use plus direction, then it will project in the upward direction. But it is to note that this magnitude, that is 5, does not affect our meshing process. It can measure 10, 11, 12, because we only have at x equals 0.3, we only have 2 coordinates in the cylinder, that is this and this. Similarly, we project it for the airfoil, and for the airfoil, and we are doing it for the x equals to y equals to minus 0.1 plane, and other is the y equals 0.1 plane. So that is the backwards and the forward plane, front and back plane. And we need to assign the blocks. So here we have assigned blocks. So let me see, we have assigned, I will say the first block, I will explain the first block. So it is 7, 4, 16, 19. Using this, we can see here in the figure that 7, 4, 16, and 19 is one. And we have created the block using 7, 4, 16, 19 vertices, and 0, 3, 15 to it. So using this and this is, we have created one block. So that is the first block, and we have assigned the simple grading as well as age grading to these edges. So we have given the age grading to the edges, and we have graded we have given the simple grading to these directions. So you can go through these files, how are these blocks generated, and you can look at it later. So this is some complex block mesh. So you can first you need to have a basic idea of how to generate the mesh in block mesh before going to these files. Or you can also use open source GMS's software, which is also good for meshing the C-shaped airfoil. So we are projecting the edges as well. So what is the benefit is that we do not have to include all the coordinates of the airfoil in our block mesh file, but we can project the edge directly in the airfoil so that we do not have main or vertices in our block mesh file. So this is one of the benefit of using the project function. So we have defined our boundary. We have defined so our boundary is the inlet. We have the top, and there is no top and bottom. There are only inlets. In the forward is the inlet, and the top and bottom are also given as inlet, and this is given as the outlet and the airfoil patch. So these are the boundary definitions. So you can check this out later. So how we have assigned the faces and the vertices. Okay, this after the block mesh dict is ready, we need to run the block mesh command. What to dict? Okay. So see that we have our mesh ready, and we can visualize in Terraform. So you can see our mesh is ready now. So we have created a structured mesh of our airfoil. So after the meshing process is done, let's now get into the boundary conditions. So to be able to see the boundary conditions are located in the Geo original folder. So we can see that there are different files. That is the U velocity file, the pressure boundary condition to be assigned, and K, nut, and omega. So we can see that the K, nu, T, and omega comes from the K omega SST model, because we have used the turbulence model in this case. So if you want to see which model that we have used, then we can go to the constant, and then so we can see that we have used the RAS model, that is the Reynolds average Navier-Stokes equation, which just means that we are representing the fluctuating terms in terms of the average mean flow. So we have used the Q omega SST model, and we have on the turbulence. So for cases in the flapping airfoil where there is the flow separation, so the K epsilon model is not able to it is not good enough to look at the separation point. And in for cases like in adverse pressure gradient, we cannot use the K epsilon model. So and also we cannot directly use the Q omega model, because the Q omega model is dependent on the free stream turbulence. So if there is a free stream turbulence, then that will affect the accuracy of the solution. So we have used the Q omega system model, blend of which is the blend of K, which is the blend of K, K epsilon and K omega model. So after that, let's go to our boundary conditions. So as I've already mentioned in the previous presentation, that we need to assign the moving of velocity in case of dynamic mesh simulations in the U file. So when the airfoil moves, then we need to assign this type of boundary condition. So we have provided the internal field to be 1 meter per second, and at the inlet also we have used 1 meter. We have provided a velocity inlet of 1 meter per second, and we have used in the outer we have used the Rowan boundary condition, that is the inlet outlet. So when the flow recirculates, then the value of the inlet is assigned when the flow is recirculating at the outlet, and if it is not recirculating, or if it is traveling from inlet to outlet, then we will just use it just uses the zero gradient boundary condition. So and as we are doing the 2D simulation, we are keeping the front and back plane as empty. Now let's do under pressure boundary condition. So we have given zero gradient at the airfoil, and fixed value at the outlet, and zero gradient at the inlet, and type, and the front and back we have kept it as empty. Now there are also the boundary conditions for K, nu T, and omega, which is the K is turbulence kinetic energy, nu T is the turbulence viscosity, and omega is the specific turbulence dissipation rate. So you can also later see what is inside this. So let me see let me see one. Let me show you then for the omega, that is the specific dissipation rate. We have used the internal field by using this formula, omega equals to K 0.5. So you can find this formula, and you can calculate your internal field. And we have used the omega wall function. So the wall functions are basically used when the y plus value is larger. So in order to simulate the cases with the adverse pressure gradient, we need y plus to be very small, but we cannot achieve that always, because of the computation limitation, and we cannot make the boundary layer very small. So in this case, we have used the omega wall function because our y plus is greater than 30, that is from 30 to 200, we can use this wall function. So you can check when to use these wall functions, and if in the later. And inlet also we have given the fixed value, outlet we have given inlet outlet boundary condition, and front and back is kept as empty. So you can check these other boundary conditions for the turbulence modeling, because we are not focusing much on this now. So you can later check which one you should use, which is better for you, depending upon Reynolds number, turbulence simulations. So now let's go to our dynamic mesh dig file. Okay. So in the constant, as I have said, that we have our dynamic mesh dictionary. So let's see what is inside the dynamic mesh dictionary. So as you can see that we have our dynamic mesh solver as an interpolated insulated body. So before going to these, let me quickly show what solvers are available, and how can we use them. So let me So when we go to the source folder, that SRC folder, then we can navigate to dynamic mesh. So in dynamic mesh, we have the motion solvers. So let's go to motion solvers. So in the motion solvers, let's navigate to displacement solvers. So in these solvers do not solve displacement Laplacian equation. These are just solving by transformation of the point. In order to solve Laplacian equation, in order to solve the Laplacian equation, we need to navigate to the active motion solver. So which I will show in a short while. So in the displacement solver, we have the solid body solvers. So if we go to solid body solver, now we can see that the interpolating body solid body motion solver. So we have used this solver in our dynamic mesh file, like the interpolating solid body. And if we go inside the interpolating solid body, we have the source codes available. Now, if we check the source code, so if we see the source code, then we can see that it looks up for the input data required are the patches. So we have provided patches. And the other one that the input required is the COFG, as coefficient of gravity, and the inner distance and the outer distance. So we can look at these two terminal and see that what are the inputs that are required in the interpolating solid body, and we have provided the input accordingly. So this is what I want to show. And if we want to see what are the motion functions that are available, then we can go to, let me see, we can go to solid body motion functions, that is solid, you can see in my terminal, motion functions. So what are the motion functions available? We can see this. So we can see here that there are different type of motion functions. These are the predefined motion function, that is the prescribed body motion. So here are linear motion, oscillating linear motion, rotating motion, solid motion functions. So what we have used in our case is that we have used the oscillating linear linear motion. So we can see that we have used the oscillating linear motion. So let's go inside it. So there is also a source code .c file. So if we go into this, then we can see that inside this, we can see that what equation does it solve is this. You can see that vector displacement equals to amplitude into sine omega t. So I had already shown you in the slides that what are the equation that we will be solving. So we can see that we will be solving amplitude into sine omega into t, and the inputs that that it looks up for is the amplitude and omega. So which we have provided here in this next terminal. We can see in the dynamic metric file. So we have provided here the amplitude and omega as well. So this is our dynamic mesh file. Interpreting, we have used the inner distance and outer distance. So in inner distance, these values have to determine the scaling value factor to the mesh. So inside the distance of 0.01, that is, if we draw a circle of 0.01 and draw a circle with radius 4, and in the radius of 0.01, there is actual mesh movement. There is no deformation. So in between this 0.01 to 4, there is mesh deformation, and outside this outer distance 4, there is no any mesh movement. So we can assign our distance, we can assign our domain with different values of mesh deformation by assigning this inner distance and outer distance. So this is the importance of this inner distance and outer distance and the interpolating solid body motion solver. So after this, I want to show you. Okay, now let's check our. So these are transfer properties that we have used since we are simulating for RE equals to 6 case, 1 is 6, that is Reynolds number equals to 1 is 6, then we have used the kinematic viscosity value accordingly. So we have used this value to make RE equals to 1 is 6. So I think you all know this, how to set up the transfer properties. So as RE equals to U into L divided by kinematic viscosity. So in this case, we have used kinematic viscosity as this value. So that's all. Now, after dynamic mesh dict is very less, now we can now run our simulation. So before that, let's see our all-round file. What are the commands that So we are first copying the original file to the original 0.OD20 folder. That is the initial where the initial boundary condition will be stored, that is in 0 folder, and we will be running the blockmesh command and decompose path, that is that decomposing the subdomains into different domains. So we are using 6 number of processors according to my system capability. So as Jungsur has already explained about how to decompose, what are the decomposition methods. I think I don't have to provide information on that more. So I've used the parallel decomposition in this. So I will be running the simulation parallelly. So after this, now we can type the all-run command. Now you can see that our simulation is running. So I think I don't have much time to wait for the simulation. So let me go to other cases as well. Okay, I think I'll show in the Explorer. So I gave you the information. I showed the setup for the plunging motion. So what if there is a pitching motion? So if there is pitching motion, everything is same. Just we have to change some thing in the dynamic mesh dictionary. So let's go to our dynamic mesh dictionary. Okay, so we can see that we have also used the interpolating solid body solver in this case, but what we need is the origin. So this is the additional parameter that is not available in the plunging case, and we have to give the oscillating rotating motion coefficient. So when we see this motion function, that when you see the source code of this motion function, then we can see that we need to also assign origin. So this origin is computed from the from this COF, that is coefficient of gravity point. So we have assigned a coefficient of gravity as 0.500. So what does this origin means is that we are going negative direction from 0.5 in to a magnitude of 0.25. So if this is taken at the center point, and the value is measured from this point, from the COFG, coefficient of gravity point. So what does origin means is that we are moving 0.25 in negative direction from the point 0.5, 0, 0. So this is our origin, and about which the airfoil rotates. So this is our center point. So this is the only difference that can be seen in the pitching case. So all things are same. So you also need to determine the amplitude. You can vary your amplitude omega, that is the angular velocity, and check what different results that you can get. So here we have used omega equals 6.28. I think this gives us the time period of 1 second. So at 1 second, it will move from its mean position. It will oscillate 360 degrees and come back to its original position. So this is this also helps to interpret our results. So this is the case for the dynamic mesh dictionary of the pitching airfoil. So for the let's go now for the flapping. That is flapping. These all are the flapping cases. So we will combine these two motions in our dynamic mesh dictionary. uh, so we can see that there is also multi-motion available in the motion coefficient in the motion functions. So we can see that in the motion functions we have the where it is now. We have the multi-motion, so we can see a multi-motion in the terminal here. So we have used this multi-motion function to prepare the dynamic mesh dictionary file. So we have used the multi-motion function and we have combined the linear oscillating rotating motion and the oscillating linear motion into this one single multi-motion file. So we can see here we have assigned pitching and plunging and given the same amplitude, the same omega that we had done for the pitching and the plunging cases. So here you can see, and we have to assign it to a path, the path that is moving. So there is the airfoil that is moving, and the coefficient of gravity. So these are the all these parameters and values are same that I had shown you in the previous case. Okay, now let's visualize our result. I think our simulation is done now. Okay. Okay, now let's open terminal here. So I'll be launching Paraform. So let's check out for the plunging case. So this is our initial condition at 0 time. So we have prescribed 1 meter per second at the internal field. So this is the case that is being shown. So let's first look how our mesh is deforming. So okay. So as we play, we can see that the mesh deformation is taking place. That is, the mesh is changing its shape and also moving, so which is the morphing mesh strategy. Okay, now let's see the velocity field. Now yeah, we can see the vortices being formed and the circulation, the flow is circulating in the region. So if you want to clearly visualize this, so let's draw. So you can add filter using the control space and add the field to add the vector field. So yeah, the arrows are very large, and you need to keep the orientation area as velocity. Let's make it 2D first. So yeah, we can see that the for the velocity, okay, we have set this to velocity. It was before it was pressure. So we can see how the flow is bending and the flow is curling in these sections. So these vectors give us the description. This gives us the visualization that how flow is bending in these areas or is curling in these areas. If you need a better visualization, then you can just decrease this and okay. Now let's play our simulation. So here we can see that the vectors are changing the direction as the airfoil is moving. And there is also flow separation that is taking place in the leading edge. You can see here. As well in the trailing edge, the flow will the call and separate from the trailing edge with the vortices are formed. So this is for the velocity vector. So now we can also compute our vorticity. So in order to compute the vorticity, we need the gradient of the velocity. So this where we can have the options for computing vorticity. So we can just click apply. Now let's disable this, and now we can see that there is an option for vorticity available. Now let's customize this because there are some places that are very high values of vorticity, so which will not which will not visualize properly. Okay, now let's play this. So here we can see that the vortex and vorticity magnitude plot, and there are formation of vortex in the leading edge as well as in the trailing edge, where the vortex are being separated from the leading edge. So this is what I wanted to show. And one other thing that I also want to show is let's extract the wall filter. So if you press Control Space, and we can access filter by searching the filters. So let me extract the airfoil. So we have our airfoil here. Let me slice this airfoil in the warm arm direction for our okay. So here we can see, let's hide this plane. So here we can see that we have got a line of our wall that is of our airfoil. Now when we plot the velocity in this airfoil, so let's go and plot with the plot on sorted lines. What we see is we have the velocity in of our wall. That is in no slip condition it needs to assign zero velocity at the wall, but in this case we can see that the velocity is changing. That is the boundary condition. We call that the moving wall velocity boundary condition. So this is what is really happening in the airfoil wall. So this is what I wanted to show you. Now we can also plot drag and lift in this in paraview. So let me plot drag and lift. So first we need the block to be extracted, which we have extracted. Now after we have extracted the block, we need to add a filter, which is generate surface normals. So what does this do is generate the surface normals of the surface. So we need to compute shell normals and tick the box here. Now after we have generated surface normal, we need to access the calculator, and let's suppose this plot drag value. What we need to do is, since the pressure force in the acceleration gives drag, so we need to access. We need to we need to multiply the normals and the acceleration with pressure. Now this will give us a drag. So we also need the drag coefficient, because that is what we are going to plot. So in order to plot the drag coefficient, we are plotting drags divided by the, let me show my presentation. So this is the formula to plot the drag and lift. So half rho v square, since rho is 1 and half means 0.5, and v velocity is also 1 meter per second, and the area is, what is our area is the planetform area of the airfoil. So since our height in the y direction is 0.2, so we need to multiply the chord length into 0.2. So in the block mesh file we have seen, we can see that. Let me show you the block mesh file. In the block mesh file, you can see that we have minus 0.1 to 0.1. So this means that our height in the in the y direction is 0.2 meters. So in order to find the area of the top surface area of the airfoil, that means we need to multiply the chord length times the height of the block mesh in the front and back plane. So what we do is we are dividing now by 0.5, which is half, and multiplying by 0.2. This way we can calculate our drag, and now we need to integrate this over our airfoil surface. So after integrating, I think we have got. Now if we plot this over time, then we will get our drag coefficients. So I have included the figure that I have plotted in paraview here. So we can see that the drag is in negative direction, which means that the thrust is being produced. That I had said that by certain combinations of the plunging amplitude and the plunging frequency, that is the reduced frequency, we can produce drag, or the wake can produce drag, or the wake might produce lift, might produce thrust. So in our case, we have got the thrust, and in the lift, you can see that the positive and negative direction of the lift, because I had already shown in upstroke and downstroke when the airfoil plunges, the lift is in positive direction, and when it is upstroke, then lift is in negative direction. So this is the cause for the positive and negative direction of the lift. And since the angle of attack is continuously changing, we have our continuous change of the CL and CD. So here we can, here I visualizing for the okay, we have our plot ready here. If we plot CD, so here we can see we have plotted our CD. Now another way to plot CD is by going to our first, because we have also functions that are available, built-in functions of OpenFOAM that are available to that are available for us to plot the first coefficient. So this is the for in the first coefficient file, we need to assign these parameters, that is the patches, that is the rho value, and the lift value, lift direction, drag direction, then the magnitude of the velocity, and area reference. So we have used the area reference 0.2. And this way we can also plot our first coefficient, and this will also give the same result as that we have plotted in the paraview. So if you want to plot this in the Excel, then you can also plot this. So let me plot drag in Excel first. Now let me insert let me insert a chart and select data. So let's do the name it CD. and let's plot from 0.01 to now let's also plot our PD from 0.01. So we can see that we have got the same plot as that we have plotted in ParaView using the first coefficient. Let me show it in my slide. So this we have got the same plot. As in ParaView, so we can plot either of both of these either of these methods. So you can it's better to plot using the first coefficient data because these are calculated by the open source built-in functions. So we have seen the velocity contours, vortex setting phenomenon, vortex setting of the okay. In this way, you can plot the various parameters in ParaView and post-process the results. So let me close my ParaView now. Now I also have some simulation results of video animation of the this is for the flapping case. So we can see that the airfoil is plunging as well as pitching. So I have used the multi-motion function in this that I had shown you. So in order to use dynamic mesh in OpenFOAM, you need dynamic mesh dictionary that is to be included in the constant folder. Now one thing that is left to show is the displacement Laplacian. So I had said that we can also use displacement Laplacian where this Laplacian equation is solved. So let's go into dynamic mesh dictionary and let's see that we have used the motion solver as displacement Laplacian and diffusivity as the inverse distance and assigned to our moving path, that is the airfoil. So you can also use velocity Laplacian or displacement as depending upon your problem. And what we need to include is that we need to include the another necessary file, that is the point displacement file. So it is in this file where you give the motion function to the moving boundary. So in this case airfoil, we are giving oscillating displacement, we are giving the amplitude, we are giving omega. So in this way you can provide the prescribed motion to the boundary. So if you have used velocity Laplacian, then in case of point displacement file, you must use the point motion u file. So this is the only difference that between the velocity Laplacian and the displacement Laplacian. If you are setting up a case with these two different motion solvers. So yes, I think we have come to the end of our session. So I think this is the end. So I would like to thank Professor Sundan Bose, Mr. John Pinto, for their invaluable guidance, and also I'd like to thank the audience. Okay, so thank you. If you have any questions, then
Yeah, thanks a lot, Manjil. So any questions for him from the participants? Okay, if not, then I'll go ahead and I'll announce the name of the shortlisted participants now. Okay, so let me just share my screen. I hope you are all excited to know the names. So out of all the participants, all the submissions that we have got, we have shortlisted 5. Okay, so I'll just present my screen and present the names. Okay, is my screen visible? Hello?
Yes, ma'am. Yes, ma'am.
Okay, okay. So the first name is of Syed Akib Ahmed. So Syed, are you there? Hello, Syed, are you there in the participants list?
He's there. Hmm.
Okay, okay. So congratulations, Syed. The second participant. So I'm just reading out the name in order of the score. Okay. So whoever is the highest scorer is number one. Okay. So I'm not disclosing the score, but it is in the order of the score. Just a second. It's not working. Yes. So the second name is Yeshas. Sorry. Yeshas Sudarshan. So are you there, Yeshas?
Yes. Yes, ma'am.
Okay. Okay. So big congratulations to you. The third name is of Amitej. Amitej Mukliyat.
Yes,
Amitej,
ma'am. I'm here. Yes, ma'am.
okay. The next name goes Shavani Kulkarni. Shavani was there in the morning. Are you there, Shavani?
Yes, ma'am.
Okay. Congratulations. And the fifth name is of Supraja. Supraja, congratulations. Supraja Shinde.
Thank you, ma'am.
Yeah. So all of you can just switch on your video if you want to share something, your experience of solving the case. And not the case, the problem that was given to you. I'll also switch on my video. So I would like to see you all the shortlisted candidates so that we can say a hi and I can, okay. Hello, Amitej. Hi, congratulations. Syed and Shavani, Yeshas, and Supraja. Supraja, I met you yesterday. Yeah. Okay, so there are our team members, Mr. John Pinto and Mr. Ivan. And I can see Mr. Pushkar from WebTech. Hello, sir. Okay, so Shavani, Amitej, Supraja, Syed, everybody, a big congrats. So what you have to do is our team members will get in touch with you. Okay, hi Yeshas. So our team members will get in touch with you and they will handhold you so that your submissions can be converted into successful case studies. Okay, so your submissions are good enough to be converted, but some shortcomings are there. So once you overcome that, it won't take much time, right, John? How much time will they take to overcome this and to make the submissions as case studies?
The report has to be improved.
Huh.
So if they dedicate time, then maybe a week maximum.
Maximum of a week. So it's nothing. So you're almost there. And once you're there, your name will be published. I think you have seen the CFD-OpenFOAM website. If not, then I'll just share my screen and I'll let you know where your submissions will be displayed. So this is our website. Is it my screen is visible, right?
Yes, ma'am.
Okay. So see, this is the case study project. And here goes the list of the completed case studies. So as you can see, all these case studies are not done by any faculty member. They're all done by students. Okay. And these are not only the students of IIT Bombay. As you can see in the list, they are from different institutes of India. Amrita Vishwa Vidyapeetham, Anna University, Tribhuvan University from Nepal. We have a good influx of students from Nepal, from this particular university. So we are really happy and grateful to Tribhuvan that there. I mean, every year we get good interns and fellows from Tribhuvan. Even Manjil, who took the session today, is from the same university. We had two more staff members from who are alumni of Tribhuvan. Okay. So as you can see in the list, we have many more other institutes other than IIT Bombay. Okay, so actually, all of you must know that FOSSEE is an organization that trains the students. It focuses on the executable part of a software, over and above the theory part. Because for the theory part, the colleges are there who help the students. The colleges also train the students on the practical aspects also. But then FOSSEE is primarily focuses on the hands-on part of the software. So this is all about the case study project. You have the submission guidelines also. When you convert your submissions into case study, you can refer to the submission guidelines. So it's all the guidelines are there. You will also receive honorarium. You will also receive certificates from FOSSEE. And do you know about research migration project? Anybody?
Yes, ma'am.
Okay, so just like cases are small problems in CFD, research migration projects are research papers that are published in renowned journals, and the learners of OpenFOAM, what they do is they take they take the problems that are already published and they replicate it using OpenFOAM. So research migration project is one step ahead of the case study project. Okay, and we also have lab migration, but for lab migration, we would need to get in touch with your faculty members. So all of you can refer your faculty members, one faculty member who is enthusiastic enough to work with us and contribute in the lab migration project. So what they will have to do is they'll have to propose a problem, a set of problem that the institutes actually takes up in their lab courses. So so they will be the proposer of the lab migration, and then the solution provider can be either from their institute, I mean from your institute or from any other institute or from the FOSSEE OpenFOAM team as well. So there are two parties involved in this lab migration project. One is the proposer and second one is the problem solution provider. Okay, so let me stop my screen and okay, so any more instructions for them, John, to proceed forward?
Oh, we will get in touch with them, ma'am. Have a separate meet. Okay, for that.
Okay, and I hope all of you have filled up the feedback form. Okay, so based on that, we can also continue, working with you in future. And in the month of January, we will announce the semester-long internship. It will be for 3 months. And the summer internship, the summer fellowship will be for 2 months. We will announce it during the month of March. Okay, so all the announcement we announce on the FOSSEE website. Okay, and you can also, add yourselves in my LinkedIn profile. So my name is Payal Mukherjee. I'm very much active on LinkedIn. Whenever there is any, internship and fellowship of FOSSEE, I always announce it through LinkedIn. So once you get connected with me through LinkedIn, you will get all the updates, proper updates on time. Okay, so with this, I'll close the session today. Okay, so fine then. Thanks for joining, and bye-bye from IIT Bombay. Bye-bye.
Thank you.
Stay in touch.
Thank you. Thank you very much.
Bye-bye.
Thank you, everyone. Bye.